128 times faster than K computer. Another the application Nikam LETKF. This is the climate application and data assimilation for the climate the data. So this is a combined application. So for this application, we expect 120 times faster than a K computer. So, and last one is an easy to use system for the wide range of users. So our system is a system which is shared by the all over Japan as well as the from the world. So we need design the easy of use system for to support a wide range of the users. So this is the three design target, and for the during the co-design, we have to define, we have to decide the many kind of the items, including technologies and architecture parameters. So basic architectures and chip configuration and the cache size and the outboard resources and how many cores and etc. So we carried out the co-design, the effort, co-design process to meet these three design targets. So especially the low power technology is very important. So we have to get the maximum performance within this power consumption. So, okay, let's move to the overview of the Fugaku and A64FX processor. The Fugaku is the ultra-scale general purpose many core system, which has the 160,000 nodes, and one processor, one node has the one processor, and the number of cores for that one processor is 48. That means the total number of core is 4.6 million cores. The instruction set of the A64FX many core processor is the ARM with the SVE. SVE is the SIMD extension defined by the ARM. And as I said, so the processor has the 48 cores plus 2 or 4 for the assistant core, which is running the operating system function. And clock is that the 2.0 gigahertz can be boosted to the 2.2. So, and 48 core is divided by the 12 cores group that we call the CMG, core memory group. This is the NUMA cluster, NUMA core cluster. So, and this CMG is connected, sharing the L2, and connect to the memory controller of the HBM. So each HBM chip is the 8 gigabyte. So we only have the HBM2. We have no external memory, external DDR memory. So that means the memory capacity is the 32 gigabyte. And each the disconnection gives us the memory bandwidth 256 gigabyte per second. So in a total, memory bandwidth to the chip to the memory is 1 terabyte per second. So standard programming model is the OpenMP and the MPI hybrid programming, and which run each MPI process on a NUMA node, NUMA CMG. This network on chip is supporting the memory coherence. So if the programmer take care of the affinity of the memory, then the programmer can run the 48 thread OpenP program in using the every cores on a chip. So, and interconnect is the TOF-D interconnect. This is the 6-dimensional torus network, which is the extended version of the previous TOF used for the K computer. And this is the die photograph of the S64FX processor. And chip is made by TSMC 7-nanometer FinFET technologies. And you can see, so this is the core, and this is the TOF interconnect, and this is a PCI Express interface, and this is the memory controller. So everything is integrated on one chip. And the memory, HBM memory is connected by TSMC Chorus technologies. This is the TSV connection using the silicon interposer. So that means this is including the all element of the node. So it might be interesting to compare the implementation to the another processor. So this is the Xeon Skylake, the die photograph, and this is our chip is the roughly saying that 400 millimeter square, and Skylake is a little bit more than that, but almost same, the similar size. And in our case, this chip is contain 48 cores, totally 52 cores. But and Skylake is contain just the 18 cores. So as you can see, the Skylake core is bigger, 3 times bigger than our cores. So that is because this our core is a very slim and a small cores, and Skylake the core is the very general purpose, which has a lot of the outer resources on a cache or something like that. And let me present the performance of the S64FX processor. This is a result of the Clover Leaf. This is taken from the UK benchmark. This is the typical the stencil application, which solved the hydrodynamics the problem, and we compare A64FX and the Szaday X2. This is the Cavium server type of the ARM processors and Skylake. And within in this the comparison, we ran MPI process for the 12 cores, 12 cores, and for example, and Szaday X2 and the Skylake, to run the MPI process, we used one socket. So it means that the A64FX supporting the 4 MPI the 4 MPI process, but Szaday X2 and the Skylake is running the 4 MPI process by using the dual the two node of the dual socket. That is the 4 socket. So and this is the execution time, and this is the relative performance of to the one core of the A64FX. So the up to the 4 process, that means that the 48 are the cores here. So the very good scalability by increasing the number of threads within a CMG like this. So, and performance of the one A64X processor is comparable to that of the 2 nodes of the Skylake here. This is the Skylake. And this performance is thanks to the HBM memory. And several open source the software, application software is already ported, like OpenFOAM, ABinit, and Spec, the FM3D or WAF or something like that. So Frontesta and Solomon is a Japanese open source application. And in this graph, we show the relative the performance to the dual socket of the Xeon disk cascade rake. So, and to the one chip of A65X processor. And then you can see, of course, the A65X is a little bit slow than the dual socket of cascade rake, but very 80% or 90%. And this is a comparison of the average power consumption. So we would say that almost the same performance to the dual socket of the Xeon with the half power consumption. But the performance is not always good. So this is a Lurish. This is the US application. So, and it solved the unstructured mesh problem. And we compare again the SanDisk2 and Skylake. So as you can see, that this blue bar indicate the A65X processor performance is not so good. So we found that the low vectorization ratio, the SIMD instruction ratio is just a few percent. And to increase the vectorization, we need more the code tuning using the SIMD. And how to improve the performance of the structured mesh or sparse matrix, the type of code. So the German the researchers pointed out this result. They said storage format is very important. So this is the performance of the CSR, usually used for the data structure in the sparse matrix, but it's not so good. So if we are using the different storage format, we can increase the performance like this. And more generally speaking, so we compare the performance of the spec benchmark. So you may know spec benchmark is a very standard benchmark to evaluate very general workload, which is used for the several platform. So this is the list of the benchmark name, and this is the total score. And as you can see, the performance of the A64FX is just about in 1/4 of the performance of the Xeon in single thread. So this bench spec int is usually run using only one thread, one core. So if you compare the core to core, then our A64FX is not so strong. The reason the low the performance is that simulated rate this benchmark is not so good, of course. This is the integer application. And the frequency is the different. So in our case, 2.0, and this is the Xeon is running at 2.7, and also the out of the resources is not so much. This is limited to the throughput-oriented architecture of the A65FX. So this is the spec OMP. So this is the comparison to chip. So using the 48 thread. So this is a Xeon and this is the A65FX. But if you compare the total score, the performance of the A65FX is the 75 or 65 to the 70% of the performance of the Xeon. But you can see the stream and the multigrid, M-grid, is the fairly good compared to the Xeon like this. So very good. And I think this is because of the HBM2. And but the MD, this is the very bad. We found that the performance improvement is possible by source-to-source tuning, source code tuning, by using the inlining or the loop unloading by hand. So let me summarize the A65FX processor characteristics. The core-to-core comparison, the 1/4 of performance of the Xeon, and chip-to-chip is 65 or 70 to the Xeon processor. But performance of the memory-intensive application is extremely good. And some scientific workload, the UK benchmark or open source HPC software is very good. So, and we found that the simulated rate, increasing the simulated rate is very important to get a performance, and we need the tuning, the memory access pattern or vectorization. So, okay. And what kind of the performance tuning should be done to get a performance? So roughly, in a short, so our A65FX is the HPC-oriented design. So this table compare the out of resources, the A65FX and the Skylake. So to minimize, not to minimize, but to get us to decrease the die size, the number of resources, a number of the out of resources, not so much here, as you can indicate. And the design is a relatively long pipeline. So for example, in floating point operation takes the 9 cycles, and we only have the L1 cache. It's mean that throughput oriented and long latency, but it goes sometimes stall of the pipeline for the loops having the complex loop body. So in that case, compared to the software pipelining, the code transformation is sometimes helps to get the performance. This is the case study using the debommer loop. So in some the loop, we can get a performance by using the software pipelining. And also to relax this kind of the restriction, so loop fission, so splitting a loop is sometimes is effective to get a performance. And lastly, I'd like to mention about the power consumption of the Fugaku system. We at the design time, we set the maximum power consumption to the 30 to the 40 megawatt, but the actual power consumption of the Fugaku is about in 20, roughly saying the 20 megawatt. So this is a power profile of 3 months, last 3 months, July to the September 2021, so this year. So in this time, utilization ratio is the 70 and 80%. So, and this graph is indicate the power consumption of the Fugaku system, and this is the power consumption and entire facility. That is including the cooling system, including a refrigerator. So we are very happy to get this kind of result. So we can operate our system, Fugaku system, the 20 megawatt, roughly saying. And in addition to this, the A62FX processor has the very interesting the mechanisms to save the power, the power control. We have two kind of the frequency, 2.0 and 2.2 in a boost mode. In addition to this, we have echo mode. Echo mode means that we are using only one SIMD pipe. Usually, the core has the 2 pipeline, but if the application does not use not so much in a floating point, the arithmetic unit, we can stop the 1 pipe. So this is the result of the stream benchmark. So, and this line bar is indicate in a performance of the stream benchmark, and this is the number of threads. And the bar graph is indicate the power consumption. And so as you can see, you can see difference. So it's just the overlap. So no difference between the echo mode and non-echo mode. That means that even if you stop the 1 pipe, the performance is not so different. No different. But power consumption is decreased, roughly saying 50 to the 25 reduction is possible by using the echo mode. So currently, we are thinking the kind of the user model to encourage to use this kind of the power saving facility, the function for the user. Okay, next one is let's move to the system software overview. And the diagram shows the structure of Fugaku system software stack. And operating system is the Red Hat Enterprise, the operating system. And we have the compiler and the math library and some library which is designed to the deep learning using the SVE. And the interesting features is that we found that almost application may work with a simple recompilation from the A62FX Red Hat environment. That means the software porting performance tuning is sometimes required, but the porting is very easy. So many other applications already supported by the spec and package managers. So the mini open source software is available through the spec. And we have a standard programming model is the OpenMP plus MPI. And that we have two kinds of the MPI, Fujitsu-1 OpenMPI based, and the Riken is providing an MPI-CH. And Fujitsu is supporting the compiler, but recently the GCC and the LLVM can generate a very good code for the ARM processors. And the container and the virtual machine, the software is already supported, especially for the virtual machine. You can use the singularities. And Riken and the Fujitsu and the ARM team is developing the AI framework called the Diehl Fugaku. So you can use the ChaNGa or this is the Japanese framework, PyTorch and TensorFlow, based on using the Diehl Fugaku library. And some software is developed by the Riken. The MC kernel is the lightweight kernel, the enabling the jitterless environment. And also our team is developing Accelerators, directive-based Pegasus language. And the FDPS is the framework for particle simulation, and also eigenvalue. The library is supported by Riken team. And I'd like to show some little bit the result of the Accelerators. So Accelerators is that the Pegasus language and which is supported by the K computer. And in this project, we ported to the Fugaku also. And Accelerators is now available on Fugaku, and performance is enhanced by the Fugaku interconnect T. So this is the result. And these benchmark, we can we could get good scalability. And FDPS is the framework for the a kind of the DSL for the particle simulation. So and based on a C++ template library. User can write only these kind of the force. So and this framework provides domain decomposition and particle exchange and interaction calculation. So and this is a DSL. So not only the Fugaku, and it supports also for the CPU and also GPU. Okay, last one is the challenge for the programming model for the Fugaku and beyond the Fugaku. So the one of challenge the programming model for the Fugaku is that how to support the massive parallelisms. I think one of the promising approach is the task-based programming model to exploit the symmetry and many cores and enables the overlapping communication and communication. So, and currently we are working on a kind of evaluation of the OpenMP 4.0 task plus MPI. So that is the multi-threaded aware MPI. And we propose the next version of the XLMP in this direction. I'd like to talk about this later. And how to exploit the symmetry. This is also important topics. SIMD is the key to get a performance of the A64FX processor. Of course, you can use this SIMD using the OpenMP SIMD directive, and also the feature compiler is supporting the various vectorization techniques, and also in A64FX specific optimization is supported, like software pipelining and loop fission. And recently, my team is working for another approach supporting the OpenCL for the SIMD. So, and of course, the communication is different. So, TOFD, TOFD. So, I think using low-level communication layer, TOFD, is a very important optimization. So, currently, our team is working for the next version of our Excalibur project. So, main idea is the supporting task-based programming on global address space (PGAS) using our description of the data, description of the data distribution by the Excalibur MP. But as well as the language approach, directive-based extension. So we provide now, we are working on a compiler-free approach. So same idea is provided by the libraries using, including the C++ plus template wrapping. And to design the task-based programming, I think using the low-level one-sided communication layer, such as the UCX, is very important. So currently, we are designing the global task runtime using the UCX, in which is also supported to multi-threaded execution environment. And as the ChaNGa++, the now is the task migration is also important agenda for the next the programming paradigm. And last one is that the various kind of the offloading. So offloading within a node. So for example, offload to the GPU and FPGA using the OpenCL. And offloading to the SIMD, as I said, the previous slide. This can be used for the Cocos and one API and the data parallel C++. And another the offloading style is that the offloading outside of node. So offloading to the cluster of the accelerators. So the Fugaku, the ESPA is the another project to use FPGA cluster. So ESPA is stand for elastic and scalable system for the high performance reconfigurable computing. And actually currently as a some node is connected to this FPGA clusters by using the InfiniBand cable, InfiniBand network. And this is the 100 meter cable by 16. So using this system, we are currently investigating the technology to offloading some kernel to this clusters. So this is the kind of the modular computing approach. So, and this is the actual diagram that we just have the 16 FPGA both, which is connected by the front-end server, And this front-end server is connected to the Fugaku system, some of node of the Fugaku system. So we developed a kind of job allocation system to assign some node, the process to this kind of node, which is working with the FPGA. Here. So, and as one of the programming model for that kind of the system, so currently we are designing some OpenP plus some remote procedure code. So OmniRPC is a grid RPC system. The group is the developing, and you can see here the OmniRPC code to some remote procedure to this front-end node. So, and on a front-end node, invoke some DGEM routine is implemented in a PG cluster. So, and now is this OmniRPC is extended to manage and request the queue to the task to avoid a blocking thread, and the co-working with the OpenP task management. And so this is the last slide. The feature, the system beyond the Fugaku will be heterogeneous parallel system, which has some accelerators. So I think programming model of the accelerator-based heterogeneous system is become very important in the future. So of course, the task-based offloading, and I think task migration is another important topics, but task migration has to support the migration between the accelerator. And if the accelerator is connected between the accelerator, then the MIMD to the MIMD offloading is another important the offloading style. So that means some set of the node is offloading to the set of the clusters, set of the accelerator. So we are working the project called the Excalibur ACC. That is an integration of the Excalibur MP and OpenCC. So this XACC is supporting the MIMD to the MIMD offloading. And so as I shown the SPA system, some of the part will be the kind of the modular configuration. So in this kind of the system, I think offloading with the remote procedure core is the very one of the typical cases. So of course, the workflow programming between the nodes, different characteristics is another style of the programming model for the modular computing platform. In that case, a smart task or job allocation is become very important, including migration and load balancing. Okay, let's move to the conclusion. We have for developing a Fugaku system, we set 3 KPI as a design target: power efficiency and effective application the performance. So, and this is the result. So, sorry for Japanese. I taken from the status from our the RCCS homepage. That this is the result. So, how much the speed up we can get compared to the previous K computer. We achieved the almost target performance. And power consumption is lower than we estimated at the design time. And the A65X is many core processor is and for the HPC workload. So you sometimes we need to performance tuning. And several international collaboration is going on. And of course, we are collaborating with the ECP software teams, voting, evaluating. And we are collaborating with the CEA France and Singapore and the BSC. And of course, we are ready to collaborate with the ChaN++ teams. It's a very near future. If you want to use the Fugaku, you can apply. So there is two kinds of the call, the periodic call and calls open throughout this year. So if you tested the relatively small, using the relatively smaller resources, you can apply anytime the timely manners. So, and for the small scale, even class S and class SS, you can apply the 1 million node hours. So, okay, this is the end of my talk. Thank you for your attention. Do you have any question?
Thank you very much. Sorry, I was on mute here and talking. So that was a very interesting talk. Time for questions. I think raise your hands. I see John with a question already. Go ahead, John. Unmute yourself. Yep.
Yes. So if I understood correctly, what you showed was that the eco mode achieved about the same performance as things running in non-eco mode. Is that a sign that you over-designed the SIMD performance for the chip, or that or is that a sign that the vectorizer isn't doing a good enough job?
Of course, we have to cover the different kind of the workloads. So in case of in case of the memory intensive application, so this is the typical memory application, you know, and the stream is just
okay.
few few arithmetics, and all the time is the memory access. In this case, you can stop the 1 pipe, but for example, in case of DGEM is the very CPU intensive application. In that case, you can you need to use the 2 pipes. So it's depending on the characteristics of the application workload.
I see. And so did you find that there was a significant benefit for using the 2 pipes with things other than DGEM for full applications?
Yeah, of course. So memory intensive, CPU intensive application like that. So for example, in HPR, so we can benefit from a lot of benefit from the two SIMD pipe. But okay. The things that we are currently discussing is that what is the incentive for the users to use this kind of the mode? So the users just want to run their application as possible as they can. So they don't have to care. They don't have to care about the power consumption. But in system side, we encourage to use this kind of mode to lower the performance, lower the power consumption. So from the next year, we are thinking a kind of budget system and a power budget.
Mhm. Thank you.
Thomas.
Yes.
Hi, Sato. Really enjoyed your talk. Always like to learn the increasing nuances of the cleverness in the design and the ruggedness of the Fugaku machine. Truly a world leader. I thought I understood the performance models with its variant of dimensions of acceleration depending on workflows and operation patterns. But what I learned from this talk, and thank you very much, is your thoughts about having an external FPGA bank of heterogeneous computing. And this is not a criticism, but it seems, in my ignorance, to be discordant with the otherwise very well balanced system in communication memory and processing. And so my simple question is, to what degree has this inclusion, this integration, been driven by understood application workflows or modules? Or would you say rather that this is a clear opportunity for future exploration?
I don't know about the futures, but with deep analysis of the workload characteristics given by the application team through the target application. So we extract, of course, we extract some important kernel from these applications and then run the simulators and some performance estimation tools to explore the design parameters of the A65X processor. But
so let me just follow on that, because I'm still trying to understand. I mean, you're really pushing another dimension, and that's fantastic. But what I don't understand is what attribute of flow control or combination of primitive operations, essentially what is missing in the rest of Fugaku that motivates you to include this? Because Fugaku, well, like K before it, it's a beautiful machine. And Fujitsu's success in its high-speed processing elements really speaks to a more unified rather than more heterogeneous kind of computing in order to achieve the necessary optimality of speed up, depending again on the pattern. So what is it that was missing in what do we have to call it? Fugaku Classic?
So, yeah. It's a very good question. So I would say that we did a co-design very seriously, and I would say that there is the bright side and dark side. So bright side is that we can get the performance in these workloads. So because every time we decide some architecture parameters, we go back to these set of the kernels and taken from these parameters and to estimate the overall performance of these applications. But the dark side of the co-design is that too much co-design for this. So, for example, recently is this is the application were given by the application the team almost 5 years ago. So, but recently the many the workloads and different workloads coming, and recently the many the GPU based the workload is coming. Then the characteristics of the workload is become different. So in that case, sometimes we found that our the architecture design cannot fit to the in that kind of the workload. So this kind of the phenomena or this kind of cases we found recently.
Thank you very much.
If I can interject here a bit, could those, so it seems like there existed some program that uses accelerators. So to use them or use FPGAs or whatever, could you have translated them with some, I mean, executed them on Fugaku directly without the accelerator subsystem, that FPGA subsystem that you have? That's point one.
No, don't forget of the FPGA system. That is the very toy system. So
that's what I thought. It was an experimental toy system that was not designed because there was something missing in Fugaku, but because people wanted to experiment with FPGA. That is the interpretation I had of what you said. Okay.
So FPGA cluster system is the kind of the very prototype and to explore the future architectures. So for example, the one of the system we explore is that the kind of the modular system. Modular system means that the set of the system which is targeted to the specific application or something like that. So, but that is just a very small system. So I would say that is a very experimental system.
Okay, I had one other question, which is about compared with K, the relative internode bandwidth compared with the floating point performance has gone down, and total bisection bandwidth has gone down. Are there any applications where this is felt? Or it was the K was just over-engineered? K was amazing on that count, but maybe it was over-engineered.
Okay. So the network is always a program. So that means the performance of the node is became almost 20 or 25 faster than the K chip, K computer chip. But performance of the network is just only 1.5 times faster. Just it's a very low improvement compared to the CPU. So that is the kind of the decision of costs and which kind of technology you can use. So and we decide that again, analysis of this target application, the almost application in this set is using a kind of the neighbor the communication. So in other words, we gave up, gave up increasing the memory, the network bandwidth for the all-to-all communication. So for example, the one floating point reduction is supported by the TOF network, but if you want to all-to-all communication like 3D FFT, so this I know the performance of the network is not so enough to get a performance. So in other words, we gave up these kind. We don't support these the network intensive, like all-to-all communication the application. We gave up to support enough.
All right. Yeah. Thank you. Any question from anyone else? All right. Thank you very much. If we can at least virtually clap, please clap and thank Professor Sato for this excellent talk delivered at midnight. And thank you very much.
So if again, last message is that if you are interested in using the Fugaku, as I said, then at last of my talk, so please consider it applied to for the core. So
yes, you have already generated an active discussion on our Slack channel about that. So you will probably hear a PPL application sometime soon. So yeah, thank you.
Thank you very much.
Yeah, and there'll be a 15-minute break. Can we take four extra minutes and begin at 10:34 our time? All right. For people who want to talk in the break, we can create a breakout room. I actually do need to take a short break, but I will be in one breakout room if someone creates one. I don't know if I have the authority to do it. It'll be great to create a couple of breakout rooms, folks. There. Oh, what? Oh, I see. What does it mean? How many breakout rooms have we created?
So I just created 4 breakout rooms.
It seems like I have 27 breakout rooms.
No, it's just the number of people in the stream.
So how do I select a breakout room to go to?
There should be a list of 4 rooms, and you can.
Room, oh, at the bottom. Okay, there are 27 people. I'll be in room 1 for a few minutes if someone. If I can figure out how to do it. I'm kind of in there. You can hear me okay? Yeah, good. I can hear you, but that's okay. That's because I turned off my, okay. I'm going to actually log off. I just wanted to see if any one of the guests wanted to chat with me. But yeah, you can maybe tell people how to, the instruction you gave me, that hovering was very useful. So if on the chat, you can paste that instruction if you want to, because people might want to talk to other people or whatever. So just say who is in the breakout room and go talk to them or something like that. But I will get off. And who is the chair? Who is chairing the next session? Okay, good. So I'll be off. You can start it on time, and hopefully I will join in 10 minutes. I will be switching rooms and joining from a different computer. And okay. What? What did you say, Simon? Yeah. All right. Let's see.
Hi, everybody. It's just about 10:34, so I think we're gonna go ahead and get started here on this next session of astrophysical simulations. Starting this session is going to be Patrick Diehl from Louisiana State University, and he's going to be talking about recent developments in HPX and Octo-Tiger. So Patrick, whenever you're ready, we can see your screen, so please go ahead and start talking.
Okay, thanks, Zane, for the nice introduction. Yeah, I will like to talk about recent developments in HPX and Octo-Tiger. And it's a pleasure to talk at the Charm++ workshop about HPX. And the things I will present today is a major effort of a large group of computer scientists, astrophysicists, and applied mathematicians. I'm in the group of the former two, so I will talk a little bit about the astrophysics things we do with Octo-Tiger, but I'm not an expert, and I provided a lot of papers. I can answer basic questions, but I just wanted to make this disclaimer, so I cannot say much about the astrophysics things, but I can reference you to papers and people if you are interested in the astrophysics part of the talk. Okay, so the motivation of the Octo-Tiger code is this one here. Here on the left, you can see this image at a peak brightness, the rare 2002 red nova V8003 was briefly revealed, and the most powerful stars were done in the galaxy. And now what happened 2008, 6 years later, a similar event was happening, and the ODL observatory was observing this event, and they were able to extract the light curve of the red light emitted by these two mergers. And now we have this interesting curve with a really flat plateau overview orbits. And it's not really clear what was happening during this merger. And our goal is to simulate this merger using Octo-Tiger and HPX as the framework underneath. And we want to get a simulation of the slide curve, and then we could look into the code and probably understand the observations a little bit better. And here it's a heavily multiphysics problem because we have to do hydrogravity and radiation and do this multiphysics problem to get the radiation and red light curve in our code. And if you are interested in this type of merger and in the astrophysics details, I provided you with one of the references here. And this is the outline of my talk. First, we want to look into the software framework. I will briefly explain Octo-Tiger to you, then HPX and what we have done in HPX to support CUDA devices. And recently we started to add HPX as a backend to Cocos because we were thinking this is really important for upcoming supercomputers, because now we have the AMD GPUs. In the near future, we might have the Intel GPUs. And so we are really interested to use the portability for all of these acceleration devices from Cocos. And so we were thinking it would be really interesting to have HPX as a backend for Cocos. So I will show you a little bit about this work. And also performance profiling is really different in this asynchronous many task systems. So we will look into the Apex tool, and later I will show you some results of all of the tools I presented here. And for some scaling results, we mainly focus on the Pitt State machine and the Summit machine here in this talk. We have older results, but due to the limited time of this talk, I only will go into the newer supercomputers. And what we were recently doing, HPX used MPI for communication, but one of our collaborators was using Lifflander, so we could have an asynchronous communication. And I would like to show you some scaling results on Pitt State, including a full system run. And recently we ported HPX and Octo-Tiger to the Power 9 architecture on Summit, and I would like to show some results here and some preliminary results about Cocos and HPX. And I also would like to show you some performance profiling because our collaborator worked a lot to integrate the GPU profiling since we integrated GPU support in HPX. And briefly at the end, I want to do some highlight of the astrophysics validation we have done, because we intensively tested Octo-Tiger and compared with other codes to really be sure Octo-Tiger is computing the correct things with HBX and this CUDA framework. And I will conclude with the conclusion and outlook. So let us begin with the software framework. So here we have Octo-Tiger. You can see this logo of Octo-Tiger, and Octo-Tiger is completely open source. It's available on GitHub, so I provided you with the link. And Octo-Tiger is designed for the simulation of the evolution of star systems. And to do this, we use the fast multipole method, and we use adaptive octrees for our adaptive mesh refinements. And currently, Octo-Tiger implements all these three modules we need for the light curve simulation. So we have a height draw solver. This can be run on CPU and GPUs. We have gravity solvers, which can be run on CPUs and GPUs. And these two parts of the code were heavily benchmarked in the reference below. I will show you later some of these results. And recently we added the radiation module. This is implemented on the CPU. We are currently on the state to start to port it to the GPU, but some intensive benchmark there is needed. And from the computer science perspective, Octo-Tiger provides communication in MPI and libfabric. We can run pure CUDA kernels integrated in HBX. Recently, we started to have HIP kernels, and more recently, we started to use the Cocos HIP backend. And I will tell you something later about all these features in the scaling results. And to give you an impression what we try to simulate here, this is an example of a merger simulation. And here you have this blue star, which is really small. And then we have the yellow star. This guy is 5 times larger, and we printed a little bit the grid cells. And so you can see that around the blue star, we have a low refinement because we have the small star. We have a different refinement around the yellow star, and further away from the stars where the stream has not started yet. So we can have a really coarse mesh. But once the stream starts to develop, we have to refine around the stream. And so it's a really adaptive code. And so we have different kind of resolutions. We have to deal with different workloads on different kind of our system and nodes in this case. And the above picture, you see that the stream starts to grow, and this is after 2.2 orbits. And if you go down on the second pictures, about 2.6 orbits, the stream has started, and the mass transfer between these stars started. And here's the references where we were running this on the KNL machine at NERSC. And here you see a 3-dimensional simulation, again, with the different grid refinement levels here. And this guy is around an orbit of 4.13. And here you can see that the accretion disks begin to start. And so in the end, this star are merged to one star. And during this merging for the V1309 scope, they were able to observe the red light. And this is the final aim where we try to go with this code, but we are not there yet. But we benchmarked a lot of different things I will show you later. So this was just a little bit an overview so you can understand what kind of simulations we are running with Octo-Tiger, and that we have these different resolutions where we have the stars and where we have the accretion disk and where the chat was starting. Okay, so Octo-Tiger is built on HBX. So HBX is an open source C++ standard library for concurrency and parallelism. HBX is also available on GitHub. So every tools we develop at Stellar Group are available on GitHub and completely open source. So I would like to highlight a few of the features of HBX we were using for this kind of code here, and then briefly show some of the components of HBX. And so HBX exposes a uniform standard-oriented API. So HBX provides you the parallel algorithms defined in C++17. We have the HBX future and HBX async, which is based on the standard async and standard future in the C++11 standard. But in the C++ standard, we only have shared memory parallelism in C++17 and maybe for a long time. So HBX was adding on top things that we have distributed possibilities to run distributed code. And HPX provides unified syntax and semantics for local and remote operations. So we were hiding from the application developer if it's a local or remote call. And HPX has a uniform, flexible, extendable performance counter framework, which we will use later for some of the analysis I will show you. And so this is really important that we have this abstraction levels for the astrophysical developers, because they don't want to go deeply into C++, so they want to have this nice abstraction level HPX provides. And here, this image is taken from the JOS paper we published last year. And this is a really nice paper if you're interested in HPX, because this paper has only 3 pages, and we describe really briefly all these different modules here from HPX architecture, and then you can read quickly, and we provide a lot of details and publications. So if you're interested in only a few of them or interested in a brief overview of HPX, I would recommend that you start with this JOS paper. And here, what we have this active global address space, AGAS, to do this unified for local and remote. We have the parcel transport layer, where we added the slip fabric for asynchronous communication, where I will show you later some results. And we have the C++20 concurrency and parallelism things implemented, even some things which will be in the next C++ standard. And for the policy and engines here, Gregor, one of our collaborators at the University of Stuttgart in Germany, he started to add a CUDA policy, and now we can launch CUDA kernels, CUDA memcopy, and all these things you need for GPU computation, and you get an HPX future back. And so you can use this HPX future with the futures from your GPU tasks and use any of the local control objects to do some synchronization. And so the GPUs with this new policy are integrated in HPX asynchronous execution graph, and HPX is resolving the dependencies you specify with the local control objects using these futures. And this is really what is new for Octo-Tiger. So we have this new GPU support. And so you can not only do local and remote, you have this GPU kernels and you can run things there. And it's really integrated in the task-based system. And here is an example. So now, thanks to our collaborators at the Swiss National Computer Center, Michael Simberg, and a lot of more people, they helped us to port HPX to Cocos. And now what you can do, you can use Cocos for your GPU or acceleration card. So you can use Cocos to launch a CUDA kernel or an AMD kernel or whatever kernel you want to launch. But if you do this with Cocos, you get an HPX future back, and then you can use this HPX futures you use with Cocos again to do the combination with your task. And here's a small example. So we have this Coco kernels. So we get this future F1 back, and then we could do .zen, and then we could do a task on the CPU. So grayish blocks are CPU tasks, green are Cocos ones, or we can have a task 2 here. We read some initial file, generate our grid on the CPU, and then we could do a launch of Cocos kernels, and then we can combine Cocos and we can combine everything with each other. And so you have always the HPX futures, and then you can use .zen when all the primitives we have to do for synchronization in HPX, but now you have Cocos, and you can use the performance portability for Cocos. And here we use the underlying CUDA. And recently we started to add the HIP API. This is an ongoing work, but I will show some results later. And here, HPX Cocos integration needs to work for both host and device side execution. So even if you would execute a CPU kernel in Cocos, you also would get an HPX future back you can use for the synchronization. And Apex is our last tool here. Apex is the autonomous performance environment for exascale. And this is a performance measurement library for distributed and asynchronous multitask systems. This is heavily done by our collaborator, Kevin Hook at the University of Oregon here. And to support performance measurements in systems that employ user level threads. So we cannot just use the normal tools looking into context switching, because this would not give a lot of information. And so Apex uses a dependency chain in addition to the call stack to produce traces and task graphs. And recently, Kevin added CAPD to capture CUDA events and VLMM to monitor the GPU. And you can get OTF2 or Google Trace events, traces as an output. And recently, Kevin added that you can get task graphs and task trees. I will show some example later using the dot library. And we have scatter plot of timers and counters with the HBX counter framework. I will show you later. And here is the references for the Apex paper. So let us go to the scaling results. The first thing I wanted to show is what we get as a benefit if we replace synchronous communication using MPI with asynchronous communication using Lifflander. And here we were working on PIT-stained. Here's a little bit information about PIT-stained. You have one CPU with 12 cores. You have this one NVIDIA Tesla P100. You have 64 gigabyte. And here we were using some scenario. And on the lowest level, we have around 5,000 subgrids and 8 gigabyte of memory. And we were going up to 4 level of refinement. So we were refining our simulation 4 times, ending up in 1.5 million cells and a lot of more memory. And this was used for our scaling test. So first we start with the left graph, and the red line shows the result using MPI as a communication backend for HBX, and the blue line uses Lifflander. And so everything is the same, the simulation, everything is the same. We just compiled HBX with Lifflander or with MPI, and we're running everything's the same. So if we look from a single node up to 2 to the power of 5, there's not much difference in the communication. But here, if we look at 2 to the power of 7, we see that the red line, which is the MPI, is getting a little bit flat. And so we can go on. And we were driving this up to a full system run using all 2,400 nodes on PIT-stained, which is 2,400 NVIDIA GPUs and over 60K cores. And so you can see that you get some benefits here in the speed up. But the more interesting plot where you can see better what is happening is on the right-hand side, where we plotted the ratio of processed subgrids per second between HBX, Lifflander, and MPI path support on PIT-stained. And higher numbers mean Lifflander is faster. And here you can see for lower node numbers, there's not much difference. So, but if you increase the node numbers, you see if you go from 2 to the power of 5, you get a factor of 2 speed up. And if you go even higher, we could show that for the full system run and for 2,000 nodes using this Lifflander asynchronous communication, we were up to 3 times faster with our computation. And nothing else changed. So everything was the same. We were just exchanging the path support in HBX. And so this is a really interesting thing we further want to explore. And below is the references if you're more interested what's going on there. So let us look onto the scaling on Summit, because on PIT-stained we only had 1 GPU. On Summit we have 6 GPUs. And here we were doing our Hydro kernel. On the left-hand side, we were running our pure Hydro test problem. And here you can see that we get scaling for different subgrid sizes at each leaf node. And on the right-hand side, we were adding the GPUs. So we have 1 up to 6 GPUs added to the same configuration with the CPUs. And here you can see by adding the GPUs, we are an order of magnitude faster for the pure Hydro module. And we were doing exactly the same for Hydro and Gravity. And here you can see the same principle. If we were adding the GPUs, we are again an order of magnitude faster and everything scales. And I will explain you in a second why we do not have the 32 cubed line here. And this you can see for the distributed runs. We were doing exactly the same for the distributed scaling of the Hydro code with GPUs enabled. And here you can see with the larger subgrid size, we have a benefit for the beginning, but then the work is not sufficient. And here you can see we could scale up to 128 node. And here you can see the speed up. But interesting to say here is that this problem has 7 million cells, and it was not enough work for 128 nodes, because we have a lot of GPUs there, over 700. So even this large problem, which is quite sufficient for the astrophysics community, was not large enough for Summit with a lot of GPUs to scale out. And here is the same for the hydro and gravity part. Yeah, and here we did it also for distributed. And here you can see again, we were not using the 32 cubed because it was not really enough work, but you can see that for both subgrid sizes, we scale a little bit better. And probably in future, we want to use 16 cubed for this scaling results. Let us go to Cocos. So here we were measuring the overhead of Cocos with HBX and the pure CUDA execution policy. And you can see there's not much difference if you have one node, if you use Cocos, or if you use the HBX CUDA framework. However, if we go on a distributed run, here we were going on Summit, we were running again on up to 128 node. So you see on one node, there's not much overhead, but somehow if we go for a distributed run for 2 nodes, we see a little bit of overhead, but going up to 128 node, we see that adding Coco as an additional abstraction layer, we have to pay around 10% of overhead instead of using HBX and the pure CUDA scheduler. But these are really recent results I got last week. So we have to investigate a little bit more because, as I told you at the beginning, the Cocos integration is really recent and we might have to optimize and do performance profiling, but at least things looking not so worse because we would assume that we have to pay a little bit overhead for using Cocos as well. So the last thing I want to show from the computer science perspective is performance profiling. So you would ask how expensive Apex is. And so here on Pitstained, we were running the CPU only problem for the hydro part without Apex and with Apex. And here in this plot, you can see it's only 1% performance overhead we add by enabling the profiling of all CPU tasks in our code. And so this is really nicely done because we were doing this up to 2000 nodes and everything works well. So even for this high number of nodes, you could use Apex to get some performance profiling, not for many time steps, of course, but you cannot run at least 100 time steps. It's not so expensive to get some insight and see what's going on this larger node count. And here we did the same on Pitstained and Summit. And here we were adding the CUDA library. And here you can see on Summit, we have a little bit less performance if we look at the cells processed per second. But on Pitstained, it's looking much worse. For larger node counts, we have 50% less cells processed per second. So we have to investigate, but we believe that using this CAP-P and NFL is really expensive to do CUDA measurements. And here, what you get of these measurements, you get a combined task graph. And here you can see the task tree and task graph example. I provided a link to higher resolution figures, but here you really see the task graph and everything includes CPU and GPU. And so you can see where your application is doing. And also for the task graph, if you would zoom in, we would get some information about how long this task was executed and everything, how long this task was waiting. So this is a really nice feature that we have this combined because before we were running with Apex and vProf. And so we had 2 different kind of performance measurements, but now we have everything combined in one framework. And here you see some sample profile of tasks on Pitstained and Summit. And the red line is Summit. And here we could see some really interesting insights on the difference between these 2 systems. And so we really could compare and see what changes if you have a different newer GPU because P and V100 are different and also the architecture is different. So here we could get some really nice insights. And for the sake of time, I cannot go really deeply, but these plots will really helpful for us to understand the difference I showed you before, that if we use on Summit, the Apex system, we get only a few overhead, but we get much more overhead on the Pitstained machine. And for the astrophysics validation, so we did a Relution convergence study. So we were running a double wide dwarf merger and we were refining our mesh. And here you can see if we refine our mesh, the property we observe is getting closer to each other. And for the astrophysics community, this means that if we refine our mesh, the quantities are somehow converging, getting closer. This is a really important factor for the code. And we added a higher reconstruction in our hydro module because the astrophysics people think this is really essential to get accurate light curves. And here, if we use a higher order integration rule, we could reduce the error we obtain by a factor of 2. And we also did an intensive comparison against Flash. And so we were running a lot of test problems to ensure we get exactly the same results as the Flash code. And we were doing some performance study. And for CPU only runs, we were not really much faster as Flash, but with the GPU runs, we were a little bit faster as the Flash code. But we also get the same results at the Flash code. So I would like to stop for the conclusion at Outlook. So we have shown that the integration of CUDA GPU within HBX and Cocos is working. So it's really nice that you get this HBX futures back for both of them and integrated in the asynchronous graph. And we are still working on the AMD. So we have the kernels ported, but we have some issues with the AMD. We were not able to get the nodes running and everything, but I think a lot of people know about this issue we had with the AMD cards. But an ISE paper is in preparation for the AMD integration. And an Outlook, we want to do more scaling results with the new Cocos HBX implementation on different architectures, use Apex for profiling. And we also want to do some optimization because currently the AMD results look not so good. So we learned even with Cocos that you cannot just use a Cocos kernel, run it on the AMD device and good scaling. At least for us, we had to adapt our kernel a little bit because the architecture of these devices is different. And we want to benchmark the radiation and port it finally to the GPU, because with the radiation, this part is the most compute intensive kernel. And once we have those things, we wanted to start to simulate the V1309 merger if we have really benchmarked our code and to try extracting this light curve and compare with the observations. So thanks for your attention, and I'm happy to take questions about what I told you.
Hi, Patrick. Thanks for your great talk. That was really exciting. Looks like we have a question that Michael Norman asked in the chat. Michael, would you like to unmute yourself and ask the question?
Yes. Sorry, camera. This is Mike Norman. Thank you for that beautiful talk. I just wanted to know, what is your typical task granularity, and how does that jibe with the efficient use of the GPUs?
So from our experience on Pitt Stain and on Summit, we are using 128 streams per GPU. So yeah, this is what we do. And then we fire up the small kernels. And if we reach 128, we wait to fire more kernels for the GPUs. And this was working quite well for us so far. But yeah, we would have to do more investigations, because in the paper currently in preparation for the SIAM conference, so we have seen that this was working really well on the P100, but on the newer model, the A100, it's not working so well. And so yeah, we are working on this one. And for the task granularity, we have some criterion from a physical evidence how to distribute the granularity and how to have different tasks aligned on the CPU. But this depends on the application. So we have different refinement criterions for this to define the task granularity on these CPUs.
But what is your basic task? Is it a subgrid of the octree?
Yes.
Thank you.
You're welcome.
Are there any other questions? I don't see any hands raised, so I'll give just another moment. But in the meantime, I have a question for you, Patrick. Is the communication that's done when you use the CUDA backend, is that to use the GPU direct communication, or is the data first staged to the host before it can be sent?
So on Summit, we are using the direct one, but on Pitstand it's not available.
Okay, got it. Thank you. And we have another question from Phil Miller real quickly. I'll just ask it. He asks, how optimizing non-blocking is the MPI parcel transport layer? Oh, Phil, you can go ahead and ask it.
Yeah. Could I give a little more context on that?
Yes, can you?
Yeah, so I just wanted to know, like, are you aggressively, calling like I send, I receive, and kind of queuing up the requests to pull in the runtime, or is it just a very naive MPI thing to get it running? Context for that is the VT runtime just uses MPI, nothing lower level, but we do very proactively kind of queue up requests and try to keep tests flowing until communication is done.
So in the simulation we were running, or for the results I showed, we just used this MPI receive and send, as you said, but currently one of our PhD students was doing something similar you were telling us, where we can get some speed up, by parcel coalescing and all these things. But in the results I showed, we were not doing this right now because it's still under development, and we are trying to do this soon. But we were more interested in the Lifflander because we read a lot about this fabric, and our collaborator was really interested in implementing it in HBX, and so we were doing this runs for showing that Lifflander is working really well, because the Swiss National Computing Center is really interested to switch from MPI to Lifflander for some of their projects, and so they invested a lot of time from John Biddiscombe. He was doing it for HBX, and he was doing it for some other project. I recently talked to him. So they are interested in this Lifflander stuff. And so they were working with us on Octo-Tiger. And so it was a coincidence that they were helping us to do this because they really were interested to see the performance of Lifflander.
Great, thank you.
Okay, great. Thanks, Patrick. We're
You're
going to
welcome.
move along now to the next talk. Yep. If anybody has follow-up questions for Patrick, maybe you can talk offline. Patrick, if you want to put your contact information in the chat, maybe that'd be good. But next up is going to be James Bordner from UC San Diego and the San Diego Supercomputing Center. And I'll go ahead and transfer it off to him. So James, please go ahead.
Okay, thank you. Good morning, everyone. I'm going to talk about recent algorithmic improvements to our code Enzo-E Cello. I'm going to begin with a quick, brief review of our application. So we want to investigate questions in astrophysics and cosmology. And this requires several things of an application. First is rich multiphysics capabilities, including gravity, hydrodynamics, magnetohydrodynamics, chemistry and cooling, radiation, star formation, all this stuff. And second, it requires a large range of scales. So here in this image, we have from star formation through galaxy formation to cosmological structure formation, can range from very small, relatively small, to really large. But also, even within a given simulation, we want to span a range of scales. So this motivates using adaptive data structures to refine on regions of interest. And thirdly, we want to run on these simulations require a lot of computation. So we want to run on the largest HPC platforms available. This requires large application to be very scalable. So our application Enzo-E Cello is in 2 layers, or multiple layers, the Enzo-E application layer and the Cello adaptive mesh refinement framework layer. So the parallel data structures we use are an array of octree adaptive mesh refinement. We have of fixed shaped blocks. Each block contains field data in arrays such as density, velocity components, and so on, and particle data such as, which we use for dark matter density and star particles. The array of octrees is implemented using a single char array where each block is a char, and this is fully distributed. Each block knows about its nearest neighbors, but otherwise there's no global representation of the data structure. AMR operations provided by Cello include adaptive remeshing for refining or coarsening blocks to evolve with the evolving features of the simulation. It applies initial conditions, boundary conditions, and numerical methods provided by the application layer. The field variables are overlap, they extend beyond the block to accommodate computational stencils of the methods. So we need to periodically refresh ghost zones with exchanging values with neighboring blocks. And particles tend to move around, so they might migrate from block to block. So Cello handles particle migration. Interlevel operations such as interpolation and coarsening of field variables and HDF5 input and output. At the application level, Enzo-E, this is built on top of Cello. This implements a new number of methods for the physics. Uses a modified piecewise parabolic method for hydrodynamics, particle mesh method for computing gravitational potential. There's a VLCT magnetohydrodynamics implemented by Matt Abruzzo, and Grackle library is used for chemistry and cooling. Enzo also supplies some specialized operations beyond what Cello supplies. So we have a second order monotonic interpolation method, which helps keep positive field variables like density positive. Some application dependent refinement criteria. So we might want to refine on dark matter density and so on, and different problem generators for setting up initial conditions for test problems or types of simulations, and a collection of linear solvers for use with the gravity solver and radiation. These are currently Krylov subspace methods and multigrid methods, or some composite of those two. So I'm going to talk about two things that we've been working on recently. First is I/O, reading HDF5 and writing data to disk, a previous approach, a new approach, preliminary performance and possible future directions, and adaptive remeshing issue. We've had issues with that, particularly the balancing part. And we'll review the previous approach and talk about our new approach. So we use HDF5 for our file format. For writing data, we previously wrote one file per process, which is not terribly scalable, though we can, if we use SMP mode, we can get one file per node. The processes open and close the files, and blocks each write their own data to the file, so there's no inter-block communication. There's some synchronization involved between since the processor level and block level, since processors need to open their files before any blocks write to it, and the processors need to close the files only after all blocks have finished writing to them. But that's relatively simple to implement using a reduction. So this approach is kind of a moderate load on the metadata servers in a Lustre file system, parallel file system. But that's reduced a bit by using the SMP mode. There's very limited flexibility, however, since it's fixed to one file per process, and there's limited scalability. For reading data, this is seemingly an easier problem, but our implementation was actually a bit worse. Our input files are generated for like cosmology simulation, are generated from an external application. You have one file per field, such as a file for density, one for velocity, the velocity components, particle displacements, and so on. The way it was implemented, however, we had each block would open each file, find its little portion of the data. So the fields for cover the entire domain, but the blocks are a relatively small portion of the domain. It would read their portion and then close the file. So this is less synchronization than even with the writing files, since each block opens the file, reads it, and closes, and it's easy to implement. However, this put an extreme load on the metadata servers of Lustre file systems, since you have potentially millions of blocks all trying to open and close files at sort of the same time. This can render the parallel file system unresponsive, and we did actually crash Frontera nodes by running this approach. So we needed to do something about this. There's also limited flexibility in that we had in how it read in files, and extremely limited scalability. So our new implementation involves regular partitioning of root level blocks in the array of octrees. So here we have this partitioning of like 4x2 root level blocks. Each partition is associated with a single file. There's one designated writer per partition. And it proceeds by a depth level traversal of all the blocks in each partition. And the blocks send their data to the writer, and the writer handles the writing. So this proceeds by the traversal of the blocks in the partition, but it kind of alternates between going to the next block and then going back to the writing block. So we have this sequence of entry methods. So the writer block requests data from the next block in the list, and then that block receives that message, packs up its data, sends it to the writer. So one minor complication is that the next block in the traversal is not known by the writing block. So since this is a distributed data structure, the writing block doesn't know about what the topology is of the rest of the partition. But the next block block I knows what block I plus 1 is. So this proceeds by the writer opening the file. If it's a leaf node, it will write its own data to the disk. In this case, it's not a leaf node, and data is only associated with leaf nodes in Cello. And for each block in the traversal, B0 sends its request to BI. BI returns both its data and the index for the next block in the traversal, so that B can send gets that for the next iteration through, and then it closes the file. So we tried this out. We did not crash Frontera this time. That was good. We ran it on a half system run, 4,000 nodes, 230,000 cores on the Scratch 3 file system on Frontera that had 32 object storage targets with peak of 120 gigabytes per second. Our test problem was a 2,000 cubed cosmology run with 16 cubed blocks, which means there were about 2 million blocks. The partitioning we used was 8 by 8 by 8, which was not really optimized yet. This is just a test run. And we wrote 9 double precision fields. And we got nominally, we got 4 outputs for a run, nominally between 20 and 25% of peak, which there's room for improvement, but it's not bad for a first try. And the input was a bit slower, but it did run. Not terribly slower, but so there's some remaining issues we want to deal with. The first is that this approach is not load balanced. So our partitions might have a lot of more blocks in one partition than another. So in future, we want to try using space filling curves to define the partitioning. That way we'll get an equal number of blocks per file. And currently we only have a single writer per file. So we're using serial HDF5, but we'd like to use parallel HDF5. So for the second topic is our adaptive mesh refinement algorithm. So remeshing is used to adapt to evolving simulation features. This proceeds by each block computing some local refinement criteria to determine whether it wants to refine, coarsen, or stay the same. And we have a couple of restrictions. One is obviously that we only want to refine or coarsen a block once per step. And also we want to limit the difference in resolution between neighboring blocks. So we want to prohibit level jumps. So if we look at the image on the right, this top one is not balanced. This is not load. I'm not talking about load balancing, but this mesh is not balanced in terms of the resolution differences between adjacent blocks. This bottom one is each block is only adjacent to blocks within one level, mesh refinement level difference. So this is called a balancing step. We need to refine on blocks that might not otherwise need to refine based on the local refinement criteria. So this is an example of mesh refinement with the mesh balancing. And the point I want to make here is that this tends to lead to a cascade of induced refinements. So this is colored by the age of the block, and you can see between this step here and this step here, just by refining these blocks here, that induce these blocks to refine, which in turn induce these blocks to refine, and these and these. So it's not, so balancing step, it's kind of difficult to determine when you're actually finished. So our previous implementation is based on this paper here. So blocks evaluate their local refinement criteria. They notify their neighbors what their desired level is, and then they update their own level as needed to avoid level jumps. And as the blocks update their levels, they in turn notify their neighbors. And this proceeds until so each block doesn't really know when the entire balancing step is done. So termination is using quiescence detection. And so just a simple mock-up of the algorithm, you begin with a balanced mesh. This is a refinement criteria for given step. Updated refinement for the next step. We coarsen blocks or refine blocks according to this local refinement criteria. And then we communicate with the neighbors with our desired level, and they update their level to maintain the level jump criteria. And that proceeds a couple steps until quiescence detection and indicates that we're done sending messages saying that we're done with the balance step. Unfortunately, we've noticed that this approach doesn't always work. We can fail with level jump detected error. This occurs non-deterministically, typically on larger runs after hundreds of cycles and thousands of cores. And so it's difficult to track down what the actual cause is. Maybe there's a bug in the code, but it might actually be the algorithm itself. But we suspect it's something related to this quiescence detection aspect. And if you look in the CHARM FAQ, should I use quiescence detection? And the answer is probably not. There's more to that, but I wanted to try to redesign this balancing step to avoid quiescence detection. So our new approach is, instead of maintaining just a single level per block, we maintain the current bounds. So both a minimum and maximum bound on the desired level of a block. The lower bound we initialize to the local refinement criteria, can't go below that. And our initial upper bound is just the current level plus 1. So we can't refine a block more than once. Based on the current bounds of our neighbors, and we do the same sort of exchange with our neighbors, but we both raise the lower bound if we need to, and we also lower the upper bound if possible. And each block then can proceed until the lower bound is equal to the upper bound. And this will always happen for all blocks. So we now know each block, we can now terminate this using just a simple reduction. And so this shows how we adjust our level bounds. The minimum lower bound, if we have a neighbor that's finer, that causes us violation of the level jump criteria, we'll need to refine. So we raise our lower bound here. It's indicated by the black underscore. And we do that if any neighbor forces this. And we can also decrease our upper bound if it's consistent with all of our neighbors. So here we don't have any neighbor that can possibly force this to be this level, so we can safely reduce the maximum level on this. So for adjusting the minimum, any neighbor can induce this, but in the bottom, we need to check all of our neighbors to see if we can do that. And you can go through a little example, the same example. We initialize our lower bounds to the local refinement criteria, upper bounds to be just 1 greater than the current level. And then we communicate with our neighbors and adjust the level bounds based on the neighbors. And we go a few steps, and all of the blocks have reached the committed state where the lower bound and upper bound are equal. So we can terminate with a simple contribute, simple reduction. So So in conclusion, we've updated our I/O scaling algorithm to improve the scaling. We're not restricted to a single file per process. We greatly reduced the load on the metadata server for HDF5 input, but there is still some room for improvement. And we are currently implementing the adaptive mesh refinement updates. And hopefully that will deal with our level jump errors that we've been encountering. And that's it. Thank you.
Thank you, James. That was a really great talk. I was glad to see all that. I'll open it up for questions at this point. Does anybody in the chat have a question? You can, I see a hand raised. Please go ahead and unmute yourself and just go ahead.
Hey, James, great talk.
Thanks.
So with the parallel IOs, ChaRM++ has this CKIO parallel writing library. I was just wondering, any thoughts? Well, any thoughts about sort of implementing an HDF5 parallel version of HDF5 built on that, or is that?
I think I looked into that at one time a while ago, but yeah, that's something I do want to look at. It's been a while since I've looked at that, so I don't know what it includes, but certainly if.
I mean, one issue is I think it's write only at the moment. It doesn't have read capabilities, but I was just wondering.
Have you used that?
Yeah, so we use it in ChaNGa, but we've got our own file format. We're not using HDF5, but a lot of codes do use HDF5, so it'd be interesting to have a sort of CHARM parallel HDF5 library.
And if there is enough incentive, if users interested, I guess we should implement the input part of it. The output part is okay. The input part needs to be done. Just as always, resource constraint thing. If there is need, then we will try to do it, and maybe with your help, we can do it. James.
Does anybody else have any questions for James?
Phil, beyond the chat, do you want to say something?
No, I don't think anything that needs to be added. Me and James and Mike and you can talk about it later.
Okay.
I have a quick question I can go ahead with. Beyond kind of support for that, further support for HDF5, do you think there's kind of further abstractions that you would appreciate in CHARM++ that would help solve some of these I/O issues that you've been having?
I can't think of anything offhand. I think we have a decent plan of how to go forward. I think the space filling curves approach will be useful in just for the load balancing aspect. And I will look into the CHARM++, what they have existing for HDF5.
Okay, sounds good. Thank you. I think that unless there's anybody else that has a question, you can go ahead and speak up now. But otherwise, we're going to move on to the next presenter. Nils, you can go ahead and start sharing your screen. So we're going to be hearing next from Nils Deppe at Caltech. He's going to be giving us a talk on simulating neutron stars with discontinuous Galerkin methods in ChaN++. So Nils, please go ahead whenever you're ready.
All right, thanks. I just want to check with you, Zane, is the screen share coming through all right? My audio is coming through all right?
Yep, looks good.
All right,
Sounds
great,
good.
thanks. All right, hi everyone. I'm Nils. This is work that's been done as a broader collaboration, part of the Simulating Extreme Spacetimes collaboration. I'll be mostly talking about our progress with simulating neutron stars, but at the end, I'll also show some results of basically evolving gravitational waves for the purposes of experimental detections, and I'm basically extracting the gravitational wave parts of these simulations more accurately than we have been able to in the past. So in terms of some motivation and everything, we are really targeting binary neutron star mergers. That's sort of where our expertise historically lies. We're also interested in accretion disk simulations. These are part of after you have two stars collide, they form a black hole. And that's roughly that's the picture you have on the right here, where you have a black hole in the middle and you have a bunch of fluid orbiting it and accreting, falling into the black hole over time. And we have some collaborators that once we have some of the sort of methods parts figured out, will help us with the core collapse supernova explosion physics. So for our purposes, we're really focused on you have two neutron stars, they orbit each other, the in spiral shrinks, so they come closer and closer together and then they collide. And this nowadays is detectable in gravitational waves and also in sort of the multi-messenger spectrum. So electromagnetic telescopes are able to see these as well. All right, so some of the big challenges here is these pictures look really cool. I always enjoy seeing them and the renderings that come out of these. But realistically, the errors in these simulations are of 10 to 20%. And the physics we want to extract from these simulations is also on the 10 to 20% level. And so, if not smaller in some cases. And so really, while these simulations look great, they are useful in certain regimes of understanding the physics. We're very quickly moving into the realm where the experimentalists will be ahead of us in terms of being able to make accurate measurements, or the measurements are more accurate than our predictions. And so we really need to figure out how can we make these simulations more accurate. And generally sort of the historical approach has been, well, add more grid points, you get higher resolution, then you're able to get better accuracy. This is challenging. Many of the codes in this field are 20 years old, back when a large node was 4 cores and not 128 cores. And so really, these codes don't really scale as well anymore as they did to machines when they were written. And so for a number of physics reasons, you really need to actually resolve the surfaces of the stars quite accurately, because how the surface moves actually ends up being encoded in the gravitational waves themselves. And that's directly what experimentalists are able to measure. So like I said, we can't really just wait for bigger computers. One reason is that more cores doesn't help us directly, right? These simulations already take 6 months to complete. So if we're already at our scaling limits, more cores isn't going to help us. And so really, we need something new. We need to redesign these codes sort of from the ground up. As mentioned sort of in the last 2 talks, the standard, or sort of alluded to, the standard approach in hydrodynamic simulations is finite difference or finite volume methods. Typically, the error scales as 1 over the number of grid points squared, and you have Cartesian meshes. So the mesh is sort of just a box. For stars, well, stars are more spherical. And so if we could deform these boxes, that would be nice. So that's one of the goals. Now, spectral methods, these work very well for smooth solutions where you don't have discontinuities. And so think of wave equations, or in the case of binary black hole mergers, the Einstein equations themselves actually don't form discontinuities if you start with smooth initial data. The error decreases much more rapidly. It decreases exponentially. And as you increase the number of grid points in each sort of little region in space. And the way that spectral methods are formulated, they are very naturally amenable to curved meshes. And so this is, on the left is an image. Both of these images are from a binary black hole merger using our current production code. And so on the left is sort of the grid frame where you're sort of the transformation from this frame to where you quote, solve the PDEs, or where your finite difference like operators occurs, time independent transformation. So we go from this sort of a grid configuration where we remove the inside of each black hole. So at the center of a black hole is a singularity, gives you an infinity. Computers don't really like doing math with infinities all over the place. And so we cut out the interior of the black holes. And then as the black holes move and orbit each other, and then they start colliding, they start to deform quite a bit. And so we basically use a feedback control system to track these. And this all works quite well for smooth, no hydrodynamics problems. Discontinuous Galerkin methods, and just a recap or sort of summary of these, try to do sort of the best of both worlds. They try to get you this exponential convergence where the solution is smooth, while also allowing you to handle discontinuities. And so similar to sort of if we take, if we look at, let's say, just going up along radially along this direction, we can say, okay, this is like a 1D sort of grid here. If we take this 1D grid, we have different refined regions. And in each one of these regions, we can choose locally how many grid points we have, which directly corresponds to the polynomial order. And so then at the boundaries between these regions is where we can, in theory, resolve discontinuities. This is what all the applied math and engineering literature sort of claims you will be able to do. And so unfortunately, that doesn't work very well in our applications. We've tried pretty much everything in the literature, and none of it really has worked as well as promised in the papers. And so instead, we basically say, okay, well, if our fancy spectral method doesn't work, then we fall back to a finite difference method that can handle the discontinuities. The alternative viewpoint is you take the standard finite difference codes that are used in everywhere in sort of numerical relativity nowadays. And you instead say, okay, well, if the solution locally in space and in time is smooth enough, I'll compress the data to a more efficient spectral type representation. So you can also think of this as a compression scheme. And so on the left, we have the discontinuous Galerkin representation of the polynomial in the cell. And on the right, we have a finite difference representation of the same solution. But instead, we increase the number of cells or sort of subcells inside the discontinuous Galerkin element, and then project the solution onto this higher resolution grid. So you can also think of this as a very aggressive adaptive mesh refinement type approach, where you basically double the number of grid points in each dimension and also switch your numerical method to be more robust. So how does all of this sort of work together? At a very high level, you have your discontinuous Galerkin loop in the top left and a finite difference loop in the bottom right, and then you have to basically connect them. So you take your discontinuous Galerkin or spectral type method time step, you check if the solution is okay. So do I have positive densities? Do I have positive pressure? Basically, is my solution physical? And you can also quite rigorously check with the mathematical question of, is my representation of the underlying data good? And you can basically quantify that. Mathematicians have figured out how to do that. If the answer is yes, you keep using the spectral type scheme. If the answer is no, you actually undo your time step, switch to a finite difference method, and then take the time step using finite difference methods. On the finite difference side of things, and you use finite difference methods to take the time steps, and after each time step, you check if the solution is representable on a discontinuous Galerkin or spectral type mesh. If not, you stick to finite difference. If so, then you switch back to discontinuous Galerkin. And so this way you can switch back and forth between these two methods, choosing whichever one is more appropriate for the solution locally in space and in time. And so this is an image from a Newtonian Kelvin-Helmholtz instability. I'll show a movie corresponding to this in just a second. But basically these sort of more strongly colored regions around the top and bottom edges of this sort of flow pattern is where we're using finite difference in this region, whereas these, I'll say, the lighter colored regions, or not as strongly colored regions in the interior and up here, are where we're using the high order spectral type methods. So most of the solution in this case is represented with the high order method. So hopefully the video comes through okay. This is just to show that sort of we're able to track with these flow features as they evolve. So this is what we're sort of tested over the last year and a half to try and see does this have any hope in working for relativistic applications. Our experience has been that if it's not fantastic in 1D, it doesn't have any hope of really working in 3D. And it also needs to work really well in the sort of Cartesian mesh Newtonian case to have any hope of working for general relativistic magnetohydrodynamics. So now let's look at a sort of standard test problem in general relativistic magnetohydrodynamics. This is a cylindrical blast wave. You start off with a dense cylinder. This is sort of a 2D problem at the center of your domain, and then you have a magnetic field in the x direction. And then as the fluid moves into the less dense region, the magnetic field makes it move at slightly different velocities and sort of provides an interesting flow pattern. And so on the left here, so these are both simulations run, same version of the code, different strategies for handling the hydrodynamics. So either sort of this classical limiting procedures in the discontinuous Galerkin community, or this sort of hybrid approach. And so the number of degrees of freedom, or sort of the effective number of degrees of freedom, are normalized to being the same. So this is one of the important things that we found also quite frustrating in the literature, is that many papers would show test problems with a resolution 10x of what you, in 1D, 10x of what you could reasonably do, or maybe 100 or 1000x of what you could reasonably do if it were a 3D problem. And so this made it very difficult to evaluate how well these methods would actually work. And so on the left, we have a third order discontinuous Galerkin method for sort of some of the experts in the room using what's called a simple Wino limiter. And so it sort of resolves the solution. It does an okay job. What you see on the right is what you should get. So if you can see the left one, it doesn't do a fantastic job. And so the other struggle with these is if we try to go beyond third order, even fourth order, the simulations basically always result in an unphysical state that we can't correct for, and the simulations crash. So it's very difficult to handle. So sort of a combination of smearing of the discontinuities and a lack of robustness basically have ruled out all of these classic type methods. This is the best one. If we look at various other strategies, they all do even worse. On the right is this hybrid approach. You can, so these regions where there's sort of these black squares imprinted, this is a rendering artifact just from the visualization. And so basically around the top and the bottom and on the sides here, this is where we're using finite difference methods to resolve the discontinuities. Whereas on the interior, where the solution is smooth, we get, and you can use a sixth order finite difference method. And, this kind of reminds me of an eyeball. So you get this sort of nice eyeball feature in these. So this is what we found to be the most promising. And so we've tried using these classic methods to simulate stars. And stars are challenging because you have a discontinuity at the surface. Outside of the star, there's empty space, but the fluid prescription, or sort of a fluid approximation of the underlying physics, doesn't allow you to actually have zero density out there. So you have to have some sort of artificial atmosphere, some small density. In the neutron star case, typically this is about 1,000 grams per centimeter cubed, which is like 100 times denser than lead. That's what empty space is treated as. And even with something like that, these simulations tend to crash quite regularly. Or in our case, we really didn't have any success. On the other hand, these hybrid schemes were much more successful. So if we look at a magnetized neutron star, this is a plot of the maximum density as a function of time divided by the maximum density at time t equals 0. So this is a normalized measurement. So this is basically to see what percent errors or how much is the central or the maximum density of the star oscillating. And this is an isolated star. It's just sitting there. The analytic correct value is it just should stay at 1. It shouldn't change over time at all. And so we take 3 different resolutions, basically doubling the resolution every time. The resolution here is comparable to what is typically done in the literature for finite difference methods. If you did finite difference methods everywhere, it's within 1 grid point more or 1 grid point fewer to the standard finite difference schemes. And so this is this is critical because we need to be able to run these simulations at resolutions that are actually feasible or representative of what is computationally possible currently. And so the 6-element case, that actually the star is, each cube that's covering the star has at least 1 grid point that's also outside the star. So that means everywhere sort of that's containing the star also is containing the region outside the star. Everything has a discontinuity, and this basically means we're doing finite difference everywhere on the star. As soon as you switch to not being in that situation where you can actually use the high order spectral method inside the star, which is the 12-element case, you immediately see you preserve sort of the central density much more accurately. And with the 24-element case, you also decrease the oscillations drastically. Now, you can think of this sort of translating the analytic time-independent solution to a numerical grid as adding a perturbation, because it's the numerical solution is not time-independent, right? There's sort of, because of your truncation error effects in the numerical solution, there's going to be some oscillations induced, as we can see, and these oscillations should be close or oscillate at the frequencies that the star oscillates at based on perturbation theory. Sort of analytically, you can ask the question of what should these stars be oscillating at, what frequencies. And so here's basically a plot of the frequency spectrum of where they're oscillating at. I'm not sure how well these dashed vertical lines come through on the screen share. In terms of the lowest resolution curve, you get a peak here, which is the lowest frequency oscillation mode that's resolved, but there's definitely sort of no resolving of any higher frequency modes. You know, we do get some peaks, but they aren't aligned with the expected frequencies. So these are numerical artifacts. The 12-element and 24-element, so the two that also called the medium and the high resolution solutions, they both also resolve second peak, so they resolve the lowest peak here as well as the second peak. And then with 24 elements, which is the dark blue curve, we can also resolve the third peak. You might be able to make some weak arguments that were close with the medium resolution, but that's sort of, you know the answer, and so that's why you can sort of say, oh, well, it's close. So I wouldn't claim that. All right, so let me just briefly summarize sort of where we're at and what we're working on right now on the neutron star front before shifting gears and talking about the gravitational wave extraction front. So currently we're able to evolve a magnetized neutron star. We have this discontinuous Galerkin finite difference hybrid approach. What we're currently working on is coupling in the full Einstein equations to this. This is done on the discontinuous Galerkin end. We're now doing this to the finite difference solver as well. And the other thing we've looked at in the Newtonian cases, working on getting higher order finite difference methods that are still robust. So one of the big challenges with this is we need to run something like 3,000 to 10,000 of these simulations, these binary neutron star simulations, to build up a large catalog for the experimentalists. Currently, any individual, with how frequently the simulations crash and not making it be completely overburdening, any individual can run maybe 3 or 4 simulations at once. If you need 3 simulations, that means we'll say, or if you need 3,000 simulations, an individual can run 6 simulations a year. We're looking at several hundred human years of time in order to basically produce this, and that's just not a reasonable timescale. So one of the big things is robustness. We also have sort of ideas and some basic tests for how to generalize all of this to curved meshes, and adaptive mesh refinement is much better understood. We also have sort of on the discontinuous Galerkin end things much further along than we do on the finite difference end. And the big push is binary neutron star mergers, initially without neutrino physics, and then very quickly we have neutrino physics in the code, just not coupled in. The neutrinos play a very critical role actually in these phenomena, and especially on the electromagnetic front of what do you see in a telescope. Let me also point out the implementation of all of this is publicly available on GitHub down here. It's part of our code Spectre. And so it's all documented with Doxygen. We don't have any high-level tutorials yet of beyond basic installation instructions, since there's not much point in writing high-level tutorials until you can do the physics you want to be able to do. All right, so the other challenge is you have these black holes or stars orbiting each other, and you need to get the gravitational waves from this to effectively infinity. And so there are a number of ways of doing this. The current ones are sort of extrapolation. You take the waves at various different radii and then you extrapolate them out to infinity. And so this work is led by Jordan Moxon and Keith Mittman. Jordan just left us not too long ago, and Keith Mittman is a postdoc or is a grad student at Caltech. And so basically the key difference here is that with sort of these new extraction methods, you can track extra physical phenomena that are actually there, which are called memory modes. And you can see that in the left, in this sort of classic picture, everything oscillates about the 0 point of the wave. Whereas the sort of part where things are oscillating about really changes as a function of time. And so this is basically a key thing that's missing in all current numerical relativity simulations. It's not important for current detectors and experiments. It will be for the future. If we look at a different component of the radiation that's extracted, again, not critical now, but it will be over sort of 10 to 20 year time scales, which seems like a long time, but there's probably everyone here that knows getting a code to work is sometimes unclear how long it'll take. And so you can see in this case, the extrapolated and the more exact extracted method are completely different. They don't look at all the same. All right, so just quickly in summary, we're able to evolve magnetized neutron stars with our discontinuous Galerkin finite difference hybrid method. We put out a couple papers on this fairly recently. And we're also able to do very accurate gravitational wave extraction. And there's a number of papers available on that as well. And that's it. Thank you.
Thank you, Nils, for your great talk. I'll open it up for questions. First one I saw is Thomas Quinn. Please just go ahead.
Hi, Nils. Fascinating stuff. Particularly this hybrid discrete Galerkin finite difference switching over. Are there time step issues associated with that? Does the finite difference, say, require many more time steps per time interval than the discrete Galerkin? And then if it does that pose, say, load imbalance issues that you have to deal with?
That's a really good question. So we actually, let me see if I can get to a slide here. So discontinuous Galerkin actually requires a fairly strict time step restriction. So it's, if n is the number of grid points inside the cell, then for that cell you have a restriction of 1/2n-1. And so we choose the number of finite difference grid points to be 2n-1 inside the discontinuous Galerkin cell, so that the time step size matches exactly between the two. But in terms of load imbalance, yes, because you all of a sudden have almost 8 times more work inside an element than you did previously. But we haven't had a chance to really explore that. We have done some experiments with Chern++'s load balancing, but the single stars aren't really that dynamical. Right, you sort of, things refine and then stabilize. So.
Okay, thanks.
I think a relevant point, just to keep attraction to the after lunch period, there's going to be a discussion of load balancing in that period, as in those talks as well. And I know there have been many of the talks so far. In other discussions, pairwise discussions, we have identified load balancing issues that we need to address, and hopefully Ronak's talk will be in that direction.
Are there any more questions for Nils? All right, well, if not, then I think we're gonna break for lunch, returning at 1 o'clock Central Time. In the meantime, we have some breakout rooms set up, so if there's any continuing follow-up or new discussion related to any of the talks given so far, or anything in general, please feel free to go ahead and use them. We'll keep them open for the entire session. But in the meantime, thanks for coming to this session on astrophysical simulations. We'll see you in just a bit under an hour. Thanks, everybody.
Welcome back, everybody. So we'll be starting the next session. Next, we'll have Weizhao Li, who will present from North Carolina State University, and he'll talk about dynamically load-balanced p-adaptive discontinuous Galerkin methods using CHAN++. Whenever you are ready, Weizhao.
Okay, all right. Just a quick check whether you can see my slides and hear my voice.
I can see your slides and I can hear your words.
Okay, all right, thank you. So hello, everyone. I am Weizhao Li. Here my presentation is about the p-adaptive discontinuous Galerkin method with dynamic load balancing. So this is the outline of this presentation. First, let me give a little bit of background of our project. So our code Kinua is open source computational tools designed as a computational tools for fluid dynamics written in modern C++. We already implement the numerical solvers for single material as well as multi-material hydrodynamics for 3D tetrahedral grid. In this presentation, I will focus on the single material flows. And since we develop our code based on the asynchronous parallel model from CHAN++, it automatically enables the built-in dynamic load balancing technology from CHAN++. And then let's first look at the governing equations. So the governing equations for single material flow is compressible Euler equations represented as here, and where the U is our solution vector and F is the flux vector. The pressure can be evaluated according to the equation of state from ideal gas, and gamma is the ratio of specific heat. So as we all know, that discontinuous Galerkin method has been recently really popular for solving the conservation laws. So due to a lot of good mathematical properties, here I'll just briefly go through the formulations for the DG methods. So first we will obtain the weak formulation by multiplying the test function W to our governing equation and perform integration by parts. After that, we will do the discretization process, make sure the W and the U are defined as the element base. Then we will obtain a weak formulation shown as here. And then after that, we will assume our high order solution within the element could be represented as U equals to the summation of UG times BG. B is the basis function, while U is the coefficient for the basis function. And then we can apply this high order solution equation to our weak formulation. And after some manipulation, we could finally obtain a semi-discrete formulation in the as shown as here, where I is from 1 to n. N is the number of degree of freedom for our system. So this is the formulation for the DG method. And before we jump to the adaptive part, I want to first explain about the DG solution here. So when we talk about DGP0, what we mean is actually we assume the solution within each element is shown as a constant value. So DGP0 is identical to finite volume method. Well, when it comes to DGP1, we assume the solution within each element is linear polynomial. So the number of degree of freedom will be 2. And as for DGP2, we assume that the solution is a quadratic polynomial. So the degree of freedom will be 3. And then when we know this, after we can extend this into a 3D dimension. So in 3D, a quadratic polynomial shows the degree of freedom as 10. So in short, we are actually need to solve a 10 times 10 linear system for DGP2 in 3D. Well, if it's DGP0, we just need to solve one equation since it's just a constant. So this indicates the load differences between the high order solution and low order solution. It also shows how expensive it could be for high order method when it comes to multi-dimensions. So since we know that it is expensive for high order methods, so we want to introduce an adaptation process so that we can increase our computation efficiency. There are two most famous adaptation. The first one is the H adaptation, which is also called AMR, automatic mesh refinement. And here we are actually focused on the P adaptation, which is the polynomial order adaptation. In the current methods, we use a local error indicator to determine the order, whether the order of this element will be refined or coarse. So the indicator we used here is the so-called spectral decay indicator. It is defined as here, where the rho p and rho p minus 1 represent the numerical density with polynomial order of p and p minus 1. So after we evaluating the spectral decay indicator for each element, we will apply the criteria, refinement criteria. If eta is larger than a threshold, we are going to refine the order, polynomial order within this element. If it's less than a user input threshold, we will coarse this. And again, both the thresholds are user input and case dependent. But this is not the whole story, because let's assume an example that this is the part of our mesh, and we do detect a vertex at the center of this mesh at omega e. So the spectral decay indicator will tell us to refine this element. But the thing is that this is the posterior error indicator. What we need to do is that we need to have this order, polynomial order, set up for the next time step. And since we know we are using a CFL number less than 1, we know in the next time step, the vertex will be moved to its neighboring cells. Therefore, in order to make sure we always capture the fluid properties in high order regions, we also need to add a protective layer after evaluating the indicator. So by adding this protective layer, we actually refine all the nodal neighboring elements around the element omega e. So before, it's just a omega e here as a refined region, while after the protective layer, all its nodal neighboring will be refined too. So after these two processes, we finish the whole adaptive strategy. Here is just a brief summary of how the process looks like. The left red box shows about the DG discretization, while the blue box actually shows how the adaptive process will be. And since we are running in parallel, we need to perform communication to update the degree of freedom as well as the solution on the chair partition boundary cells. So, and by simply applying this adaptive, it do reduce the total number of degree of freedom for our test, for our simulation. However, it also introduced an unbalanced load distribution. So here I'll just explain about the three factors of the why unbalanced load balancing is introduced. So the first one is the number of unknown. As we just discussed, for example, if the red line is the partition, well, the element on the processor number 1 is applied DGP2. Then in 2D, it will solve a linear system 6 times 6. Well, for another cell, as is applied DGP0 on processor number 2, then that will be just one equation. So the number of unknowns determines the load difference between cells and between partitions. The second factor that affects this is that the number of quadrature points, because in terms of a high order method, we also need more quadrature points so that to make sure we obtain enough accuracy for the numerical integration. Therefore, this is another factor leads to the load difference between them. And the last one is actually about the time step. For a higher order method, we need a smaller time step for this simulation. Therefore, it requires more iterations than the lower order method. This is another difference between the high order method and the lower one. And since this actually adds up to an unbalanced load distribution, in order to solve such problem, we need a dynamic load balancing technology. And that is why we develop our code based on Chum++ library. And next, let's talk about some of the numerical results we have. The first one is the simple benchmark test of Saw Shock 2 problem. It is a 1D Riemann problem we are running it in a 3D mesh with 11,000 tetrahedra, and the initialization is given as here. So here is the numerical distribution for the salt shock tube problem. The top half actually shows the distribution of the density, and the bottom half shows the distribution of degree of freedom. So when the cell is marked as red here, which means this cell is applied DGP2 method. Well, if it's light blue, which means DGP1 is applied in this region, the rest is just the DGP0 or finite volume method. So if we look at a 1D plot here, we can see that for the rarefaction wave, we do apply a DGP1 method to solve this region. While for the contact discontinuity and shock, we do apply a higher order DGP2 method to solve such regions, which is what we expected. And then if we take a deep look at it, we can see that our adaptive DG method shows almost identical solution as DGP2. So this indicates that our methods not just simply reduce the total number of degree of freedom, but we also remain the same accuracy as a uniform high order method. And then after that, we can take a look at the walk log timetable for this simple problem. So the first case is just a simple DGP2. We're using 128 cores. It took us 36 minutes to finish the whole process simulation. Well, when it comes to DP adaptive, using 128 cores, it took us 33 minutes, which is not improved too much, since we know that we significantly reduced the number of degree of freedom. So that was caused by the load imbalance. So, and you can see that in the case 4, finally, when we turn on the load balancer, we will see a 2.1 times speed up. Again, this is for a really simple salt shock tube problem. We're going to investigate a little bit further in the next 2 test cases. The second test case here we have is the saddle blast problem. It actually describes a flow with a strong spherical shock wave. The initialization is shown here. Actually, we are actually giving a higher pressure initialization at the original point, which causes a blast wave propagates across the whole domain. And we are using a mesh with 29,000 tetrahedra. So here is a short video about our solution. The left part half is actually our density, numerical density distribution, and the right part is about the distribution of number of degree of freedom. So as you can see, the red region actually indicates the DGP2 region, which is the heavier load assigned region, while the rest is just the light blue is actually DGP1, the rest is DGP0. And then we can see that our refinement region always captures the shock, and also ahead of it because we have the protective layer. For this problem, it is a dynamic load imbalance test case. Although we don't have too much de-refinement, as you can see, we do have some, but it's not too much. Mostly it's about refinement. The refinement region just expands. And if we look at the walk log timetable for this problem, the first test case is the reference as the DGP2 with 64 cores. That is 4 computation nodes. It took our 5 hours to finish this test case. And for the case 2, actually what we try to do here is that we try to run DGP2, a uniform DGP2 with over decomposition. So you can see we have more partitions here. Well, it gives us a walk log time of 5 hours and 26 minutes, which makes sense because for a perfectly load balanced distribution, just simply apply the over decomposition gives extra communication. So it took more time to finish this simulation. And then when we apply just the p-adaptive, it cost us 3 hours to finish it. It improves a little bit since we do reduce the degree of freedom. Well, when we apply p-adaptive plus over decomposition, we can see we already obtain a speed up of 2 times speed up. Well, this is because when we try to apply the over decomposition to a load imbalance test case, we kind of do it's the same as a kind of do a load reassignment at the beginning of the test case. Again, this is only at the beginning. It doesn't make sure our load is always balanced during the simulation, but it do improves our parallel performance a little bit, improves a little bit about the load imbalance situation. So that's why we can see a 2 times speed up. Well, the final optimal solution we obtain from this test case is a 2.4 times speed up compared with the regional p-adaptive with load balancer. So the last test case here I want to show is a triple point problem. The triple point problem is actually a 3-stage 2-dimensional Riemann problem, but we still run it in 3D. And it is originally proposed as multi-material. Here we are running it with a single material variant. So the initialization is given shown at here. As we can see, there are 3-stage initialization, and we are using a mesh with 600,000 tetrahedra. Here is a short video about how the solution evolves. The upper half actually shows the numerical density distribution. The lower half actually shows the degree of freedom distribution for that. And as we can see, our refinement region do captures all the necessary fluid properties we want, which means that we do apply high order solution into the region we want. And on the other hand, it is better than the saddle blast case because, again, previously saddle blast test case, we normally just do a refinement. There is not much de-refinement. But for this test case, we can see there is a more refine and de-refinement, and this region actually moves a lot across the whole domain. And we will say that the process will be more dynamic compared with the previously saddle blast wave. And we are expecting a better solution for that. So if we look at our walk clock timetable for this triple point problem, let's first look at the case 1. We just apply DGP2 with 32 cores. Again, we are not here, the results not listed at the final time. We run at t equals to 1. So with 32 cores, it costs us 5 hours to finish this job. And the thing is that when we just turn on the p-adaptive, we can see that it costs more time to finish than a uniform DGP2, even though we applied adaptive and reduced the total number of degree of freedom. And there are 2 reasons for that. The first, as I was saying, because the load imbalance is more serious than the previous saddle blast, which leads to a really extreme case that shows a poor parallel performance. And on the other hand, when we turn on the adaptive, we also introduce more functions that evaluate the error indicator and also like adding the protective layer. Therefore, since we have a poor performance from parallel, and on top of that, we add extra mutation, so it took more time to finish. This actually shows how important a load balancing technology is for our research project. And if we look at case 3, when we apply p-adaptive DG method with over decomposition, we do achieve 1.7 times speed up. It's not as good as previous one, but this time it do improve a little bit, but not the optimal level. If we look at the final results, case 4, it is actually p-adaptive with load balancer. We can achieve 3 times speed up compared with the p-adaptive DG without any load balancing. So, which means that previously it took 6 hours. Right now, we only need 2 hours to obtain exactly the same results as before. So in order to further investigate the parallel performance about this table, we also output a usage profile for this triple point problem. So as you can see here, each column actually represents the usage % of each processor. And the leftmost column is the average data. So the green portion of the column indicates the % of the working status for that processor during the whole simulation. While the white actually represents the idle state. Again, this since DGP2 is a perfectly load-balanced test case, we don't have too much white regions here. And we listed this as a reference to show that if DGP2 is applied, it's a load-balanced test case. And then this is actually how the usage profile will look like when p-adaptive DG applied with 32 cores. And as we can see here, there are 4 processors that's almost 95% of its time is remain working status. But the thing is that except these 4 processors, the rest of like 28 processors just remain idle status for almost half of the simulation. You can see the average data is almost like 50 or 60% of the usage. And that explains why it shows that such a poor parallel performance. And then when we apply over decomposition with the p-adaptive, we do see an improvement. As you can see, first we can see the average data, it shows to like almost 60%, almost to 70%. And also by looking at it, it is a little bit better than previous one, but still we can see that the load is not 100% balanced distributed. It improves the condition, but it does not fix the condition here. So finally, when we try to apply a p-adaptive DG with the load balancer, we obtain, this is the usage profile will look like. For the average usage percent, we achieve like 80%. And if we look at the load assignment or the load distribution across all the processors, it is almost identical. So that also explains that why we can achieve a 3 times speed up compared with the original p-adaptive without load balancer. So here is just a short summary about what I've been presenting. First, we do propose a p-adaptive DG method. However, the developed adaptive methods will also introduce unbalanced load distribution. Sometimes will lead to a really poor parallel performance. And also we show that our adaptive scheme combined with the load balancing technology from Chamberlain Plus could significantly increase the computation efficiency. And at an optimal level, we can achieve a 3 times speed up in terms of a practical test case experiment. As for the future job, we are trying to implement more complex numerical methods within our parallel structure. For example, our multi-material hydrodynamic solver. Since more complex solvers means that more computation for high order. Therefore, the load difference between high order and lower order will be larger, and we should obtain a better solution from the dynamic load balancing technique. And that's for my whole presentation. Thank you.
Are there any questions?
I think Nils pull a hand, right?
Yeah, this is a great talk, really interesting, and we should chat more in the next break if you're available. So how do you choose your base resolution? And I guess, do you choose the base resolution to be sort of, this should resolve the problem, or this gives us sort of decent resolution for a P0 scheme, and then let's see what we get with adaptive order? Or how do you choose the base resolution? Like I guess the number of tetrahedral elements, I guess is the question.
The number, no, we are actually doing a P adaptation. So if you mean the base level, let me go back to our adaptive.
Yeah, I guess, how do you choose the tetrahedral decomposition of the domain for the problems, right? Like, how do you choose the number of tetrahedron that you use?
What do you mean? How do I choose the number of tetrahedra? Because in our case,
even before you start doing p-adaptivity, even before you
Mhm.
start running the simulation, what is the size of the, how do you choose the size of the tetrahedra?
Oh, so actually, at the beginning of our simulation, we actually assign every element as a higher order as DGP2 scheme, and then after the simulation starts, some of those elements will be dropped to like DGP1 or DGP0.
But you still have a choice of how fine or how coarse to make the not H adaptivity, but how fine or coarse to make the tetrahedra. What decides the size of the tetrahedra when you begin, at the very beginning? How did you choose the 680,000 for that problem, for example?
Oh, that is actually a mesh. We test and we found that it shows enough fluid properties, and we tried that 600,000.
Okay, so then I guess my sort of question concern, for example, for like the SOD problem or something, how do you expect this maps to sort of real world problems? Because something we've, as I mentioned, we've really struggled with is that a lot of the test cases are very easy to over resolve, that you have way more resolution than you could conceivably have in sort of the actual application spectrum. How does that map in this case? How do you make sure you sort of don't have such high resolution that for like a SOD test problem that this would never scale to whatever the realistic applications that Los Alamos has for this are?
What do you mean the over resolution? You mean you apply a higher order?
No, you just choose so many tetrahedron that that it just looks good sort of regardless of what you do, just because you have such a high resolution. But if you ran like a 1D problem with 40,000 grid points, it's going to look fantastic always. So, this is like a really nicely resolved shock tube, but, I don't know.
Oh, so
realistically, I'm trying to compare this to like a finite difference method where you have like 200 grid points, because that is really all you could get if you wanted to do a realistic simulation.
Okay, so what do you mean that because I'm using for this shock tube problem, I'm using a more fine mesh, right? So that the results could look as good. But the thing is that what I want to show here is that for the same mesh, our p-adaptive solution can be consistent with DGP2 solution, with the uniform DGP2 solution. So if we apply on a coarse mesh, again, that solution will not look as good as this one, maybe. It may be more diffused because we use a coarse mesh. But the thing is that the DGP2 is our standard reference. The DGP2 will show a more diffused solution. Well, what we want to see is that our adaptive solution is identical to our DGP2. That's the whole point. It doesn't matter which mesh we are using here, right?
That has not been my experience. That's the part that I'm concerned about, but I've taken enough time. We should talk about this later, but thank you for the answer. That was very helpful.
Okay, thank you.
But Nils, if I understand, well, okay, we should move on, but very quick comment on that. If I understand Weizhao's point is that you can choose the mesh dimension, mesh sizes based on whatever criteria is appropriate, and whether there are errors with that or not, that's a separate issue. But he's only saying orthogonally that within that, if you use DGP2 versus adaptive, just the p adaptation, just the how many terms you use at each point, he gets the same solution. That's all. And I think that's separate question of what grid size you use, should use. But I'm speaking out of my depth here. So let's move to the second question, Simang.
Do you mind if I quickly pitch in here? Just to respond to Nils' comment about resolution.
Yeah.
I want to basically echo what both Weizhao and Sanjay just said, that it's an orthogonal question, and we haven't looked at what kind of resolution we would need for real world problems. All that we are saying here is, given a mesh that resolves the physics features in the flow properly, what happens if we apply a p-adaptive method to that? that is what we have been answering. And we can talk more about this. Sorry for taking some time here.
Yeah, I would really like to talk more about this because this is sort of something we've been struggling with, that the sort of your end of the claim hasn't matched up with our experience in our application domain, but it's a different application domain. So I would really like to talk later if you have time.
Okay. Looks like the second question disappeared. Okay. I do have a question about the Sedov comment, actually. Can you put up that chart of performance? When there were 5 rows, I think, instead of, okay, that one. So it's not a question, it's more like a promise or a comment. But going from 1 to 2, when you over decompose, the time increases by half an hour, which is like, what would you say, 10 to 11, it's like 10%. And I would like to understand why, and I would like to address that, because the cost of over decomposition is something that we hear all the time. And I would like to neutralize that to the extent that's possible. So is there something you can say about where that cost is coming from? Is it should not be more communication volume, because one could, well, I guess it depends on how those are mapped. Is it communication volume? Is it the memory? Is it some extra work? How can you understand that?
Oh, because for this problem, we do think that is caused by the communication volume, because if we look at the difference between the case 1 and 2, the only difference is actually the overcomputation, right? And all the others, unlike the DGP2 and p-adaptive, we have some function differences. But for the uniform DGP2 and the uniform DGP2 with over decomposition, there's no other difference between that. So we do thought that was about the communication, because it requires more, maybe the time to receive and send, it costs more time for that.
But a lot of that communication extra communication will be within node.
Yes, but we are not running with SMP modes here.
Yeah, okay, so that could be another issue. So the new, you should maybe pay attention, not pay attention is not what I meant. There is hope here, because there should be newer XP-mem based communication mechanism that you will hear hopefully somewhere later in the workshop that might improve that. But over decomposition cost, actually, just abstractly speaking, there is communication, but there is also extra memory, and there is sometimes extra computation. So through projections and various other things, one can actually decompose and separate out those costs. Will be useful to know what those are. They are related to communication, but they may be separate ramifications, and therefore they will be separate redressals. Mechanism for that, but anyway, that's just for future. And secondly, the load balance, I'm hoping, will also be Simang's question as what load balancer did you use? I will ask you that question, but I will also say, I think I'm hoping that down the line, especially when you go to large number of nodes and cores, you would have opportunity for improving on that count as well. So instead of 80%, maybe we can go higher with tasks and with better load balancers. So that's just expressing my hope here for the project.
Okay, all right. Actually, for the Sato plus test case here, we are actually using a greedy refined load balancing.
Yep.
Yep.
Okay.
Are there any more questions? Otherwise, we'll move on to the next speaker. Okay. So next we have Jonathan Lifflander from Sandia National Labs, and he will talk about optimizing distributed load balancing for time varying imbalance. Jonathan, whenever you're ready.
Okay, can you all hear me?
Yes, we can hear you.
We are seeing your whole screen. Okay, now
there we go. Yeah, sorry, I don't use Zoom a lot, so that's getting used to it here. Okay, so yeah, I'm presenting a talk entitled Optimizing Distributed Load Balancing for Workloads with Time Varying Imbalance. This is based on a paper we just published at Cluster 2021. This is a collaboration of the Dharma group at Sandia, including Phil Miller, Nicole, Francesco, Philippe, and Matt. Okay, so the first question is, what is Dharma? It's a toolkit of libraries that we're building that supports incremental AMT, which stands for asynchronous many-task adoption, and we're targeting it towards production scientific applications. So the main tools that we have are Dharma VT, which stands for virtual transport. This is our main runtime. It's an MPI-oriented AMT runtime. And then we have Checkpoint, which is a separate library for serialization and checkpointing data to disk. And then we have Detector, which is a small library we use for C++ trait detection. And more germane to this talk, LBAF, which is our load balancing analysis framework. And so I'll talk about this more in detail, but it's a Python framework we're building for experimenting with load balancing strategies. So some of the background, as many of us know, MPI is really dominated as a distributed memory programming model. This is especially true at Sandia. A lot of this is because there's a deep technical and intellectual ecosystem around it. If we look at the next generation Sandia applications, they're developed on top of these really large MPI libraries. Trilinos is probably the best example of this, which is a collection of libraries that involve linear solvers, STK, which is a toolkit for meshing. And really, there's little chance that these applications are going to be rewritten completely on top of a tasking runtime. So the goal here is to try to build a runtime that coexists and provides a transitional AMT runtime that demonstrates some incremental value. And so we want to build a runtime that's highly interoperable and that allows application developers to just rewrite parts of their application and over decompose those and see some benefit and then add more of their application. And so a key point here is the transition between MPI and AMT must be inexpensive. So we're expecting that we're going to have frequent context switches from MPI to the AMT runtime, potentially many times per time step. So for domain developers, we want to provide constructs that have an SPMD feel to them, which gives them a natural transition to AMT while also retaining some asynchrony. And we also choose to exist with a diversity of on-node techniques. At Sandia, that's mostly Cocos. And Phil's actually going to give a talk tomorrow about some of our work with Cocos and running on the GPU. And we also want MPI operations to be safely interwoven with AMT execution. So we have worked on some operations that do that. And we've also found that serialization and checkpointing can actually be a good backdoor to starting to introduce AMT libraries, because there aren't really good serialization libraries out there for a lot of C++ data structures. And so we talk more about this runtime we're building in a paper we published last year at an SC workshop. Today, I'm going to talk more about load balancing. So at a high level, there's several types of load balancing strategies. Centralized ones typically gather up all the data. So they send the whole task graph to a single node. And they'll, on that single node, they'll apply some algorithm and then scatter the results of that. And typically these don't scale, might work for hundreds or possibly even thousands of processes. But at some point, scalability will be a problem. And so the cost of this limits the value of running. So you have to run it infrequently. Another approach, which is somewhat scalable, is hierarchical approaches. So you'll form groups of nodes or spanning trees. Typically, these have log P scalability, but they can still be limited as system sizes increase. And so there's another class of load balancers that are fully distributed. They're typically very inexpensive to run. They're highly scalable. Historically, they've been difficult to get a really good load distribution due to the limited information. But in 2013, Harshita and Professor Kali published a paper with a new fully distributed strategy that actually obtains really good results compared to others. So in this work, we build on this paper and we find some issues that we improve for our particular workloads. So to do this work, we've built this LBAF, which is a load balancing analysis framework. It allows you to simulate load balancers in sequential code in Python. So you can implement a simulated distributed load balancer and test it, compute statistics on the data. So the way this workflow works is typically we take the application, we'll run it in VT on some number of processes, and then we'll output this load balancing data, typically one file per rank, that outlines the tasks in each phase and then break down across subphases and then communication structure. So on the right-hand side, I kind of have a sample of this. It's just a JSON file that specifies different entities on each node, how long they took, what resource they were running on, what collection they're part of, etc. And so what we do is we output that data after we run it in VT, and then we feed it into LBAF. And then in LBAF, we can easily test new load balancing algorithms that are distributed without doing all the work of actually implementing the distributed algorithm, which allows us to quickly research and develop, explore new strategies. And so then LBAF can actually output a new set of files, which we then use in the same format, which we then use as a mapping. So LBAF outputs these files based on some research load balancer we're building, and then we can input those into the application, and then the load balancer just follows the mapping that LBAF used. So we can actually test in the real application whether the load balancing algorithm we thought was better was actually better. And so we found this workflow to be pretty nice. And this framework is open source. It's on GitHub, and if anyone's interested, we are interested in collaboration on this, and we're working on enhancing it and making it more general. So the base algorithm that we're building on from this paper is fully distributed. As I said, it was inspired from these epidemic algorithms. It has no central coordination, no tree or group building. It essentially operates in two distinct stages. First, there's the gossip stage, where we randomly select ranks and spread information that way. And then a transfer phase, where we use the information we spread during the gossip phase to make transfers from overloaded processors to underloaded to reduce the imbalance. So here's kind of a graphical illustration. If we have 9 processes, here we have 4 of them that are overloaded and the rest that are underloaded. So they start out, none of them know about each other. And then during the gossip phase, which proceeds in some number of rounds with a fan out, each underloaded will send K messages to randomly to other processes. And in the first round, and then in rounds 2 to N, we'll just continue propagating this information. So we'll take the information we have, accumulate it with our information, and then forward it on. And you can optimize this process by not sending information backwards. So if you know that a previous rank already sent you its information, you forward it on to new processors. So it's not completely just picking a random processor, but you exclude the previous ones. And they call, in the paper, this is called informed selection. So once this is done, each underloaded processor or overloaded processor will know about a set of underloaded. And depending on how much information you transfer, it may know about more or less, depending on how many rounds in your fan out. And then during the transfer phase, each overloaded goes through the set of its tasks, and it decides locally to send some of its work to an underloaded processor. And in the paper, it builds a probability density function, which it uses to bias this based on how underloaded the processors are. So more underloaded ones will be picked more often, depending on how underloaded they are. So some of our improvements in the original paper, it was suggested that this just be run once. So you do the gossiping and then you do the transfer. So we had the idea to try to apply this algorithm iteratively. So instead of just running it once, we'll keep running it and see if we can keep improving imbalance. And then beyond that, because it's pretty cheap to run, we found that we could actually run multiple trials of this whole iteration process that are completely distinct. This will actually avoid us getting stuck in local minima. And we found this to actually be effective in practice. At some trials, even after multiple iterations, we would get stuck with some amount of imbalance that it wouldn't improve, but on other trials, it would do better. So this is sort of the algorithm for doing this. We basically reset all our state for each trial, and then for each iteration, we do the inform transfer. Instead of, it's called transfer, but we don't actually do the transfer there for each iteration. Instead, we just do bookkeeping for each transfer, and we don't actually implement it. And the same across multiple trials. So each trial will have a set of proposed migrations, and then depending on what we evaluate the imbalance to be, we'll pick what the best one was and use it. So the second optimization is during the transfer phase. In the original algorithm, we build this probability distribution function, which we use to determine the rank that we're going to try to transfer work to. And then this is sampled, this function is sampled to pick a possible candidate for transfer. So in the original paper, the CMF is computed once, and then we go through this loop where we go through all our tasks and then try to keep picking underloaded processors and try to transfer. And so in our modification, what we do is we actually reevaluate the CMF every time we make an assignment. So once a task is assigned to an underloaded processor, it might now be close to the average. So we shouldn't bias towards it as much. So by rebuilding the CMF, we can more carefully pick the next processor. So it's a small improvement, but we did find that it improves the performance of the algorithm. And the final optimization is relaxing the objective function. So to discover this issue, what we did is we created a synthetic load balancing problem in the load balancing analysis framework that has a huge amount of imbalance. So some processors, I think this was on simulated on like 128 ranks, several processors basically have all the load. And so if we use the original objective function during the transfer phase and we run this iteratively, we find that initially we have a bunch of transfers, but the rejection rate is very high. So many of the transfers are rejected. So it's around 94% rejection rate. It improves the imbalance, and then it sort of just gets stuck there, and the rejection rate just increases over and over for each iteration. So it's not making much progress. It goes from an imbalance of 280, which is a huge amount, to 182. So it makes a little bit of progress, but not a lot. And so taking this and looking at it, we realized that this high rejection rate hints that the objective function might be too strict. And so we make this relaxation to the objection function that allows transfers as long as the global maximum load doesn't increase. So the original criterion in this function is that if some underloaded processor plus the load of the object we're selecting is less than the average, then we enact the transfer because it's less than the average. It's not going to make it any worse. So the relax criteria just says that even if it does go over the average, it's allowed as long as the global maximum doesn't increase. So we take the load of the overloaded minus the underloaded, and if that's greater than the load of the object, then we go ahead and perform the transfer. And so on this synthetic problem with this new, this adjustment, the small adjustment, we're actually able to decrease the imbalance very quickly. So the imbalance starts at 280, and then the first iteration, it goes down to 3, and then pretty quickly it converges to around 0.62. In our paper, we have a proof of optimality for this, if you want to look at that. And we also notice that the rejection rate isn't as high. So it starts at 5%. And then as we expect, as iterations continue, the rejection rate goes up because we're getting closer to a good solution. And so the final thing we looked at was task ordering. In the original paper, task selection is arbitrary. So each process that's overloaded, when it's determining what task to offload, it just arbitrarily picks. And so we proposed several new mappings. The first one, which is a straw man, was just picking the most load intensive, so the biggest the task first. And then we have two other algorithms that we think should do better. And one is fewest migrations. So that picks the smallest task from the overloaded that will bring the load down to the average. So we want to pick the biggest one that that will satisfy the imbalance. So that way we minimize the migrations that we have to do. And then the other one, which is algorithm 6, is the most lightweight task. So we calculate what the marginal task is, which is the most load intensive of lightweight tasks that must be migrated for the rank not to be overloaded. So we do this by calculating these partial sums to find this task that's the most lightweight that can be migrated. So these are both total orders that we can apply to the tasks for the ordering. And so more details of exactly how we do that are in the paper. So we have built this load balancer in VT. We call it tempered LB. It implements the trials, iterations, and old new versions of the CMF and different transfer criterion that we've explored. All this is open source and can be found on GitHub. For evaluation, we're working on this application called Empire. It's a electrostatic, electromagnetic plasma physics application. It's a next generation application that's being developed at Sandia to replace an existing capability. And the part we're concerned with is PIC, a particle and cell algorithm. And for some of the problems they're running, the particle distributions can be spatially concentrated initially, which causes heavy load imbalance. And more interestingly, the particles can move rapidly across the domain. So there's dynamic workload variation that occurs. Particles can also be injected, they can be merged, all kinds of things that can happen that can change the distribution of particles. So load balancing is needed for this type of problem. And so I have a graphic here of kind of how we do this. On the left, we start with the SPMD mesh decomposition. So they run something like decomp. We take our mesh. It just splits it into the number of ranks. It doesn't look at the particles at all. So it just splits the mesh however it sees fit, probably based on the number of elements or something. And so on two ranks, it'll split it into these striped and solid regions. And so what we do is we take those and we apply a second level decomposition. So in this illustration, we use an over decomposition factor of 4. So we split each one of those into contiguous regions. And then the load balancer is able to move those along with the particles to get a better load distribution. In our actual runs, we're using more like 24 chunks per MPI rank. So that's our over decomposition factor. So these are some of our high level results with tempered LB. This is execution time of a problem called B-dot on an ARM cluster. And so on the very left-hand side, I have the SPMD performance. This is without tasking. And it's split up into the particle update and the non-particle update. The particle update is the part that we have implemented with tasking. So the non-particle update are things like the solver, which we haven't touched. And so if we turn on tasking without load balancing, we get about a 20% slowdown. This is mostly due to probably less efficient kernels and things that may be optimizable. And then when we use Grapevine LB, which is the original algorithm, we get about a 1.3x speed up or 1.5 on the particle update. using the original algorithm. And then we have greedy LB, which is a centralized implementation. It does the best on the particle update, so it gets about a 3.3x speed up. And then we have hierarchical LB, which gets a 3.1x speed up on the particle update. And then tempered LB is able to match that performance with the optimizations that we have implemented. So if we dive deeper into the performance, on the x-axis, I have the time step. So this problem runs for 1600 time steps. And then the y-axis is the execution time per time step. So the brown line is running without AMT, and the purple is with AMT without the load balancer. So you can see the overhead. And then the orange is the grapevine LB algorithm. And then the three load balancers, hierarchical, greedy, and tempered LB, all get about the same performance across the time steps and do a pretty good job. So to evaluate this more closely, we can actually look at the imbalance over time, which is calculated as the max over the average minus 1. So we want this to go to 0, ideally. So without load balancing, we have this purple line. So the imbalance is around 7 or a little bit over 7. And over time, this actually drops a little bit because more particles are introduced in the system. So relatively, there's less imbalance without the load balancer. And then the 3 load balancers down here, we can see, so we're running it every 100 time steps in this run. So I is pretty low. It basically stays below 0.4 during this entire run. And especially during this interval between 800 and 1100, we can see this is where particles are changing a lot. We can see where the imbalance starts to increase a lot, the load balancers run, and then it decreases, and so on. So it seems these load balancers are doing a pretty good job, and our new distributed load balancer is able to meet the performance of centralized or hierarchical load balancers for this problem. So we have also graphed for all these the max and the min rank for each time step. And so we can see kind of the range of the amount of load that each rank has. So these load balancers keep it fairly tight across the range. And again, during this interval, we can see where it starts increasing the max, and then it gets pulled down once it runs. And then finally, we tried our different task orderings on the same problem. So the most load intensive tasks, which is our straw man, and then the fewest migrations and most lightweight tasks. And for this problem, we didn't see much improvement, which was a bit surprising. We thought that these orderings would have more of a difference. It looks like that the most lightweight task actually performs a little bit worse. And so we're still investigating this. We think for other workloads that these other orderings might have more impact on the performance. So our main contribution is the set of improvements we've been working on. We identified some weakness in the load transfer. We established some new theoretical results that justify our relaxed transfer criterion. We demonstrated some benefits in the soon-to-be production application. We think that task orderings are interesting, and for the other applications we're looking at, we think they may improve performance. And so we're working on 2 other applications now that we're just starting to run the load balancer on. One is Nimble SM, which is a solid mechanics contact code that has very highly dynamic interactions. They're unpredictable. That's eventually planned into a pipeline into Sierra SM, which is Sandia's production solid mechanics code. And we're also looking at another application called Gemma. And it has a matrix assembly phase that's very imbalanced, but it's not a time step based application. So there's some challenges with applying persistence based load balancers. So yeah, that's all I have for today. Any questions?
I see Nils has his hands up. Do you want to go with the question?
Sure. Have you looked at this at all for mesh-based codes as opposed to particle and cell? Or maybe you haven't, you're just not allowed to say, but in any case, do you have any comments on or experience with this on mesh-based codes that you're allowed to share with us?
When you say like, so Empire has a mesh. When you say mesh-based codes, what do you mean exactly?
I guess sort of, you know, the last talk, discontinuous Galerkin or continuous Galerkin finite volume code, sort of more typical adaptive mesh refinement solving hydrodynamics.
Oh yeah, no, we haven't actually looked at those particular applications yet, but we think it's an interesting domain to study.
Yeah, okay.
Yeah.
Great, yeah, I'd be super interested to see what comes out of that. So.
Okay.
Professor Sanjay, you have a question?
Yeah. So first a quick comment. I think using not using the average is absolutely the right thing to do for this algorithm, as well as for greedy and so on. You should allow a little higher leeway like you have done. I would probably not pick LX, that I assume is the max. I would put some weight factor like 0.8, 0.7 LX or something. So maybe you can comment on that. Let me ask. And the reason is because you want the max to go down. You don't want max to remain where it is. I suppose LX is the current max, as in the, you're not updating the max continually as you go through the algorithm, are you?
Right, because we don't know the max because it's local. Or I mean, we don't know what the new max.
You don't know the current max as it evolves, but sorry, do you mind if I jump in, Jonathan?
Yeah, go ahead.
Yeah, so in as much as it's an annealing process, any given process is going to work itself downhill. You know, we're not going to make a transfer that looks like it's worse than, you know, making some other process more loaded than the donor currently is. So it's basically the loosest criterion we can give that, you know, keeps load moving around and giving it a chance to find a good place to land.
So can you say what is LX exactly?
Oh, this is that's
the load on process, or wait, no, hold on.
I thought that was the max across the
No,
system.
this is the under, so I believe this is the underloaded and this is the overloaded.
The LP. I interpreted this as LP plus OX greater than LX. So that's probably a better way of looking at that inequality. But adding to the processor's load, this object load doesn't make it bigger than LX. But anyway, I think this is too arcane. We can talk about that offline. But I would have liked a 0.8, 0.5 type number in front of that LX. LX minus. Okay, to the overload. But actually, my question, I have two separate questions. One is the same question that I asked Aditya and Weizhao in the earlier talk. You have over decomposition increasing the cost by some significant number, and you also kind of had, maybe it is because this or that, but have you done more precise analysis of that over decomposition overhead? It was a few slides earlier, no numbers on the slide. So.
Oh, sorry. Yeah, here where the
yeah, that one.
Is increasing. Yeah, we've looked at it some. We don't have extremely precise analysis of it, but as we over decompose, the kernels are going to become less efficient, and there is more transfer happening across the over decomposed blocks. So particles are migrating across them. So whenever that happens, it basically interrupts this very efficient kernel that just migrates the particle, you know, step by step across the portion of the mesh, and then it has to transfer across. So even if it's local, there's going to be overhead to doing that rather than.
I understand. I think I would just like to see that it broken down by the inefficient kernel component and the extra communication component. It would be very useful for the community. I think this community to understand that difference. But that's we can talk about that another time.
So without load balancing, there shouldn't be any additional communication across ranks. There'll just be communication within the rank that is occurring instead of just running the kernel.
Got it. Okay.
Yeah, I don't know, Phil, if you have anything else to add there.
No, I think that covers it.
Okay. Any other questions?
So it looks like there are no more questions. Thank you, Jonathan. We'll move on to the next talk. The next talk is by Ronak, who is a graduate student at UIUC, and he will talk about vector load balancing in CHARM++. Ronak, whenever you're ready.
Okay, can everyone see my screen and hear me?
Yes, we can hear you and see your screen.
So thanks for the introduction.
Not very clearly.
Give me 1 second then.
Yeah, you're very muted or muffled, very faint.
We can increase our volume, but so it's not unclear, but it's low.
Okay, is this any better?
Other people should speak. I'm not the best for judging audio.
It sounded better to me.
Okay.
Yeah.
Is this okay then? I'll use this for now. Okay, hopefully this is a bit better to hear. In any case, I'll get started. So as the introduction said, my name is Ronak Buch. I'm a graduate student.
Ronak, your screen is black. Yes, like we can't see your screen.
Oh, it's blank. Is this working now?
I still think we can't see your screen. I'll let someone else also comment.
No, I can.
Black. The very first time you shared it worked fine though.
Yeah, I'm doing the same thing. I don't know what's changing now.
But in parallel with that, send your slides to someone just in case.
Okay.
Nope.
Can you see my screen now? Is this working at
Nope.
all?
Still black. It just says Ronak has started screen sharing. So.
Did you put your application window into full screen? I think if you don't do that, it might be better.
I did. I've tried both ways.
Okay.
Is it PDF or PowerPoint?
It's a PDF.
Yeah, I would suggest in any case put something better. Nope, same.
Try uploading it to Slack and someone else can display it.
Yeah, put the PDF in Slack for the group, and someone else can.
Okay, I just sent it in Slack, so someone can pick that up and share it.
I can do that.
Okay.
Is this visible?
Yep.
Yeah, I can see it.
Let me know when you want to change slides.
Okay, okay. All right, sorry for all of that, but hopefully this works now. So yeah, let's get started. So I'll be talking a bit about the vector load balancing stuff we've been doing in CHARM++. This is just a sample of some of the work we've been doing. So there's a bit more than this, but these are the highlights for now. Let's go to the next slide. So first, I'd like to just talk about load balancing in general. So dynamic load balancing, obviously the session is about that in a way, but in case you don't know the ground of how things work, really what we want to do here is to arrange work on the PEs we have to maximize performance. And the reason we do this is that the execution time of the application is often determined by how loaded one of the PEs in the job is. The maximum load determines the iteration time. In CHARM++, we can do this because we have migratable objects and we have the CHARM++ runtime itself that can do load measurement automatically for applications. And we've seen in our own experience and through literature that we need this to scale everything except the most regular static applications. Next slide. So really, we should distill this down to even something more basic than that. What really is load? In some sense, load is this proxy we use to represent performance. Performance realistically is how an application runs, how quickly things finish, or time to solution, as it were. And load is a metric we can use to calculate things around performance. So it's really a metric measuring the utilization of a resource over some period that's correlated to what the performance of our application is. At the end of the day, we really want to minimize execution time. We don't really care if load is properly balanced or not. And so far, usually in most applications and up to this point, balancing for equal CPU time on every PE has been good enough to get high performance for lots of applications. But it seems like we can do better by using a richer set of metrics. So a lot of what I've been working on is exploring how we can collect these things and what we can do with them to improve performance. Next slide, please. So in particular, the result of all this is vector load balancing. The gist of vector load balancing is that rather than load being the single scalar value that traditionally has been CPU load, it's now a vector of multiple values. And this vector can be composed of things like CPU load, as we've been doing for so long, but also things like GPU load or network load or memory usage or IO load. It can also be the timings of separate phases of an application. So we often have force calculation, for example, and then integration to add those forces onto particles. And those are orthogonal parts of your application. So those can be different parts of a load vector. Separately, we can also do application provided things. So everything else that's resource oriented, the runtime itself can measure, but we can expose some APIs so that the runtime can say, we think this object has performance characteristics that correlate with this variable that we will pass in. Number of particles, for example, or different kinds of things that the runtime doesn't have awareness of, but the application does. Next slide, please. So to implement all of this and to get it working, one thing we have to do, of course, is measure different things. So to that end, we've added various features into CHARM++ to add the ability to store and use vector loads. In particular, we have an API that the applications can call into to indicate phase boundaries. So this is a single line call, and you can say that at the end of force calculation or at the end of phase alpha of your application, insert a call to the runtime, and then the runtime will start a new timer to determine the next phase of the application. So this very easily lets users pass in this data into the runtime system without too much modification of their application code. We also have things like runtime flags to automatically add optional runtime managed load. This, for example, we have one for communication, so it can automatically add the messages sent from an object or the number of bytes sent from an object as part of that vector if you just pass in this flag at runtime. We, of course, also have a way that the user can specify the load vector completely and explicitly. So if you have different scales or different phases that you as the developer know, you can just pass that in directly to the runtime. And we're adding right now ways to do GPU load, memory use, and things like that, the more sophisticated measurements that the runtime currently doesn't have. So those are all kind of future work, but we're planning on adding those one by one. Next slide, please. Okay, so one of the big challenges with the vector load balancing is that now we have a lot more data than we used to. And this extra dimensionality makes it very computationally difficult. One big takeaway from this is that objects can no longer be totally ordered because the vectors themselves could be, you could have one that's high and one that's low, and then another object could be low and then high. You can't necessarily give them an ordering. So what our goal is in terms of strategies is to minimize the maximum over all dimensions simultaneously. So in mathematical terms, we've taken a single variable optimization problem and made it now multivariable. So in order to do this, we need to develop new load balancing strategies that can use this new data and give us good solutions. Next slide, please. So to start with, we use the simplest vector strategies we can. So the most naive way we can do this is just look over all the objects we have, find the one that has the maximum load in some dimension, and then place it on the PE with minimum load in that dimension. Really, this only works well when the object has load in just a solitary dimension, like this 0, 0, 0, L 0 case. So if every object is completely orthogonal, then we can do this, but realistically, we need to consider the vector holistically and make sure that we don't overload it in certain dimensions. Next slide, please. So to get holistic vector strategies, there are a couple things we can do. So the main two that we've worked on is first, placing objects based on the largest load, as we just discussed on the previous slide, but then refining some of the partitions we decided on to improve balance. So Meneses, for example, has a way that supports vector loads, and that's what Meneses does. It will do this by partitioning and then adjust some of the edges to make them more balanced. What we've mostly focused on instead is to use norms. So a norm, of course, will take a vector and map that to a scalar. So what we do here is we find the object with the maximum norm and we place it on the PE with the minimum norm after placement. This strategy generally works pretty well, but computationally can be quite expensive. One thing to note about this is that the PE weight will vary with the object. So if you have two PEs, one that has load 2, 0 and one with load 0, 3, the 2, 0 PE is lighter than the 0, 3 case. But if the object you're currently considering has load 3, 0, placing it on the first object with load 2, 0 would result in 5, 0, placing on the second one would result in 3, 3. So under the 2 norm, now the position of those two things is switched. So depending on the object you're currently considering, the ordering of objects actually changes. So it can be very computationally hard to figure this out, and it's not necessarily consistent. Okay, next slide, please. So one thing we've done to use this is create this load balancer that we call norm-LB. And norm-LB has gone through several iterations, so I'll kind of go through those in order. Initially, what we did is just order them by norm and then just do an exhaustive search across all the PEs. So the quality is exactly what we want. We minimize the norm by placing at every single object. But the performance is quite bad. It's theta of the number of processors times number of objects. So you can see here, comparing the standard scalar greedy to this new norm-LB, the make span, which is the sum, the maximum of each dimension all summed together, is much better with norm, and that's to be expected. Greedy doesn't know about the vector, whereas norm does. So we get about a 15% improvement in performance. But looking at the strategy time, it's almost 2 orders of magnitude slower to use norm. So performance is quite bad. So we need to do things to fix how fast these applications or how fast these strategies will run. Next slide, please. So one thing we did to try to do that is to use KD trees. So a KD tree, if you're not familiar, is this arbitrary dimensional space partitioning tree. And the way that we use it to our benefit is that we can bound the state, the domains of space that we search as we find candidate processors. So this lets us rule out swaths of the candidate PEs and let us reduce the number of PEs we actually search through. KDs work really well for searching in a static point set. It's used a lot to do things like nearest neighbor. But here it's a bit complicated because we update the tree every time we assign something to it. The elements in the tree are PEs. So every time we assign an object to a PE, that has a new load now, so we have to redo what the KD tree looks like. And there are a couple of problems with that. One is that updating a KD tree can be very costly. And second, these updates often result in an unbalanced tree. So we don't get the benefits of what the tree structure normally gives us. And in fact, in some cases, this is worse than the naive exhaustive version I just talked about. So this is a step in the right direction, but it's not good enough to be a solution. So next slide, please. So one way we try to get around this is looking through the literature. There's something called random relaxed KD trees. So random relaxed KD trees will help fix these things by two different things. One, they're relaxed. So what that means is that in a KD tree, normally at every level, you cycle through discriminants. Discriminant is the dimension you split on. So the root will split on dimension 1, and then its children will split on dimension 2, so on and so forth until you get to dimension k. And then it'll start again from dimension 1. Instead, in relaxed KD trees, each node stores an arbitrary discriminant. So both a node and its child can in fact split on the same dimension. And this gives us some flexibility in how we construct these trees. The second big important thing is that they're random. So the discriminant is uniformly randomly chosen. So we have equal probability at each node that it can split on any of the dimensions 1 through k. And the second important thing is that each insertion has some probability of becoming the root or the root of the subtree of the child or the root of the subtree of that child and so on. So we get this implicit balance because of the stochastic property of the tree. Next slide, please. So here's a comparison of a visualization of what the two different kinds of trees look like. On the left, we have a standard KD tree, and on the right, we have a relaxed KD tree. So you can see here that the children on the relaxed KD trees sometimes will split on that same dimension. And we get sort of what can look like an unordered split. But in truth, this ends up giving us a lot of flexibility and better performance when it comes to particularly our case where we update the tree a lot. Next slide, please. So we used a random relaxed KD tree to implement normal LD, and we got a lot of benefits from doing that. So the results for all of these three methods are the same. Both the exhaustive, the standard KD, and relaxed KD result in the same mapping at the end of the day. But the time it takes to get there varies drastically. So here we have two columns. We have one with 1E4 PEs and 1E5 objects, and then one with 1E4 PEs and 1E6 objects. So we see the exhaustive one, as we expected, kind of performs poorly globally. The standard KD gives us a big improvement in the first case, but in the second case, we see it's actually slower than the original exhaustive version. But the relaxed implementation is better in both. It's still not necessarily where we want it to be, but it's a big step in the right direction in terms of performance, and we don't sacrifice any quality by doing this. So things have improved a lot. We're still looking to do a few more optimizations there, but things have started to go in the right direction with regards to performance. Next slide, please. So here are a couple of performance plots. So I'll run through these quickly. So here's just a sample run of an AMPI application with no load balancing. And here we can see these different phases lead to different amounts of load on each of the PEs. Next slide. So here with regular load balancing, we see that happens right about halfway through the execution. On the left is before load balancing, on the right is after load balancing. We greatly improve what performance looks like, but we still have some gaps in between these different phase boundaries. And a lot of it is because this is run with a load balancer that doesn't have vector awareness. This is regular load balancing. Next slide. So here you see the difference is less dramatic, of course, but with vector support, we get much smaller margins between these different phases after load balancing happens. Next slide. So looking at the actual performance in terms of speed up, just adding load balancing gave us a 1.44x speed up over the case without load balancing at all. But adding phase awareness and using a vector load balancer gives us a 1.67 times speed up. So we still get better results when we add in more sophistication and more awareness of what the application is actually doing and utilizing that when we are making load balancing decisions. Next slide. So again, this is sort of the same thing, but now in the charm application. So here we see a very simple phase-based application. The next slide. So this is the utilization across time. Next slide. So when we go from no LB to using scalar LB, now we see chunks where we actually use all of the machine, but we still have gaps in between phases as we saw before. Next slide, please. And here again, with vector LB, we see a much improved utilization and much smaller gaps in between phases because now we're doing more intelligent placement. Okay, next slide. All right, so another topic I'd like to talk about is what I've been working on a bit more recently. So we've seen that vector loads give us much better performance insight, and this is because we get nuance and detail in what resources and what time an application is actually running. However, that doesn't necessarily improve all applications. And we've seen this, this isn't a new lesson, we've learned this lesson before. Performance can vary a lot based on the location of objects, for example. So applications that do a lot of communication are very reliant on having locality because the distance between where you place objects that communicate with each other can change latency, can change the load on links and routers. And these things aren't necessarily captured by just the standard load metrics. Even using a vector doesn't necessarily give us awareness of what these things can be. So usually we've solved this problem in the past by using graph partitioners or geometric balancing strategies. And so far we didn't have support for those things with these vector strategies. So Charm supports all of this stuff, but just not in a way that we can easily integrate it into this new framework and new vector-based world that we're adding. So we decided we should add that. For vector, we're first adding application positions, and then later on, we're going to work on adding the com graph. So I'll talk about the application position work first. Next slide. So in order to get this working, we've added an LB position API. And in general, right now, applications that use geometric strategies use this very ad hoc way of passing data. ChaNGa, for example, has used this for a long time and uses a Charm++ feature that is called user data in load balancers. Basically, you can register some chunk of data, pass that through a void star, and then the load balancing strategy can get that. But it's not typed, it's application specific, and every application then needs its own custom LB strategies. And when we're adding new features from the runtime side, we then have to integrate them into each application individually, and it creates this big complexity. So I wanted to solve this problem, standardize things, and make it easier both for us as developers and for application users. So to do this, we've added this standardized LB position API to Charm. So the API call basically looks like this. We have a set obj time right now that lets you pass in object loads. So we've also added a set obj position, and it takes a vector of basically floating point types. It allows positions of arbitrary dimension, and the load balancers we have also support arbitrary dimension. And the way it works basically is when you write a load balancer at registration time, you can say this is a position oriented load balancer. You can opt in, and then the framework will start passing you positions. So this kind of solves the problems that we had before. It allows for very generic application agnostic strategies. So now instead of writing one specifically for ChaNGa, I can use that with other astrophysics applications or other things that need locality. So this is fully implemented. There are no real publishable or results to show quite yet. I'm currently testing this with ChaNGa and other applications. But right now we're expecting this will go out in Charm 7.1. And hopefully very soon I'll have results that validate that this works at least as well as what we had before. Next slide, please. So the obvious next place to take this is vector geometric strategies. One of the whole reasons we added this was that so we could support things like this. So like I said, one of the things that we've been working on is using orthogonal recursive bisection with the position API that we just added. So I have an implemented version where this all works in Charm. And now what I'm doing is adding vector support to it. The way that orthogonal recursive bisection works is that in the scalar world, we pick a dimension and we find a point, a coordinate in that dimension such that we split the objects into two halves. And we select that coordinate such that we minimize the difference in load between both halves. Ideally, the difference is 0, which means both halves have equal load. In the vector world, things are a little bit more complicated. Each dimension in practice is going to have a different split coordinate. So we can't just split it at one particular point. So I've been toying with some different ways of doing this. Either you can take the average at each dimension, you can try to find a point that minimizes the square of all the sum of the squares of differences in each dimension. Another thing we've been trying to do is, rather than having a split at a single coordinate, we create a region. So in a 2D case, for example, instead of splitting at a plane, we split at a region, at a volume. Everything on the left of the volume still goes to the left, everything to the right of the volume still goes to the right. But things in that neighborhood around the coordinate, things that are objects that are inside that volume, we can arbitrarily place in either half, depending on how it affects the load vector sums of both halves. So this is, like I said, still a topic of active experimentation and trials, but that's currently where we're trying to push these things. And we want to make sure it's useful. All the things that we're adding in terms of vector loads is still useful for programs that need communication locality. Next slide, please. Okay, and then some more future further vector LB work. One of the things we're looking into as well is doing dimensionality reduction. So obviously, as I said before, complexity can grow a lot when we have vector loads. So if we could reduce that down and make a 5-dimensional vector into a 3-dimensional vector, that would help time solution a lot. Performance, as I said, can still be an issue. So we've made big strides with NormLB, and now things are a lot faster than they used to be. But even further than the stuff that I discussed, we also have bounded versions of NormLB that let you bound the number of states you search, for example. This will give you worse quality in all likelihood, but it lets you constrain performance and make sure that you get more well-defined iteration times when it comes to strategies. There are more optimizations we can do. There are, in particular, since this is an optimization problem, we can use a lot of relaxation and approximation to tune things, because we don't need the perfect solution. We need something that's good enough and fast enough for that particular application. Another thing we're working on adding is support for constraint-based objectives. Right now, we just minimize the entire vector, but we don't necessarily always have to do that. If we, for example, have memory as one of the elements of that vector, minimizing it doesn't necessarily make sense. We just need to make sure it stays below the physical capacity of that machine. And same for things like cache. And speaking of memory and cache, one thing we're also working on adding is support for different kinds of load, as I said earlier, things like GPU and memory and IO load. Next slide. Okay, so that was an overview of the stuff we've been working on and the directions we're hoping to take with vector LB. But so far we've learned that there are a lot of complex modern applications where we need sophisticated performance measurement. Just a single value that describes a very coarse measurement of CPU utilization isn't good enough to really capture the properties of how applications run today. Combining these different metrics into a vector, we've shown, has been able to improve the quality of load balancing for several applications. And it's become very obvious now that new techniques that we develop, like vector LB, have to maintain communication locality to actually be useful for certain class of applications. And without that, we won't really be able to apply the new techniques we have into the applications that you all will develop. So we're working on making that more integrated and easy to use. Okay, that's all I have. I'll be happy to take questions.
I think Brad has a question.
Yeah, please go ahead, Brad.
Yeah, I've got maybe just a couple of basic questions. The first one goes back to, on slide 13, you had a table with kind of 3 rows. There was sort of the standard approach, the standard KD, and then the relaxed KD. In the standard KD, you showed that in some cases it helped a lot. In other cases, it hurt, actually. Do you have any, is there any intuition as to what it is about a workload that makes it likely to help or hurt in those cases? Is it simply a matter of scale, or is there something more about those workloads or some sort of bad behavior it got into that caused it to be so much worse?
So my suspicion is that it's effectively scale in that it has to do with the number of objects you do, the number of updates you do to the tree.
Okay.
The reason why is because we do very structured updates. Basically, we try to find something that's low, one of the smallest elements in the tree, and we try to make it one of the biggest elements in the tree every time. So since we do this over and over and over again, we almost specifically try to unbalance the tree. So I think that's where the big performance loss is, and that's why relaxed helps so much, because it implicitly will try to keep things balanced.
Okay, great. Thanks very much. The other question I had, so in slide 21, when you showed the improvements with your approach in Charm++, this may have just slipped by me too quickly. So I understand the concept of vector load, but I didn't understand in that experiment, what was the arity of your vector and what different metrics were you using in the vector load?
So yeah, I didn't explain those very deeply, just in the interest of time, but in those, these were phase-based applications. So I think I was running with 3 or 4 different phases. So it was a 4-dimensional vector. And basically these were phases that had some overlap, but having some awareness of that, we could actually place those better than using scalar approaches.
Got it. Okay, great. Thank you very much.
Maybe Ronak, can you explain or have you adequately explained why phase-based applications need vector, or what is a phase-based application? I mean, you have that AMPI figure that maybe you can explain. It's like if phase 1 is balanced, well, balancing phase 1 plus phase 2 is not adequate. You can probably just show that figure one more time for the rest of the, I'm sure Brad knows this, got this, but
sure,
I wasn't clear that it was explained.
Right, yeah, just.
Oh, I don't know if, sorry, it's not you who can show the slide.
Yeah, I'm trying to share it again.
That's okay, not important.
Getting a problem.
But yeah, just as a brief overview, the whole point of that is that lots of scientific applications need, they rely on the output of a certain computation to do the next phase of the application. So there's kind of either implicit barriers or explicitly there are separate phases of the application where data passes from one step to the next. And if these are iterations, and if these are fully between load balancing periods, then great, you probably don't need vector because that maps exactly with what we measure. But in lots of applications, these are kind of iterations will have these individual subphases. And these individual subphases will, again, depend on each other. So if you just balance one of those things, other ones may be imbalanced and vice versa. And if you measure all of them collectively, certain objects may be heavy in one part, but light in another. So you don't necessarily get good global balance, even though it seems like you're measuring everything and balancing on everything. In truth, the underlying distribution isn't actually good when that's all you have to base your decisions on.
Okay, great. Thanks very much. That makes a lot of sense.
Sure. I think I saw Nils had a question too, his hand up, but maybe not.
It was more of a comment that these last things of adding the position and everything is very reminiscent of discussions we've had for AMR and these types of computational fluid dynamics applications. So I'm really excited to see what comes out of this, especially if it's in 7.1.
Yeah, that was part of our motivation, was the discussions we had with the Spectre team. So yeah, of course, hopefully it does remind you of that.
And hopefully it is clear that that's orthogonal, the vector from vector loads, that there is a little vector here of positions, but that's, I mean, this is just to facilitate, and this is actually an invitation to the community, maybe Jonathan, Phil, and others, as well as anyone else. You can write a generic balancer based on knowing the positions of objects in space, assuming nearby positions communicate more. And so various types of approximate algorithms for that ORB is what we are working on anyways, and so would be a good thing to have in the repertoire.
Exactly, and I think to that end too, if people have ideas of other such like optional features certain balancing strategies can have. I know we've done this in the past in Charm with ComGraph that we're planning on adding again to this framework. But now you can kind of add these traits as we see them to particular strategies. So if there are other things that people think of could be good things that we could make more generic that currently is a specific thing to your application, then I would love to hear those as well.
Does anybody have any more questions?
I think Gangbin has his hand up. Do you have a question, Gangbin?
Oh yeah, I'm a little bit confused with the phase load balancing. Do you actually migrate objects between phases?
No. So that, yeah, sorry, go ahead.
So you basically determine the global, like optimal positions? for all the phases?
Yeah, that's sort of the motivation, is that we measure all the phases. So in between calls to @sync or in between calls to load balancer, we store data that measures each phase individually. So then when it comes time to actually run the load balancer, we know where certain objects are busy. So we use that to make a decision with this more specific detailed data. So we don't balance them at every phase, but we use that data when it comes time to actually balance to have awareness of what phases certain objects of certain P's are actually busy in, and use that to improve our placement decisions.
Yeah, and I must add, Gangbin here, that Gangbin's thesis, he had done work on a class of strategies which, especially for the phase-based balancer, between phase A and phase B, they allow in each iteration, some objects can be just moved. And that's an additional degree of freedom for the load balancer to say it might still be better every iteration to move the objects when we transition from phase A to phase B. I think that still remains correct, but Ronak's strategies, when this collection vector balancer doesn't go in that direction.
I see.
Yeah, that's right. And one thing I'll add to that is that all this vector stuff is built on top of the new infrastructure TreeLD that we talked about a bit last year. And that lets us basically do hierarchical LB at any point. So we could make it such that we do, for example, we do node local load balancing at every phase, or we can do migrations locally since they should be low cost, and then use that same information, but less often at a global scale or at a regional scale in terms of the job. So ideas like that could be valid. Again, we could put that into the framework. We just don't have that right now.
Okay.
Any more questions?
Well, I suggest if there are no questions, we take a break. And I think instead of taking a 7-minute break, we take a 17-minute break. Is everyone okay with that, including the next speaker? And you might want to put up a slide there saying resuming at 3 o'clock or something.
That works fine for me. Thanks.
Yep. Okay, Brad. All right. Thanks. All right. Let's stop here then.
Fred, if you're ready, you can go ahead and start sharing your screen just to make sure that's working.
Okay, sounds good. Thanks. How's that?
Yep, looks good.
Okay, and just to check the obvious, when I advance, it advances?
Yep.
Great, thanks.
Okay, so we'll give people about 5 more minutes to come back.
Yep, okay, sounds good.
Okay, I think we can go ahead and get started now. The next session. This session is on programming languages, and the first talk will be by Brad Chamberlain of HPE. He'll be talking about the Chapel parallel programming language and updates to it in the recent past. Brad's been at HPE Cray, leading the development of Chapel since its beginning in 2006. So go ahead and take it away, Brad.
Okay, great. Can you hear me okay?
Yep.
All right, great. So yeah, I'm Brad Chamberlain. I'm the technical lead for the Chapel project at Hewlett-Packard. And I want to express my appreciation to Szaday and to the organizers for the opportunity to speak today. It was suggested that I talk about some of the things that are new with Chapel. So I picked out 3 of the things that I've been recently excited about, and they resulted in a nice amount of symmetry here in the title. So I'm going to talk about a few user applications that I'm particularly excited about these days, some work we've been doing with aggregators in Chapel, and then some work we've been doing targeting accelerators. So let's go ahead and get started. Let me get focused in the right window. All right, so what is Chapel? If you're not familiar with it, I'm not going to be able to give you a very in-depth introduction today, but you'll hopefully pick up a little bit of as we go. It is a modern parallel programming language. It's designed to be portable and scalable. So we do a lot of our development on just sort of commodity laptops. I do a lot of mine on a Mac. And then you can take those programs and run them on clusters or the cloud or supercomputers by HPE or other vendors. And it's an open source and collaborative project. So we do our development at GitHub. It's licensed with the Apache 2.0 license. And like any good open source project, we get code contributions from users and collaborators in the open source community. The 2 high-level goals of Chapel are to support general parallel programming, which you can think of as if you have some parallel algorithm in mind and some parallel hardware that you'd like to run that on, you ought to be able to do that in Chapel, or else we're not succeeding at this goal. And the second is to make parallel programming at scale far more productive than it is today. So in particular, trying to get beyond the sort of MPI plus X world that a lot of the HPC community is relying on to do their applications today. Sometimes people like to know how Chapel compares to other languages. Probably the easiest way to say it is we're trying to create a language that is as nice to read and write code in as Python, which I think for a lot of people is sort of the standard to beat nowadays in terms of easy to use. But where Python has historically had problems with performance and parallelism and scalability, we want to sort of maintain what is sort of expected from HPC. So scalar code that's as fast as Fortran, scalable as MPI or SHMEM or UPC, as portable as C in the sense that you can run it anywhere, and as flexible as C++ in the sense of being able to create your own types or overload operators or methods, or sort of expand the language from within the language, if you will. And then the last bullet here sometimes gets a little snicker within the HPC community, but it's about being as fun as your favorite programming language, because our belief is that many people get into programming because they really think it's fun, they enjoy it. But frankly, in HPC, I mean, it's fun to run on big systems and get good performance, but the programming part of it, I would say most people don't find that fun. And I think as a community, we have a hard time attracting and retaining people for that reason. So what can we do to make programming HPC systems fun in addition to thrilling? This is my sort of 1-slide overview of Chapel, and we'll get a little bit into some more of the code later on, but only just a bit today. So over here on the left, I've got a couple of standard benchmarks, Stream Triad at the top and HPC Challenge Random Access at the bottom. And these are written in C plus MPI. And so as you might expect from those models, there's quite a bit of code to express what are really some fairly straightforward computations. These blue boxes in the middle show the equivalent Chapel code. And so you can see it's much more succinct. And if you spend a little time with it, you'd probably be able to guess what it's doing pretty well. And the reason there is, again, that we have leveraged a lot of advances in modern programming language design. And we've also implemented parallelism and locality as first-class concerns in the language. We think these are the 2 main things that HPC programmers need to be concerned about. So rather than sort of tacking them in after the fact, they're sort of built into the language from the start. And then over here on the right, I've got a couple of performance graphs. These are going up to 256 nodes, or about 9,000 cores on a Cray XC. You can see in the case of Stream Triad that we're basically competing neck and neck with the reference version. In the case of random access, we're actually outscaling the reference version by a large amount. This is to a large extent because we've written the computation in a high-level way that lets the compiler optimize it better. And it's a particularly good match for the Cray XC, which has atomic operations in the network. So that's a case where we can really do great. Now, if it were only benchmarks, that's not all that interesting. So in the past few years, we've sort of moved from being like, yeah, try out the language and see what you think about it, but you might not want to use it for your real work, to actually encouraging people to use it more and more for real applications. So this slide shows a handful of the most notable current applications being developed in Chapel, and I'll be talking about a few of these today. So this is actually a good time for me to jump to my outline. So I've given you just a bit of context for Chapel. Next, I'm going to talk a bit about a couple applications that I particularly like these days. Then I'll give you a quick tour of some basic Chapel features that will be helpful for the rest of the talk. The section on aggregation, section on aggregators, and then of course I'll wrap up. All right, so jumping back to this application slide, one of the things I really like about this application slide is that early on in the project, people would say, you know, if you just had a killer app, you know, people would stop asking like, why are you doing a new language and stuff? But we were sort of resistant to having a killer app because we didn't want to get pegged as like a one app language or anything like that. And so one of the things I really like about the slide is that you've got, you know, sort of traditional scientific simulations up here at the top, like computational fluid dynamics and astrophysics. And then you've got more sort of data science or sort of numerical computing types of things like this Arcuda NumPy, this branch and bound optimization framework, and some AI work that we're doing in-house here. So the first app I want to dive into just a little bit today is Arcuda. And again, Arcuda is basically a Python library that supports NumPy and pandas at large scales for doing data science on huge data sets. And so we usually say that this computes massive scale results within the human thought loop, where massive scale is like multi-terabyte scale arrays, so often dozens of terabytes in each array. And then within the human thought loop is to turn those operations around in seconds to minutes, so you don't lose your train of thought as you're sort of going through a hypothesis and massaging your data and manipulating it and examining it. And this approach uses a Python client Chapel server model. So the user is essentially sitting in their Jupyter notebook, typing Python commands that look a lot like normal NumPy and pandas commands, but they're implemented using the Arcuda library rather than NumPy or pandas. And then under the covers, that's communicating out to a server written in Chapel out on the supercomputer or whatever that's actually doing the computation. And that gets you the scalability and performance. So this is an application that's currently about 16,000 lines of Chapel, most of which was written in 2019, but there have been continual improvements since then, both in terms of building out new features and improving the performance. This was developed primarily by Mike Merrill and Bill Roos at DoD. There are a number of other people working on it as well now. And it's an open source project. So if this appeals to you or you just want to dig into it some more, here's the link. You can go and download it and run it. And then if you were to ask them, why did they use Chapel? Some of the top reasons. The first one is it's a high-level language with performance and scalability. And this high-level part is key because since they're catering to Python users, they wanted to choose a language where if those Python users looked under the hood in order to add new capabilities or tinker with things, they wouldn't be repelled by what they saw. They would find it reasonable and natural. And in practice, they've actually had some Python users get their first HPC codes running as a result of having written this in Chapel. It has great distributed array support, which are really heavily used in Arcuda, and it ports from laptop to supercomputer. So like us, they do a lot of their development on MacBooks and the like. And then once they've got it working, they can just take it to the supercomputer, and it typically works right out of the box there as well. Oops, sorry. So the one other thing I want to say about Arcuda, so recently we've been looking a lot at sorting performance within Arcuda. And this is a hero run we did this summer on a large Apollo-based system from HPE. We sorted 72 terabytes of 8-byte values, and we achieved a rate of 480 gigabytes per second. So it ran in about 2.5 minutes. And this used 73,000 cores of AMD Rome, which is more cores than I ever would have expected I would get to run on when I was a grad student. And the part I like about this is about 100 lines of Chapel code. And now I don't track sort of the world of sorting very closely, but what I've been told is that this is pretty close to the current world record holder for sorting performance. And I would argue that if you thought about performance in terms of number of lines of source code, this quite likely is a record, because I have a feeling that most others are probably a lot more heroic, although I don't know for sure. Jumping to the other application I want to talk about today, let's look at this CHAMPS, which is a computational fluid dynamics framework. So this, as I said, 3D unstructured computational fluid dynamics framework used for airplane simulation. And this is about 48,000 lines of Chapel code that was written from scratch in about 2 years' time. Sorry, is somebody trying to get a word in? No, okay. So this was written by a team led by Professor Eric Laurendeau at Polytechnique Montreal, him and his students and postdocs. And why did they choose Chapel? Well, primarily the performance and scalability was competitive with MPI plus C++. And frankly, the students found it far more productive to use. So they actually convinced their advisor to let them use Chapel. He was reluctant, he thought it was too risky. And happily, he's now very happy that they made that choice. So in the past 6 months or so, the CHAMPS team has been presenting at a number of industry and for them nationwide places within Canada. And what's really cool about this work, I think, is that their workshops, unlike ours, instead of people going and talking about their work and sort of listening and then going back home again, they're typically all working on joint problems. They come in with sort of their results and they sort of share the results. Here's what we got, here's how we got them. And so it really is much more of a working workshop, I guess, than a lot of ones we go to in HPC. And as a result of that, what they've found is that they're achieving results that are at similar large scales and quality of results to other major players in industry, government, and academia. And I think this is pretty notable. They've been able to pull this off in just a couple of years. So we invited Eric, their PI, to give a talk at our annual workshop this past year. The title of his talk is here. And I'm just going to call out some excerpts here because it sort of reinforces this productivity benefit that I mentioned. So he said, to show you what Chapel did in our lab, NS Code, which was their previous framework, ended up being 120,000 lines. And my students said, we can't handle it anymore. It's too complex. We lost track of everything. And today they went from 120,000 lines down to 48,000 lines, so about 3 times less. But he goes on to say, but the code is not 2D, it's 3D. It's not structured, it's unstructured, which is way more complex. And it's multi-physics. It's got aeroelastic and aeroicing. So he's got industrial type code in 48,000 lines. So for him, this is the proof of Chapel's benefit, plus the smiles he has on his students every day in the lab because they love Chapel as well. And that's the key, that's his takeaway. And he goes on to say that Chapel promotes programming efficiency. They ask students at the master's degree to do stuff that would take 2 years, and they do it in 3 months. So they have things that they do in a summer internship that they just couldn't do before. So I pulled out these quotes, obviously, because they make me happy in terms of Chapel's productivity. But I want to point out the whole talk is available online, and it's a really great talk if you want to learn about the use of HPC within aerodynamics and aeronautics simulation. All right, so with that, I'm going to jump out and give you a brief tour of a couple Chapel features that'll be key for the rest of the talk. And I'm going to be focusing on the lower level features within Chapel here, specifically support for creating tasks in the language and for controlling locality. So one term you need to know before I dive into some code is this term locales. In Chapel, a locale, which you've seen on some of my graphs, is the unit of the target architecture that can run tasks and store variables. So on most HPC systems, you can think of a locale as being a compute node, and that's a good approximation. And when you run a Chapel program, you specify the number of locales to use on the command line. So like here, I'm saying run on 4 locales. And so when I run my program, I'll get 4 compute nodes to run it on. And within the code, I'll have this built-in array called locales, which has 4 elements in it, 1 corresponding to each of those compute nodes. And one other thing you need to know is when I start running my Chapel program, all the user code, the main, if you will, is going to start running as a single task in locale 0, and then it'll spread out from there. All right, so with that, let's look at some code. This is a task parallel hello world program in Chapel. And just to call out some features, this identifier here that I'm referring to is essentially a built-in way of referring to the locale in which I'm currently running. So in the first query here, I'm asking how many processing units or cores does this locale have? I'm storing that in a variable called num_tasks. And then later on, I'm asking what the name of the locale is so I can personalize my message. Then we use a co-for-all to actually create the tasks. And a co-for-all is like a for loop in most languages, but it's a concurrent parallel loop. And so each iteration is going to be executed by a separate task. So in this case, I'm going to have a trip of the loop per core. Each of those is going to be a separate task. And so each task is going to be printing out its own little hello message. And because I haven't done anything to coordinate between those tasks or synchronize between them, those messages are going to come out in an arbitrary order, as you can see over here in my terminal, right? So each one sort of prints out, I'm task 3 of 4 running on this node. Now, nothing in this code refers to other locales. So this is a shared memory program, and I would never actually leave locale 0 if I ran it. So we don't have the kind of dynamic migration of data and tasks as in Charm++, for example. We're a much more explicit language in that respect. But with a fairly simple change, I can turn this into a distributed program. what I'm going to do is add another outer co-for-all loop here, and I'm going to iterate over that locales array I was talking about before to essentially generate a task per locale. And then I'm going to use this on clause to tell each task to run on its corresponding locale. And at this point, I've essentially created SPMD execution across my machine. And then I'll execute the same co-for-all as before, so that each one will query how many cores do I have, and let me print out a message per core. And so with that sort of additional nested parallelism, I've changed this from a shared memory code into a distributed memory code that'll run across as many compute nodes on my machine as I let it. All right, so that's your quick introduction to Chapel. With that, let's turn to some recent work we've been doing with aggregators. And this work I'm going to exhibit in the context of a Bail computation. Some of you are probably familiar with Bail, particularly index gather I'm going to be looking at today. And this is basically just a gather operation. So I basically have a couple of distributed arrays, the destination array and the indices array, which are of the same size. And I'm going to basically be gathering from that, into that destination array from my source array, which could potentially have a different number of elements, but is also distributed. And if we look at this, so this uses a for all loop. We haven't seen a for all today, but I'll tell you that under the covers, what this essentially gets lowered down to is code that we have seen today. So we have a co-for all loop across all of our locales that destination array is distributed across. And so here again, I've got that SPMD style execution. And then we do task parallelism across the cores again. And then we have a serial loop within here that's basically taking the subset of the index space that this locale owns and sort of doing those updates from the source to the destination array, which I'm realizing I misspelled here, one at a time. And so something you might think about here, eventually we thought about, it took us a little while, was that, I as the user have told you this is a for all loop. All the iterations can be done in parallel. There's no dependencies between them. But then at the inner loop here, I'm basically using a serial loop to implement them. And because my destination and source arrays are distributed, this is typically going to be generating communication and very expensive communication. So why am I doing those high latency operations serially? And so once we made this observation, we basically came in and did an optimization. So since you've asserted to us that this is a for all loop, that these are order independent iterations, what we do is in our compiler, we now rewrite this serial loop into this loop that uses an unordered copy. You can think of this as like a fire and forget kind of assignment, or not really forget, but forget until the next fence. So we sort of fire these off as quickly as we can. And then at the end of the for loop, we do this fence to sort of make sure that all those operations have completed before we go on. And so on the next slide, what we'll see is the performance this gives us. In the light blue down here, we've got the naive version where I'm literally having each task serial do its remote gathers one at a time. And then this dark blue shows the unordered version that I've just shown you. And you can see you get something like, I don't know, maybe an 8 times performance increase by doing that. But what we found comparing to other implementations of Bail index gather was that we're still losing by quite a bit. So while this is really great, it's still really fine grained, and fine grained communication is never great on HPC systems. So what we did was we implemented a new library, copy aggregation library. And so I made just a couple of minor modifications to the code here. The first is I'm actually using the module that provides the library. And then I'm using this syntax, which basically gives me a task private variable within my for all loop. So rather than creating a variable one per iteration, it's one per task that's helping implement this for all. And specifically, I'm giving each task its own copy of this source aggregator object that's defined within this library. And this is going to basically do aggregations and get us coarser grained communication. And the one other change I have to make here is to change my assignment into a call to this copy method on the aggregator, which basically says we're doing a copy. And then what the aggregator does automatically is as it aggregates these copies and as its buffers fill up, it's going to communicate those operations to the remote locale automatically without any user code telling it to, and asynchronously. So this is our aggregated version of index gather. And the performance we get there is, as you can see, much better. What is like 1.5 times better than the previous version, something like that, with relatively minor and straightforward code changes, I would say. And even better than that, so nothing about these aggregators sort of required to change the language or change the compiler. So this is something that if we had not written it, you as a user could write it. It was about 100 lines of fairly straightforward Chapel code. The entire module is something like 420 lines. And this was developed by my colleague over the past couple of years. I also mentioned, going back to that Arcuda hero sort we saw before, these aggregators have been key to our getting performance results like this. So if we didn't have aggregators, this performance, this graph wouldn't look nearly as good as it does today. And then one other thing I want to say in this section is that, as a compiler person, I think a question that one would ask is, sure, this rewrite isn't that bad. I haven't had to change the code too much, but could the compiler be doing that for me? So this is a question we asked in the last year or so. And one of my other colleagues found that, yeah, in many cases, we can have the compiler automatically transform this simple version of the index gather into the more optimized version. And this is a paper that Engin published in LCPC last week. So if this is something that's interest to you, go back and take a look at that. He talks about how we achieve that. And what you can see on this graph in green is that automatically aggregated version using the naive implementation of the algorithm actually performs neck and neck with the manual aggregated case. So that's a great result for us. And that wraps up my section on aggregators. And so next I'm going to switch to my last section about Chamberlain GPUs or accelerators. So the case for Chamberlain GPUs, I think, is very simple and straightforward. I said at the very beginning of the talk, Chapel's designed for any parallel algorithm on any parallel architecture. But one of the more embarrassing things we've had to admit in recent years is people say, like, well, what about GPUs? And we say, well, we don't really do that yet. Obviously, GPUs are more and more important in HPC, so that's been a big gap in our portfolio. Now, it's not as though this has never occurred to us. We've been doing work for almost 10 years on Chamberlain GPUs. In fact, it was pioneered by Albert Sadelnik from UIUC back in 2012. He was the first person to get some Chapel code running on GPUs. And there have been other efforts since then that have been done, but none of these have made it onto master. So if you were to download the Chapel release and try to compile for GPUs, there just hasn't been any support for it until our most recent releases. So I'll say that users have used Chapel with GPUs, but they've done this through interoperability. So they write their kernels in CUDA or OpenCL or things like that, and they call out to it. But again, that's not ideal from a productivity standpoint. And we would argue that Chapel's features for parallelism locality that you've seen are a really good match for GPUs. And for us, code generation has been the major sticking point, where we're currently tackling that by leveraging our LLVM backend. So the idea here is we have something in language called hierarchical locales. So in addition to locales I showed you earlier, locales can contain sublocales. And so this is a notional model where imagine that each of our compute nodes had a sublocale representing the GPU. And so if I said something like on here.gpu, that would say allocate this array in the GPU's memory, and then any computation within this scope would also be done by the GPU. That's sort of what we're trying to build towards. And here's a very simple computation. Let's say I say on the GPU, allocate this array. It's obviously a really small one, just to fit on the slide. And then do a parallel loop over the array, just incrementing by 5 or something like that, right? This is the kind of code we'd like to have people write and have run on a GPU. 6 months ago, this is where we were. We had our first GPU codes running on Chapel, but to be honest, they looked pretty heroic. So you see some pragmas in here. There's some features that aren't really meant to be user-facing. There's a lot of interoperability we're still relying on. But happily, in the release we just did about a month ago, we got our code like this, basically compiling and running on the GPU. And the only real difference here between this and what I told you we were building is that rather than here.gpu, I've written here.getChild1. And the reason for that is that the locale model we're using today has child 0 representing the CPU and child 1 representing the GPU. So this is just kind of a not very pretty way of referring to the GPU. But apart from that, it's essentially what I told you we wanted to build. This is not the ultimate locale model. So we're looking at various ways of modeling compute nodes with GPUs and CPUs and multiple NUMA domains. And so this slide just shows some of the different block diagrams that we're considering there. One of the things we were really striving for and accomplished in this release cycle that, again, just finished up about a month ago, was to take our version of Stream Triad and run that on a GPU. And if you look back at the beginning of my talk, I had a Stream Triad block, and this is pretty similar to it, a little bit different, but still very high-level recognizable Chapel code, again, prefixed by that on clause to tell it to run on the GPU. And with this, we're getting decent performance when the problem size gets large enough. Obviously, at smaller problem sizes, we've got some amortization efforts, overheads that we need to overcome just in terms of what it takes to launch our kernels today. So again, this is very early days for this. I have no reason to believe we won't close this gap, but just to give you a snapshot of where this lives today. We've got a bunch of next steps, but in the interest of time, why don't I just move on? These slides will all be available afterwards, and you can look through these on your own time. Again, early days, there's still plenty of to do here. So with that, let me wrap up to leave some time for questions. This slide's got some pointers to Chapel resources. Again, don't feel like you have to scribble these down. I'll make these slides available. Got our homepage, social media feeds on Twitter, Facebook, and YouTube, and then a bunch of places where we interact with the community, answer questions, talk to users, things like that. On this slide, I've got a bunch of suggested things to read or talks to watch if you want to learn more about Chapel or Arcuda or Champs. On this slide, I just want to mention briefly that we're hiring. We're currently a team that's 18.5 full-time people working on Chapel. That's our full-time job all the time. We're planning on adding 1 or 2 more people in the next few months. And so if you're interested in that, check out this link. And if you're still in the middle of your studies, I'll mention that we also host summer interns and take Google Summer of Code students as other ways to work with the team. So let me just summarize. Chapel is being used today for productive parallel programming at scale. I've shown you a couple of examples today where users have reaped its productivity benefits in applications ranging from 16,000 to 48,000 lines. I've showed you these aggregators we've been working on recently. And for gather, scatter, or sort patterns like we've seen in Arcuda, this is a really key pattern for us to optimize and support. And then again, Chapel GPU support is still in its very early days, arguably, but it's improving by leaps and bounds. And I hope you saw that from the step we took from last release to this release in terms of how clean the code looked. And so ultimately, the goal here is to have users like the Champs team be able to leverage GPUs more productively in their code. And with that, I think I've got about 4 minutes for questions, if there are any.
Great, thanks for the talk, Brad. We've got one question already in the chat, which I'll read. It's from Phil Miller. He asked, did automatic introduction of aggregation apply to other existing applications with noticeable performance impact? So you mentioned that recent paper.
Right. That's a really good question. So this is an optimization that, to be honest, we have not turned on by default yet. And the reason for that is that the memory overheads of the aggregators are pretty high. And we're not certain yet that this is something that should just sort of happen without the user opting into it. So we haven't tried it across a lot of applications. But what I will say is with Arcuda, again, I mentioned that this pattern is beneficial in a lot of cases. There are currently something like 60-ish loops that manually apply aggregators using the library that I showed earlier. And I think that the aggregation library currently catches between 40 and 50 of those automatically. So that's good, but obviously there's still cases that we can't automatically optimize where the ability for a user to do it is beneficial. And then in terms of performance, typically the change between using the manual aggregators and the automatic ones we haven't looked at, they're basically neck and neck because they're doing the same thing under the covers. And so the other cases would be cases where users had not been using the aggregators and suddenly they use the flag and get a benefit. And again, because the flag's off by default, I don't happen to know of such cases off the top of my head. And it's still early days for that optimization. So we need to talk to users more and get them trying it out to see what they see from that. But yeah, thanks for that question.
I had another kind of similar question, which is, how have the production applications fed back into the design of Chapel? So with Arcuda, you have this aggregators concept, but are there other examples of applications feeding back into the design of Chapel?
So there definitely are, and I'm trying to think if I can come up with a really great example off the top of my head. I'll say that, for those who look at a Chapel timeline, they're sometimes very surprised at how long we've been around. So we've been working on this project for, it's getting close to 2 decades since like the inception point of the project, although it took us a long time to figure out what we were building and how we were going to build it. And the reason for that is because it's a very large and aggressive language, as hopefully you've seen today. And for most of its history, if people asked us, should we be writing applications in Chapel, we would say, well, probably not yet. But what we'd like you to do is try out some of your key idioms and give us feedback. So all throughout the course of the project, we've gotten tons of feedback. And most of the great stuff in the language didn't come from those of us who started the language. It's things that we were suggested by users or sort of came up by looking at their codes or things like that. And as I was killing for time, I'm trying to think. So we talk to the Arcuda users and the Champs users all the time and other users. And we're always getting feedback from them. And so I guess I'm just going to say, yes, we definitely improved the language a lot through user feedback. And I'm not coming up with a super great example, although, as you said, aggregators did come out of the Arcuda work originally. And that's a good example of one, I guess.
Okay, thanks. If anyone else has a question, we've got time for another. You can go ahead and unmute yourself.
I see Sanjay's got his hand up.
Question?
Oh, go ahead. I couldn't tell who that was.
Go ahead, Sanjay.
Sanjay, you're on mute.
Yep, sorry about that. Can you hear me now?
Yes.
Okay, so one quick question about the aggregators. Did you consider pipelining? But I have a bigger philosophical question too. By pipelining, I mean aggregate in bundles. But the bigger philosophical question, and I wish we had these talks tomorrow when after Alex Icon's talk. But listening to Legate, NumPy, and generally these Python interpreter type ideas, I wonder what is your impression of this idea, whether the compiled language versus something that uses the interpreter to do some symbolic execution, to do some compiler-like stuff, so that you stay within Python-like world, and you get the benefits of some compilations. So I don't know if they are truly interpreter languages, but they're kind of in between there. What's your feeling for, it's like, it's of course a heavy compiler infrastructure that you're building there. If you just can rely on some Python, then why not? So how do you respond to that?
Yeah, so something we talked about from the earliest days of Chapel was wanting to have both a compiled and an interpreted mode, because that ability to, there wasn't Jupyter back then, but MATLAB was sort of what everyone wanted on their HPC system, and that ability to do things interactively. And unfortunately, early on in the project, we had to drop, we sort of started into that effort and we had to drop it because we're just too small of a team to do both a compiler and an interpreter. But as you say, like, let's say Chapel continues to gain in popularity. Wouldn't it be great if I could just interactively program in Chapel rather than having to go through Python if I wasn't necessarily a Python programmer, or I didn't want to deal with dynamic typing or things like that? And so that's something, we actually have a new initiative we just started in the last 6 months, didn't make it into today's talk, to basically go back and revamp our compilers significantly. And one of the things we're doing there is supporting more of like incremental compilation and compilation of little snippets of code, so that it could be integrated into like an interpreter or a debugger or things like that in order to evaluate Chapel code and incorporate it into a running program dynamically. So that's another effort that's still very much in its early days. We sort of envision this as being a 3-year effort, but the goal of that will be come out with a compiler that can do both sort of traditional static compilation like we do today, but also more of an interactive interpreted mode, if you will. And we hear from users a lot that that's something they would really value. And in fact, they'd like to see Chapel in Jupyter, and you can use Chapel in Jupyter today if you do it just right, but like C, it's kind of clunky because it's not an interpreted language. So that's where we're going with that. You asked about pipelining. I'd be happy to talk to that, but I realize we're a couple minutes over, so I'm also happy to turn over the next speaker if we'd like to do that.
Yeah.
Okay. Yeah. Thanks again, Brad.
Okay. And we can take that question up at the break if there's still interest.
Yeah. With that, we'll transition to our next talk by Justin Szaday. Justin, if you could share your screen. Okay, you can see it now. So Justin is a PhD candidate in the Parallel Programming Lab at the University of Illinois. And today he'll be talking about recent advances in Charm++ based languages. Go ahead, Justin.
Thank you, Sam, for the introduction. Can you hear me all right?
Yep.
Okay, great. So as Sam said, I'll be talking about some of my work on Charm-based languages in the past year. And this talk is sort of a follow-up to my talk from last year with the same title. So I'll be starting out by giving some context for my work and then talk about our approach, go through some of the enhancements that we're offering with our platform and some preliminary results and our plans for future work, and then talk about some conclusions. So the first question is why domain-specific languages? Well, as hardware complexity continues to rise, it poses challenges in programming for heterogeneous systems. We need people to train people on how to use like GPUs and other technologies like FPGAs, and they may need to use multiple technologies to make use of them within one program. And so that can start to get pretty complicated. And then there's also the problem of updating specialized software and bringing it forward to new hardware, and then choosing the best hardware configuration for a given program. And in response to these challenges, there have been various responses. Some are like building better auto-tuners or tools that'll go through the problem space and try all the different permutations and pick a good one. And then there's also the approach of just simply lifting the abstraction level away from these hardware complexities. And towards this end, languages better suited for HPC than C, C++, and Fortran can help a lot. And domain-specific languages can help address these needs. DSLs integrate domain knowledge to enhance productivity. They offer direct access to common domain abstractions that domain experts will be familiar with, and efficiency, because they tend to make the search space smaller so that like an auto-tuner can more efficiently navigate it and utilize domain knowledge to do so. Research in HPC continues, and it supports distributed domain-specific languages like PyOP2, grid tools, and OpenPME, each of their specializations shown on the right. However, on the whole, at least relative to DSLs that run on a single node, DSLs that scale beyond a single node are pretty rare. This may be because scalable DSLs require additional considerations like how to partition your data, how to communicate it between nodes, and how to synchronize optimizations. But DSL frameworks can help to overcome these barriers. They offer common abstractions for these different operations and that domain-specific language authors can utilize. And some of the domain-specific language frameworks that are out there span various abstraction levels, offering just low-level parallelism abstractions like fork join and messaging, or mid to high-level parallel abstractions like channels and tasks. And then furthermore, there are domain-specific language frameworks like Quark and Dawn, frameworks for lattice and grid domains problems and weather and climate applications, respectively. In terms of how DSLs are built, well, not many of them are built with these frameworks still on the whole. Most still use low-level compiler and communication tools like MPI or LLVM. And so that means that the language authors have to do more work. Some are built on existing libraries, like OpenPME is built on OpenFPM. And there are a few of them that incorporate runtime adaptivity, load balancing in the Charm++ sense, like OpenABL and Marlin, one for agent-based simulations and the other for reinforcement learning, respectively. Our work with Charm++ in some senses blends the latter two approaches, utilizing Charm++ to give us runtime adaptivity. So that's one of the major things that Charm++ can offer DSLs, is that they have that it has intrinsic over-decomposition and runtime adaptivity, and its flexible local view of control and data can easily capture other local views of global, Its flexible local view of control and data can easily capture other views of control and data, like global view of control and data in the PGAS sense. Noting these benefits, there have been various past Charm-based works that have built parallel abstractions, like from other domains like trees, futures, PGAS structures, and some DSLs that have been built using Charm. However, these past DSL efforts did not leverage a common framework, which meant that their development processes were pretty repetitive and they made them harder to maintain. So if we wanted to use a DSL framework to build DSLs based on Charm++, we'd find that migratable objects require rich OOP support to reach their full potential. However, most DSL frameworks out there don't consider OOP concepts at all and just leave them as exercises for the DSL author. That said, performance will suffer without first-class support for these concepts. Consider programming in an object-oriented style in C versus in C++. A C++ compiler, being aware of OOP concepts, will be able to optimize a lot of the things that a C compiler wouldn't be able to, like virtual method calls. Which brings me to my next point, that embedding migratable objects in C++, we found that that has various shortcomings, particularly like the standards are lacking in some areas that would be helpful for our work, like if you wanted to register functions in an automated way, it's pretty difficult. There are some workarounds that you can do for that, but then you start to move out of the territory covered by the standards. And one other challenge is that the STL containers force copying in some cases. So like the STD vector container will take ownership of a pointer internally, but you can't replace that pointer with something else if you wanted to, like a pointer within a message buffer that arrived. All of this sort of leads to syntactic constraints causing verbosity and other concerns. And on the other side of things, if we wanted to embed migrative objects in interpreted or JIT languages, there are performance implications, obviously, but those languages have gotten better for some domains. That said, we were interested in trying to pursue something more general. So enter AIR, our new framework. It's a compiler framework for building DSLs based on Charm++ that has an extensible compiler which supports DSL analysis and transformation passes, and rich support for OOP and Charm concepts. Like it'll handle this automatic registration and serialization of user-defined tags. And it has a C++ backend with runtime and compiler level optimizations for communication and enhanced support for performance critical abstractions. Our goals are broadly to build something that is general purpose and usable for many domains. So to prove and drive the generality of AIR, our compiler framework, we've built a Scala-inspired general purpose language with it and embedded some DSLs within it like Charisma, which is a language for data-independent data flows. And I talked about that last year and won't get too much into it this year. Beyond this, we've explored elevating the visibility of internal mechanisms when they are useful for constructing other parallel abstractions. So some things buried deep within the Charm++ runtime system, I found that if we bring them to the surface, we can utilize them for multiple other parallel abstractions. And one other concern that we've wanted to address is if something buried within the system has an avoidable performance impact, we'd like to bring that up so that users can be aware of it. Another thing that we've tried to explore is facilitating optimizations through stronger guarantees, like discouraging user-level locks and regulating data sharing. And then whenever possible, we try to extend the underlying model, that's to say Charm++, to minimize semantic gaps between it and the languages that we're building on top of it. So one example of some of the enhancements that we can offer with the compiler pertains to eliminating tedium. So if you wanted to write a templated entry method in Charm++, you would end up having to explicitly specialize all of the different versions of it. So here we have a printer char that has a print method that's templated and accepts one template argument, and we specialize it with a string and a double. And in our Charm interface file, we actually have to declare it like this. But with a compiler, you can just say, have a templated entry method, and then it'll be able to generate all of this registration code for you. Another area where we've offered optimizations is with deserialization, because in HPC machines, copying can be a huge waste of time. The first of the optimization techniques that we've developed is called identity-aware or finer graph packing. And this allows us to effortlessly handle recurrent relationships like doubly linked graphs. What it does is every time it encounters a unique object, it records that object using the object's pointer, and then uses back references to refer to that when it encounters it again. This means that if a data structure is recurrent and it has like references to its parent inside of it, or maybe it's not as nicely structured as that, when it hits an object again, it'll just use a back reference and it won't go into an infinite loop like might happen with a more naive framework. The other type of optimization that we offer is global pointer to offset optimizations. In this scheme, we deserialize plain old data types. So that would be any thing that's not a class with virtual methods as pointers to an offset within a message buffer. So when we do that, we retain ownership of the message with a reference counted pointer. And then that lets us keep the message alive until it's no longer necessary. And we can use that for other optimizations in a moment. But one of the big takeaways is that we can eliminate the overheads of encapsulation. On the right, I just have a little struct declared with an array inside of it. And if you were to do this in Charm++ compared to just sending the array directly, you would incur an additional copy because Charm++ can only apply pointer to offset optimizations through its compiler, the CharmXI interface compiler. The last optimization that I'm going to talk about builds on the pointer to offset optimizations, and it's in-place message optimizations. So if we've retained a message that we received via pointer to offset, we can edit that in place and then resend it if we no longer use it. And this will let us avoid repacking. Error uses a control flow analysis pass to find these repacking opportunities. So what does a repacking opportunity look like? Well, it occurs when you receive a value via pointer to offset, then send it to an entry method with a compatible message structure, and then it's unused again after the send. So here we have a block A and block B that we receive from the entry method input A, and then we send that again to the same input A and input B methods later of another char. And so we can retain the ownership of these message buffers that we receive, and then just send them later on and avoid repacking. And in practice, this can give us really big speedups, especially as our tile size gets bigger. This little example was drawn from Cannon's matrix multiply. And when we scale that up, we can see that eventually we start to have a bigger than 2x speed up for avoiding the copies. And here it's worth noting that this top line matches the standard charm, and this is error with disabling these in-place optimizations. The next type of enhancement that I'll talk about is in comparison to SDAG. SDAG, or structured dagger, is Charm++'s notation for representing parallel control flow. These are the dependencies between messages arriving and local control flow. And you may use this to direct the progress through phases of computation. So in this example, which is mimicking like a Jacobi, you may start an iteration by sending out values to your neighbors. Then for each of your neighbors, you might wait for an update from them. And then after all of those values arrive, you might do some computation with them. And then depending on whether or not it's the last iteration, you might do something else. In AIR, we've implemented mailboxes to enable air laying like selective receives. These are syntax constructs that blend pattern matching and message processing. So we can have rich predicates for picking which methods just to select. In SDAG, typically you can only use one CMK refnum to match a value, and usually that's a 16-bit value. So if you wanted to match two integers for a call, you would have to join those together, and then you would end up having two 8-bit integers that only go from 0 to 255. Whereas with pattern matching, you can have unconstrained matches on a method. So on the right, we have the same code written in the language built on AIR, and we we filter the receive by two predicates, checking the first argument to see whether it's equal to I, and then checking the second argument and seeing whether it's equal to J, and then this is unconstrained. One other interesting thing that we can do is, since this is implementing full pattern matching, we can use classes and the types of classes to match as well at runtime. So if we have a trait and we call it response, and then we implement that trait two ways with a ping and a pong class, then later on we can declare a mailbox that takes responses and filter just depending on whether or not we want pings or pongs for a particular clause within our await block. This brings us to some of the other features of mailboxes that we've implemented. These are to mimic features within SDAG that Erlang doesn't necessarily have, like compound clauses, where you need to receive a message from both foo and bar to continue. And then the await all construct, where you need to receive foo, and then and bar and baz. Whereas in Erlang, you can only write it as an await any in our language, where the first one of those methods that it receives a value for, it'll just continue the whole past that construct afterwards, and it won't look for the rest of them. Here we need to receive foo bar and then baz. With this await all construct, we can do overlapped execution. So only the ordering of bar after baz is enforced in this example, and foo can execute between or after them, depending on how the program suspends. And another area of enhancements is pertaining to sections, which facilitate efficient operations over subsets of collectives. So if you have a char array and you wanted to operate on just a portion of it, you would use a section. The current Charm++ API is constrained in some ways. It requires explicit centralized creation for each of these sections and user-managed cookies to maintain correctness. And work is underway to improve the sections in Charm++, copying innovations from Charm for Pi, like the elimination of cookies and switching to a distributed section-based creation scheme. But this is an area where compiler support can help too. So in Charm++, you would have something like this at the top with the current syntax, where you have to get your section info and then put it into a cookie. And then you have to use a contribute call where you specify the size of the data and the type of reduction that you're doing, and a callback at the end. And both of these are RTS registered functions, whereas we're aiming for something more like this, where we eliminate the section registration, which isn't shown here, and just create the sections at the call site so that the range of chars that you're operating on, in this case, all the chars with indexes 0 to n with stepping by 2, is visible at the call site. And then we also want to eliminate the requirement for RTS registered functions and just be able to use statically typed callbacks and combiner functions. So here we're saying contribute an integer and then add it with all of the integers from the other chars and then call the callback when it's done. And since we're eliminating the requirements of having registered functions, we would like to be able to use lambda functions for these parameters. So just being able to say ij goes to I plus 1 or I plus j, and then saying when the final result I goes to print line, something along those lines. So some of the other features that we're working on is to add rich support for generic types, supporting parameter packs and tuple manipulation, Swift-like where clauses to enforce constraints on your generics. In terms of C++, they would be corresponding to std enable if or requires from C++ 20. We also have operator overloading like Scala, so we can use operator objects as functors, and then any arbitrary identifier can be an infix operator, like you can define a range by saying 1 to 10, or 1 to n in this case. And then we also have pattern matching, which I mentioned before. And one thing that we can do with that as well is we have user-defined extractor methods. So if you wanted to match an optional value with a value, you would say sum x, or in the case of none, you would say case none. And users can write their own extractor methods like sum and none in this case. We've woven these features together to form a rich STL for languages that target error, and we also include some parallel abstractions out of the box, like distributed hash tables and tuple spaces, channels, and futures, all of which are transparently granted Charm++'s benefits of over-decomposition and migratability. And using these features, we've written various mini apps like Jacobi's method in 2D and Cannon's matrix multiply. Performance typically matches or exceeds Charm++, with gains usually in the 5 to 20% range, unless the larger optimizations are mentioned that I mentioned before are involved, like in the case of Cannon's matrix multiply. where we can use in-place optimizations to get bigger gains. Currently, we're dealing with complexities in our message delivery pipeline that preclude larger gains. And these changes are required to facilitate mailboxes, lightweight sections, and et cetera. Our recent focus has been on microbenchmarking to try and eliminate these overheads. And we've successfully eliminated the overheads for the round trip ping pong time. And we're working to get our bandwidth to match Charm++. So aside from correcting the issues mentioned, like the limitation, one of them are the limitations of the C++ backend. Currently, our support for generating code for generic types is incomplete. If you have types that are in this language, we have the notion of value and reference types like in Swift. So one is reference counted normally, or at least owned, and it's heap allocated, and the other is stack allocated. And if you do specializations of mixed kind of types, so if you have a class that you specialize with values and with references, it may break down at the compiler level. And that's just because of limitations in targeting C++. And we hope to fix those soon. And then correcting the micro-benchmark performance. Aside from those corrections, we have many ideas for future work with these tools. We want to write more mini apps like LeanMD, Barnes Hut, HPCCG, etc., and integrate more domain-specific languages from Charm's back catalog like DivCon and MSA. DivCon is particularly noteworthy because it's a divide and conquer language that uses tasks to represent those algorithms. And successfully integrating DivCon into our suite of languages would establish a lot of infrastructure for other tasking-based languages. We would like to try and expose a textual representation for AIR as well, like an XML-based AST, a la Omni's Xcode XML, which is the language or the compiler that powers the scalable MP language. And we would like to ensure that the code that we're generating is robustly migratable. There are some areas where it's not quite there yet, and we're working to solve those issues as well. And finally, we would like to at least explore tentatively providing facilities for hardware accelerators. So in conclusion, I've introduced AIR, which is a compiler framework to build DSLs based on Charm++, and talked about some of the optimizations for message packing that we offer and the enhanced message processing facilities and lightweight sections. We plan to publish soon, and we'll have more to say then. But in the meantime, please feel free to reach out if you're interested.
Okay, thanks, Justin. We don't have any questions in the chat yet, but people can raise their hands if they have questions. It's really interesting to see how compiler support can not only make the language easier to use, but also improve the performance in certain aspects. Brad Chamberlain has a question. Go ahead and unmute yourself.
Yeah, my question is a very basic one, but it's one that I think you'll find if you haven't already, language creators get asked all the time. I'm just curious, have you had a chance to sort of shop the language past prospective users or current Charm++ users to get feedback or thoughts, or like is it resonating well with people, or the things about they'd like to change? Or has it kind of been too early, or maybe not part of your academic plan to do that kind of thing?
I'd like to shop for feedback more, but I haven't gotten much yet.
Okay, totally fair. Just curious.
Okay, any other questions? Nils, go ahead.
Yeah, so this looks really nice. I'm looking forward to seeing what sort of the maybe not final result, but the first sort of published result will look like. For some of these mini apps, like the Jacobi one comes to mind. Often it's shown with a fixed number of iterations, but sort of in realistic science applications, you're solving, say, Poisson's equation, doing an elliptic solve. you're actually measuring some error criterion as you go, and that determines the when you stop. I guess this is less of a question, maybe more of a request or like a thought or comment. But have you thought about, looked at, or plan to try to get some inspiration from maybe more of the community, if there's some way to take some of these like NAMD or something, you know, like these huge applications and pare them down into, this is a minimal example, but it's large enough that it accurately reflects the types of problems we're trying to solve. Because I know when we were shopping around sort of for, well, which task-based parallel runtime systems exist, this was a big challenge, was sort of like, oh, well, this works well for NAMD, but is it going to work well for relativistic astrophysics and this kind of a thing? I don't know if you've thought about this at all.
Yeah, it would definitely be great to get some feedback like that. And I think that once the compiler is a little bit better established, I would like to try and chop around to have people write some basic examples along those lines.
Okay, cool. Yeah, definitely reach out. I'd be happy to talk about that. That sounds really cool.
Sounds good. Thank you.
Thanks.
Okay. If there are any other questions, if not, I think we probably want to do about a 9-minute break and come back at 4:10, if that sounds good.
Can I add just one couple sentences? The particular question that Nils asked, well, one of the things that Justin answered already, he's looking at various mini apps, and once they are coded, he will probably get answer those questions. In particular, in MD-like application that's small enough, well, that's DynMD. And so he's going to do a bunch of mini apps like that. And I don't know your particular question about convergence, but that's easy enough that the same benchmark will do well for that. Just an additional reduction, but the reduction is already part of the current benchmark.
Towards that end, we just need to be able to load more realistic data into the current benchmark, and then it'll converge.
And to answer Brad's question, look at this. Me and Justin have been asking our own research group to please experiment. And by the way, it all has complete functionality equivalent to ChaN++ and plus more of these DSLs, right? But everyone is just so busy doing their own things with their own existing ChaN++ or whatever that we haven't gotten that feedback within my group. And so it's a tough challenge to get feedback like that. So it'll be great to have a broader community provide feedback, and it will be great for our group members to do some more.
Yeah, I think that's always a challenge, but and I totally understand it. So no critique implied there, but yeah, I was just kind of curious what you'd heard so far. Yeah, if we from time to time, there's been talk about we in the HPC community should really start a national center for like programming model evaluation and study and comparison and stuff. And every time I hear a glimmer of that, I'm like, oh, that would be great. Like we could really use that as a community. But unfortunately, that has not ever come to pass. So maybe someday before we're all retired.
Sanjay, you're muted. Okay. With that, I think we'll go to break then. And the next session will start up at 4:10. So a quick 7-minute break. And then that'll be the last session of the day.
All right, welcome back everyone. We will now start our next session on plasma physics and astrophysics. And first up, we have Esteban Meneses from the National High Technology Center. He will be speaking on adaptive plasma physics simulations dealing with load imbalance using ChaNGa++. So Esteban, whenever you're ready, you can get started.
Okay, can you hear me well, Aditya?
Yeah.
Okay, slides.
Yes, I can see the slides.
Okay. Awesome, thank you so much. Well, I gotta say I was a PhD student in Sanjay's group, and I graduated in 2013. That was 8 years ago. So it's good to be here and see some familiar faces and some old friends. And I'm very happy to share with you some ideas on the work we have been doing with the plasma physicists here in Costa Rica, and also show you this experiment that my student Diego Jimenez did last year in collaboration with Ivan Vargas, which is our colleague in the physics department. So I'd like to start saying that Costa Rica as a country in 2020, last year, produced 99.8% of electricity using renewable sources. And to give you a breakdown of those sources, I want to show you this picture of Arena Lake. You see the lake, which actually is an artificial lake. It's part of a dam that was built a while ago, and that particular lake feeds 3 hydroelectric plants in that region alone. And electric plants represent 72% of the total electricity production in the country. And you also see the volcano in the back. It's one volcano in a chain of 4 or 5 volcanoes in that particular part of Costa Rica. And the largest geothermal project is in one of those volcanoes, and geothermal energy accounts for 15% of the total electricity produced. Something that you don't see in the picture, but actually is quite common to see, the wind turbines that populate the whole region, and wind energy represents 12%, and the other 1% comes from solar and biomass energy. So to keep up with this ambition of producing clean energy as a country, there are several challenges we must solve. One is the growing concerns of hydroelectric plants and the environmental impact that they have. And the other is the growing interest in electric cars and the demand that will increase. So while there are some efforts in improving the wind and solar installations, there's also some research directions that we are taking. One is fusion energy. So they recently opened this facility on campus for the plasma physics laboratory for fusion energy and its applications, and it will host, or it actually, several projects on plasma physics. So we've been working with those colleagues for a few years now. One of the projects is about building fusion reactors using the same type of energy fuels that the sun, that is hydrogen atoms collide with each other, and in the fusion process releasing some heat that will be converted into electricity. And there are some other applications as well. So here's an outline of the talk. I'll give you a little bit of background on the actual project, and then we will describe, I will describe the experiment we run with ChaNGa++, and I'll show you some results I'll leave some discussion points for the end. Here's a picture of what is called a Accelerator, a plasma reactor that was built by our colleagues at the physics department. It's called the Accelerator Costa Rica 1, SCR1, and it uses magnetic confinement for producing the fusion. What you see is a torus, like a donut, and the black stripes that you see around the chamber are actually the coils. And the coils are quite important because they are a crucial factor in actually achieving confinement and producing fusion. So we'll see that aspect later in the presentation. But this is a real picture of this reactor, which is an experimental device, not meant for real energy production, but for research purposes in measuring some physics variables and understanding the design of those devices. So there is a code associated with that device that uses the Biot-Savart solver, and the code it's called BS Ultra, meant for Biot-Savart solver for computing and tracing magnetic field lines. And BS Ultra is just one part of the whole pipeline the physicists use to run the simulations. And we've been working with that particular software in improving it, parallelizing the code and so on, and producing, of course, those visualizations. So what you see on the top left corner is a CAD image of the device itself, and the bottom figure shows you the coils and the arrangement of those coils, and also within those coils, you see the plasma being confined, and the colors represent the energy fields. On your right, you see something that is quite important for the physicists, which is the actual volume of the confined plasma. So understanding that volume or the geometry is fundamental for the amount of energy that will be produced by the device. This method, the Biot-Savart, uses particles. So that's why you see on the bottom right corner a figure with the particles in the simulation. So the code itself for the simulations follows a field line tracing trace method, not a super sophisticated numerical method, but one that physicists find useful for the type of experiments that they're running and the validation they're doing. Recently, there has been an interest in this type of methods for vector research, and so they plan to still use that code in addition to other codes that the community has developed. BS Ultra is written in C language, and it has MPI, an OpenMP, and vectorization, so the traditional recipe for building parallel HPC software. And again, one of the major goals of this software is to evaluate the design of the coil configuration and how it will affect confinement. So you see a couple of pictures at the bottom. The left one is the coil, the coils used for the SCR1, and you see some of the particles going around the torus in one simulation. And aside from some synchronization points, tracing each particle, the trajectory of each particle is mostly independent. So this is, heavily compute-bound code, and also kind of embarrassingly parallel for most of the execution. Another important figure for physicists is what appears on the bottom right corner, which is called a Poincaré plot, and it's basically a cut. That's a transversal cut of the chamber, And what you're seeing is concentric ellipses representing the different energy fields. And on top of those energy fields, particles travel around the device. And the form and the position of those ellipses are important for understanding some of the effects of confinement. And studying these types of results is what physicists care about in the simulations. Of course, running the BS Ultra is just, again, one part of the whole process they do in analyzing data from the simulation. So what happens with the BS Ultra is that I'm going to show you an example here. For some scenarios, we found some load imbalance. So here's 63,000 particles using 16 ranks. And what we see is some divergence of particles. And divergence means here one particle that is not confined. So what happens with a particle that diverges is that its trajectory is not traced anymore. So the more particles diverge, the less computation a particular rank has to do. So in this particular case, what we found was a load imbalance shown in the plot on the right. So we sorted the ranks according to the computation time, and you see rank 8 having more than twice as much work as the later rank 11. So we computed the load imbalance using the traditional formula, and we found 75% of load imbalance. And using that, we decided we could try CHARM. And in one effort last year, we started porting the code from the MPI plus X implementation to pure CHARM++. And I'm going to talk about a little bit on the porting process and how we mapped one structure from one version to the other. But basically, every rank was transformed into an SMP node, and OpenMP threads were mapped to chars. And we presented a paper recently on per conference with the results. So if you want to see more details on that effort, you can look at the paper. So what I'm going to do is, to avoid describing all the CHARM++ infrastructure that we used, I think most of you will be familiar with that, with those terms and with those concepts. So I'm going to concentrate on the results. We use 2 KNL systems. We have on site our own cluster. It's called Cabré, and we use that mostly for debugging and performance analysis. But for the skin runs, we used Theta Supercomputer at Argonne National Lab. And we used the SMP build of CHARM. And the particular configuration that we chose was one communication thread per SMP process, and 62 PEs plus 1 COM per node. We leave one thread out, as recommended by some of the best practices in CHARM SMP that we found in the literature and different presentations. So in the first experiment that we run was actually to understand the CHARM++ overhead. And so we call this the ground zero comparison, which was basically running the 2 versions, the MPI plus X in CHARM++, and just understanding what was the impact of adding CHARM++. So for this experiment, we used a non-divergent particle set that we knew wouldn't produce any load imbalance. So we use 4 KNL nodes in 10,000 iterations. And again, there's no load balancing. So the results are in this table, and you see 3 versions of the code: the MPI plus X static. That means we're not using the dynamic scheduler of OpenMP. And so we have an average time of 323 seconds, and that's the average over more than 10 executions. And you have the standard deviation and the coefficient of variation. And then we use the MPI plus X dynamic, which has a comparable result, and the CHARM++ SMP. So we found the overhead of CHARM++ was around 7.9%. And we thought it was still profitable to keep using the load balancing features of CHARM, as the load imbalance that we measured initially was 75%. And again, it was 75% at some scale, but that percentage may change if you increase the number of nodes. Then we implemented the load balancing in the CHARM++ version and used one load or several load balancers, but we ended up just using the greedy load balancer. It was enough for our comparison. So in this case, we used 16 nodes and 63,000 particles and a virtualization ratio of 8 to 1. We actually run several different virtualization ratios that I'll show later. But this one was the one that we chose for the final experiments. In this case, we run 20K iterations, and we decided to just call the load balancer in the middle of those 20K iterations. So 10K iterations will be run without any load balancing, and after that, we will see the load balancing effect. And so what you see in the plot at the bottom are 4 versions of the code. So the CHARM++ without any load balancing. And you see 2 different bars. The first bar for the first 10K and the second bar for the second 10K iterations. So on the second set, you see the CHARM++ with load balancing, and you see the significant difference of using the load balancer. The third set of bars is the OpenMPI plus OpenMP static, which is basically roughly the same performance between the 2 sets of iterations. And finally, you see the OpenMP, the MPI plus OpenMP dynamic version, which actually improves a little bit on performance. So if you compare the best CHARM++ version with the best MPI plus, you have a speed up of 1.64 by using CHARM. So then we kept looking into other details of CHARM++. Here's a picture of projections showing the performance of load imbalance. The not using load balance and using the load balancer. Again, we used the greedy load balancing strategy. We tried other load balancing strategies, but greedy was enough for our purposes. And that moved the average CPU usage between the 2 versions from 45 to 80%. And what was cool is something that we already knew, which was the CHARM++ ability to deal with internode load imbalance, as opposed to MPI plus OpenMP dynamic that only solves the intra-node imbalance. Here's some comparison of the different virtualization ratios. We tried different values for that from 2 to 64. And here is a comparison of a run with 20K iterations, again, running the first 10K without any load balancing call, and then the second 10K iterations using the load balancer. And so you can see the comparison after maybe 16, a visualization ratio of 16, the curve flattens. So yeah, we decided to not use more than 16 for the visualization ratio, but in the end, we chose 8, which was had comparable results. Here's again another projections plot on the visualization ratio, comparing to a visualization ratio of 2 with a visualization ratio of 1. What happens is that we were not able to completely eliminate the last tail of the imbalance. So we could improve it by increasing the visualization ratio, because now charts were smaller and we can manage to have a better distribution of work, but we were not able to completely balance the load. At any rate, results were looking good, so we were satisfied by having those results so far. And another experiment that we run with the ChaNGa version was try to see if we could repeat the good scaling of MPI plus OpenMP. So we run the simulations from 16 to 256 nodes on Theta supercomputer, and we use different problem sizes. And as you can see in the plot at the bottom, and that's weak scaling results. So the implementation, the ChaNGa implementation scales well. Okay, and here we were using again an 8-to-1 virtualization ratio. All right, so finally we also implemented the checkpoint abilities, and we measure some checkpoint time for different configurations of the simulation. So you can see the checkpoint time having kind of a large variation with this number of repetitions, which was again higher than 10. So probably the file system was getting involved, but that requires further exploration on our side. But the checkpoint, it came pretty handy for things we want to do in the future. So as a pop, porting to Charm gave us the opportunity to understand better how to migrate these codes. So MPI ranks are mapped to node processes in the SMP build. So we partition the data into charms, and those are, managed by the runtime system in the different SMP worker threads. So choosing a good visualization was important. And then ChaNGa load balancer was able to deal with this imbalance across nodes. And again, several parameters must be tuned. The frequency, the algorithm was not that important, but also the virtualization ratio. So in comparing SMP with the non-SMP, we found that the SMP version of Charm had some variability, which was non-negligible in some experiments, and we're still trying to figure out exactly what are the conditions under which we have this variability. But it's an effect we've seen in other projects, particularly with the epidemic simulations. The non-SMP is more stable in performance, but doesn't scale that well. So we ended up using the SMP version. And even when you have to sacrifice one thread, and that can affect some compute intensive applications. Okay, so a very cool thing that we did was to use the ChaNGa version to retrofit some of the features into the original MPI plus X version. And I'm talking here about code refactoring and other changes. And we ended up with a better version of the original MPI plus X implementation. And here are some scaling experiments going up to 1 million particles on theta and running from 64 nodes all the way to 1,000 nodes. And you can see the results. The scaling is quite good, and the efficiency goes down to 85% at the high end. And that allows us to produce more refined visualizations. You're seeing at the bottom left a frontal view of the device, and in the middle you see the particles of the plasma volume being confined, and on the right you see another Poincaré plot, but this time using much more or having much more details on the representation. Another cool thing that we were able to do was to create a new computer graphics model for creating the same texture that you will see in real plasma pictures, or trying to reproduce that image. So we developed a computer graphics model with different variables that we can tune and produce a visualization like the one at the bottom, trying to reproduce the same features that we see in real pictures. So we again presented this all our work at ParaTreeT this year. And right now we are in a collaboration with a couple of scientists at the Max Planck Computer University in Germany. And the project is advancing physics computer simulations with the latest high performance computing techniques. And we are concentrating on two things: exploring task parallelism, StarPU, which is a framework that they like, and also ChaNGa, and also exploring performance portability libraries like Cocos and Raja. And we are exploring this code that they have, JAMPIC, and that uses AMREX library. And right now we are trying to port that library onto AMPI. And also want to mention that I've been teaching a class on adaptive MPI, and this is a picture from earlier this year at the Santos Dumont Supercomputer Summer School in Brazil. And this is hosted by the LNCC, the National Laboratory on Computational Science, I guess. And so in that session, more than 100 people connected. It was a short session, maybe 3 hours session of AMPI, but it was really fun. Okay, so I want to thank my funding sources for this presentation, and I'll leave you with these remarks. Thank you so much.
Thank you, Esteban. Does anyone have any questions? I think there's a question in the chat. Phil Miller asks, why did you decide to port to CHARM++ rather than CHARM MPI or adaptive MPI?
Yes, that's a really good question. We wanted to have the full set of CHARM++ features available to us, particularly the language, from the language point of view, because we were trying to develop a new version of the code, and so we didn't want to be restricted by the MPI features. But that was a luxury, I would say, that we had for this particular project. For all our projects, we just try first the adaptive MPI.
Okay, I think Ronak has a question.
Yeah, I was curious if you used the OMP integration at all, the OpenMP integration at all, or anything to do intranode performance, because you saw that you still had a bit of a tail, and maybe OpenMP style things would help with that.
Okay, that's a good point, Ronak. We didn't. So we just use the regular expression. So maybe that's something we can try later.
Okay.
Yeah.
Okay. There are no any other questions. Thank you, Esteban, for that talk. Okay, so next we have Thomas Quinn from the University of Washington, and he will be talking about a universe of ChaNGa applications. So Thomas, you can get started whenever you're ready. I think Thomas, you're muted if you're speaking.
Some issue, Tom? Tom would have nice videos, so we can just say, send your talk to someone else.
Sanjay in the chat, Tom said he can't unmute himself. I don't know if one of the hosts or something is able to control anything there, or if there's something going on.
Can you hear me now?
Yep.
Yeah. Okay. All right, now I got it. Figure out how to share. So my main zero window has shut down. That's my problem. So now I can't share my screen. I'm afraid I'm going to have to. Yeah.
Should we switch your talk, Tom?
I might have to log out and log back in.
But if you go a little bit late, are you okay? Then we can maybe do another talk.
Okay. Yeah. Yeah, so I don't know what's happened. All right, yeah, how about you have somebody else go out and I'll.
Wow. And that's Joseph Hutter, so we don't know whether he's ready.
I'm here.
Ready, Joseph? Okay, why don't you start?
Can you see me? Yep. And then let me share screen. So Tom, you'll have to unshare screen so that I can.
Oh, I am screen sharing. Oh, hold on. Okay. If you can hear me and I can share my screen, then we might be good.
It looks like it might have been a background. There were some nice trees.
Excellent.
Oh, there we go. Yeah, we can see it.
Okay. Sorry about that. All right. Thank you for your patience. I'm going to be talking about, we've had a number of astrophysics talks already today. I'm going to be talking about ChaNGa, which is written by a collaboration between a research group called the M-Body Shop and the Parallel Programming Lab. I'd like to point out sort of the emblem we have here for the M-Body Shop. The top visualization is a protoplanetary disk. So this is on scales of our own solar system. The bottom panel is showing a filament of galaxies that spans many megaparsecs in size, so a fraction of the universe. And so we are doing astrophysical calculations over a huge range of scale, enabled by the algorithms in ChaNGa, and ultimately enabled by the CHAN++ languages. So let me start. So the talk will be an overview of the various applications we're able to do with this framework. And I'll start with the largest scales, where the problem is understanding what the dark matter of the universe is. And as this graphic shows, is that 95% of the universe is stuff that is not like you and I. It's not protons, neutrons, electrons like we're made of. In fact, the only thing I really know about it is that it acts gravitationally. There are various particle astrophysics candidates. One of the early success of simulations was to show that one of the primary candidates, known as the neutrino, is not what the dark matter is. And there are other more exotic candidates which we're trying to confirm or rule out with our simulations. So the good thing, yes.
I think your mic gain might be just a little high. It's kind of cutting out a little bit of your top range.
Okay. Yeah. All right. Let's see if I can do this. This is a little tricky. Is that better?
I think so. Just give us a sentence.
Okay. So one of the good thing about dark matter is the physics are simple, and by simple, I mean that we know what Newton's laws are. It's not so simple in terms of computational complexity. It's naively of order n squared because everything tracks everything else gravitationally. It's not simple because there's a huge dynamic range, over 100,000 at least. And so that requires a hierarchical adaptive solver in order to compute it. And furthermore, the hierarchy in space means a hierarchy in time. And so there's a huge range of timescales as well, requiring a multi-step algorithm. And furthermore, there's lots of communication because gravity is a long-range force. And again, to reiterate what I started out with, this dynamic range problem is common to astrophysics because gravity is common to many astrophysical problems, from these cosmological scales all the way down to solar system scales, where in the solar system we're talking about 10-kilometer objects in a billion-kilometer system. So on the largest scales, we can just do gravity. This is work by collaborators of mine using the code PKD-Grav. It just has gravity because gravity wins on the largest scales. But I want to point out that this kind of filamentary structure should be occurring all the way down to galaxy scale. So this image is roughly 100 times smaller than the image on the previous slide, and it has that same sort of structure, and we expect that kind of structure to continue all the way down to perhaps solar system scales. And so, to model all this, we have our code, the Charm Embodied Gravity Solver. It's a massively parallel tree code built on Charm++. And the usability of this code for various problems is built on the fact that it has this framework for doing the gravity algorithm and for doing a couple of basic neighbor finding algorithms. And built on these two algorithms, we're able to model a large number of astrophysical systems. The scaling is excellent. For that image that I showed you on the slide before, we get this kind of scaling. This is on blue waters, running from 8K cores to eighth of a million cores, achieving 80% parallel efficiency. But gravity isn't the only thing. If we looked at model galaxies using only gravity, we get a very different result than what we see in the real universe. And so, and furthermore, the problem with dark matter is that it's dark, right? You can't really see it. You've got to look at its impact on the visible structures. And so, and clearly the baryonic physics has its consequences. So to calculate the baryonic physics, we use this technique called smooth particle hydrodynamics. It's a good technique when you have high Mach number and large density contrast hydrodynamical problems. You can think of it as essentially a Monte Carlo method for solving the Navier-Stokes equation. And computationally, it's nice for us because it represents the fluid as particles, the same way we represent the dark matter as particles. And so it's a natural extension for the particle method we have for gravity. And so as an application, we'd like to test the nature of the dark matter itself. And again, we can't just look at the dark matter. We have to look at how the dark matter affects the baryons, the stars, and the gas. And so this is a recent paper by my graduate student, Akasha Cruz, where we have two different galaxies. We got this pair on the left, the pair on the right, and each galaxy is simulated with a standard dark matter model, and with a dark matter model where the dark matter has some interparticle nuclear force. We call it self-interacting dark matter. That's the SI in these labels. the scale of the picture you see is about the size of our Milky Way. So we're looking at the visible portion of our Milky Way. And you can see that the changing the dark matter model can significantly affect the number of stars that get produced. And by the way, the different panels are just evolution through time. This is earlier time. This is closer to the present day. So, so we can, again, we can program in, using the native finding algorithm, program in this self-interaction in the dark matter and get these predictions about what things would look like if the dark matter model were different. There are other effects going on, even in this simulation. The big effect is recognizing that each galaxy actually has a supermassive black hole buried in the center. Here, this image is the first ever observation of the actual black hole. Here's the shadow of the black hole. And the size of this thing is about 1 million times, actually, this one, 1 billion times larger than the black holes that Nils was talking about earlier. These are indeed large, and they have an effect on the overall evolution of the galaxy as a whole. And this we need to model. And so we have, again, using a neighbor finding algorithm to find where black holes form and how they interact with the nearby material in terms of accretion and feedback. Here we like our black holes to be free range. That is, they're not tied to the center of a galaxy, because we want to explore how such black holes actually get to the center of the galaxy and how they interact as they come in. And let's see if this works. Just sorry, before I get to the movie, here's one question we'd like to know the answer to. We know there's a big black hole in the center of our Milky Way. Are there wandering black holes around the Milky Way? Not so easily observable because, well, they're black. They're only observable when they accrete large amount of material, like they would at the center of our center of a galaxy. So to show how this problem works, this is a movie which I hope is going over Zoom. The white dots are the massive black holes that we're forming. They're in the center of these forming galaxies, which you see are long filaments here. The blue is colder gas. By cold, I mean 10,000 degrees Kelvin. The red is warmer gas. By warm, I mean 1 million degrees Kelvin. And you can see as satellite galaxies fall onto the main galaxies, they bring in their massive black hole. And so you're left with a number of black holes wandering around this Milky Way-sized galaxy, as well as the black hole in the center. And so because of this process, well, the model predicts that around our own Milky Way, there should be a number of these dark black holes, which, well, yeah, so the observational consequences is if we look particularly at galaxies far away, we might see evidence of these black holes by emission off-center from the middle of the galaxy. So speaking of the hot gas, so 1 million degree gas is actually not easy to look at. And so we go to clusters of galaxies, because there the temperature of the gas goes up into the tens of millions of degrees. And that's interesting because 10 million plus degree gas emits in X-rays. So this is a simulation generated from, an image generated from one of our simulations showing the temperature structure in the center of a cluster of galaxies. The other nice thing about clusters is that material you saw blown away from the center of the galaxy can be collected in the cluster as a whole, where it could be observed. So by metals, we mean material that's not hydrogen or helium that collects in the cluster of galaxies, where we can observe it, for example, in highly ionized oxygen. And so these are predictions being made for, say, Hubble Space Telescope observations of clusters of galaxies. Another interesting thing to look at in galaxy clusters is the very central region of the galaxy. Most galaxy clusters have a very large central galaxy. We're trying to understand how such a galaxy comes to exist. And from these images, which I'm showing the density and the entropy and the, temperature, and the bottom one is the entropy as a function of time during a merger event. So that is, the satellite galaxy comes in, interacts with the central galaxy, and generates a huge shock and completely changes the entropy structure in the middle of the galaxy, cluster, which could explain the kinds of galaxies we see and the X-ray emission that we see in centers of galaxy. Just to give you an idea of what how galaxies can change their appearance. So these two central images are from galaxies simulated at the center of galaxy cores, whereas galaxies in the outskirt of clusters tend to have these either spiral or barred spiral morphologies. Again, these are all simulated images from our large-scale structure simulations. More recently, we've been looking at faint satellites of galaxies. This simulation, by the way, the simulation before was run on blue waters. This simulation is run on Frontera. These are a series of Milky Way-sized galaxies. We call it the DC Justice League, where we're honoring the female Supreme Court justices. And what we're interested in here is the faint satellites. And so you can't see those in the images because they're faint, but we can look at the numbers of such galaxies as a function of brightness. This is in weird astronomy units where more negative is brighter. And our simulations are shown with the solid lines, and we're able to match number counts of faint galaxies around nearby galaxies. The Milky Way, the Andromeda, M81, other nearby galaxies have similar numbers of galaxies. And in future observations, we'll be looking for these kinds of galaxies around further out in the universe. So this is recently published work by a graduate student, my colleague. Another thing we're looking at is a little smaller scale, the very centers of galaxies and how those spiral disks actually form. This is a simulation that was run on Pitts Dynt, where we're following the evolution of a galaxy resolved with 1 billion particles. And the importance of the resolution here is we're trying to understand, are those disks thin or are they thick? Because we see a thick disk in our current galaxy. And the interesting result is that the disk actually formed thin, but at various angles over time. And so that if you integrate that over time, you end up with right, they mix together and produce a thick disk. If you have lower resolution, as we once did, you wouldn't be able to resolve how the thin disks form at various angles over time. So again, a recent result from a graduate student at University of Zurich. All right, I'm running short on time, so let me just point out that we have implemented magnetohydrodynamics. These are important as we go down to now stellar size objects. A colleague of mine, Phil Chang, has used the same neighbor finding algorithm to build Voronoi meshes upon which he can use finite difference algorithms to solve the hydrodynamics. Sorry, finite volume. And so he's been using it to model the collisions of stars, in particular the binary stars merging, going down to even, he's also implemented radiation hydrodynamics on a moving mesh version of ChaNGa. Something I'm interested in is protoplanetary disks. Here's an observation of a protoplanetary disk by the Atacama Large Millimeter Array. And so the question is from whence do these rings come from? And we've been modeling the formation of these rings by looking at the collisions of 10-kilometer bodies in a ring around a star, not shown here, that's being perturbed by a planet, which would be unseen in that observation. And the presence of the planet, so here's the position of these 10-kilometer bodies. Here's a mock observation of the dust produced by collisions of those bodies. And you see, we can get those ring structures here because of the presence of an unseen planet. We are also modeling the migration of dust through a gaseous disk. And this is a demonstration how you need high resolution in order to accurately do that modeling. And then finally, from that dust, how do you actually build planets, as well as creating dust? If we have an algorithm that not only detects collisions, but also merges the bodies together, we can model how these smaller bodies aggregate into bigger bodies, aggregate into eventually form the planets. And this is an interesting question because our planetary configuration looks very different than the planetary configuration around smaller stars. Actually, the scales are slightly wrong here. This whole system would fit inside Mercury because this is a much smaller star. And so Spencer Wallace, current graduate student, is modeling the growth of planets in our solar system and around in extrasolar systems like TRAPPIST-1. So again, using the same framework to do the collision detection. And going even smaller, we're interested in what are the circumplanetary disks. So here's a system of planets. What's the disk like around individual planets, particularly the temperature of those disks? All right, so that was a whirlwind. The point I want to make again is that we have just a couple basic algorithms and which we're able to scale efficiently because of the Charm++ features that I enumerate here. And a particular feature is the modularity that a C++ based language brings to us to easily add new physics. But with just those couple of algorithms, we're able to do quite a variety of applications. And so, leading into the next talk, this motivates us. Well, suppose we were more easily able to modify the algorithms and still have them scale. And that's the motivation behind the next talk you're going to hear by Joseph. I should let you know the code's freely available. Also let you know that there's a large user community of the code at this website. And then finally, I'd like to thank the people that have funded this work and thank you for your patience and your listening.
Thank you, Thomas. Are there any questions?
It's getting late in the day.
Yeah. Okay. I think if there are no other questions, thank you, Thomas, again for your talk. And we'll move on to the next talk, which is the last talk of the day, from Joseph Putter from UIUC, and we'll be talking about ParaTreeT, fast general framework for spatial tree traversal. Joseph, you can go ahead when you're ready.
Thank you. Let me share my screen.
Can I ask a quick question? While Joseph is getting screen up, you talk about modular physics with C++. Does that apply to the parallel algorithms part of it, or just the sequential aspects of it?
Essentially, the sequential aspects of it, right? That I can take essentially sequential code, plug it into the neighbor finding algorithm, or say apply it to the neighbors that are found by the parallel neighbor finding algorithm.
Okay.
Okay. Any other questions? Good to go. Okay, so my name is Joseph Hutter, and I'm here to talk to you today about ParaTreeT. ParaTreeT, which stands for the Parallel Tree Toolkit, is a fast general framework for spatial tree traversal. And this is a joint collaboration between researchers here at the University of Illinois with the Parallel Programming Lab and at the University of Washington with the N-Body Shop. So before I introduce ParaTreeT, I'd like to discuss the problem that it seeks to solve. So let's say that you're trying to study a system of bodies in n-dimensional space by calculating interbody forces, applying them, and then advancing the time step, and then you do that over the course of many time steps. So you could do each step in quadratic time, but that'll become intractable once you start looking at larger problems. So you instead might recursively divide the space and let bodies interact with those subspaces instead of each other body. And one common approach to doing this is with tree traversals. But now you've got another problem. You have to implement this distributed tree code and optimize it. And there are a lot of potential bottlenecks. So you have to distribute the problem to a number of processes. As traversals require nodes that are remote, you need to communicate those tree nodes. You need to balance highly irregular load among those processes. Even when traversing a local tree, you need to do that in a cache efficient manner. And on top of that, you're still evaluating your flop heavy models. To add to this issue, often the more interesting problems are the ones that are finer grained and thus require more work. So all you wanted to do was study your spatial models, but now you need a similar level of programming knowledge as you have in your respective subdomain. So ParaTreeT seeks to solve this problem by letting you focus on your models, and we instead provide peak performance and great programmer productivity. Since this is the Charm workshop, let me sing Charm's praises. So on the library side, we get a few awesome wins from using Charm++. So because of that variety of workloads I mentioned in the last slide, you want an adaptive runtime system. And you also want inherent asynchrony, especially as you're fielding remote requests and responses, so that you can continue traversing after arriving on remote nodes. Those tree messages are also variable sized and should be sent out as soon as possible, which is, as opposed to MPI, which is more inclined to larger blocking transfers. And work in space units with chars can be packed up and redistributed as we balance and rebalance load throughout simulations. And for users, they get extensive portability to a large number of systems, which is important when defining a general framework. And when they need to use Charm++ on top of the library and those abstractions, they can just create simple modules with chars instead of needing to hack into areas of the code. Now, before I talk performance, I want to talk about the APIs. So ParaTreeT is able to offer generality without loss of performance because it exposes decisions to the user within a sensible structure through which it can be performant. And those interfaces are built either at compile time with these static APIs, and the more complex decisions are come through polymorphism with dynamic APIs. So let's look at the beginning of a simulation step, and let's assume for now we're on a single thread. So you're going to take these 5 bodies or particles, and you're going to, let's say you create a KD tree, and you're going to get the tree in the middle here. So you still need to take the data that comes from particles and move that into a level of the subspaces and where the parent nodes are. And so we do that with a data class, or a data abstraction. So the user will define a data class with these 3 functions so that they can move data from, they can create summary information in the parent nodes that describe the subtree underneath it. And so for leaves, the library will call this data function on those particles that are in the leaves. And then on the parent nodes, it'll initialize the parent nodes with the empty data constructor, and then it'll constructor, and then it'll pass that information up to the parent nodes from its children through the plus equals operator. And then now let's say you're going to do a traversal. Let's say you're doing a top-down traversal. When you arrive on a non-leaf node, the library will call the open function for you so that you can decide whether you want to continue traversing or use that summary information. So if you want to use the summary information, then we'll call node, and that traversal will stop there. And if you arrive on a leaf, then we'll call the leaf function. So those are 2 separate classes that you'll define. And on top of that, the more complex decisions come through a few different interfaces. So before we were just looking at what it looks like, or what a tree construction looks like on a single thread. But with larger problems that are distributed across processes, you need to define some way of decomposing this to different processes. Since we use Charm++, there's also virtualization, so not just the processes. So with that, you might override one of our standard prepackaged decompositions with fine splitters, and then you need a flush function. And then once the particle domain has been decomposed to a number of processes, then you actually have to build a tree. And that's done with those 2 functions, get branch factor and find child's last particle. And then when you're traversing, if you don't want to use one of the prepackaged traversal types like top down or up and down, then you can define those on your own with this start traversal, which is when just at the outset, and then resume traversal when remote nodes have been received and are ready to be resumed. So here is what the overall user code for ParaTreeT gravity application looks like. And you can see how we encode the decisions we made earlier by looking at what's red underlined. The data class is encoded through the driver, that's that centroid data. The tree type and decomposition type get enums and are passed to the configuration object at the start of the simulation. The traversal type is this start function. So start down means just the basic down traversal. And the visitor class is encoded in the template parameter of that function. And then, so in here, the centroid data and gravity visitor code live in the user code directory, and all the library code is separate. So we've already implemented a lot of the major commonly used tree decomposition and traversal types. So KD trees, most people know. And then there are OT trees and binary OT trees. And those are n-dimensional. They aren't just for 3 dimensions, but you can think about them in 3 dimensions. And then on top of that, we also have a longest dimension tree that we'll look at later, which is built on the KD tree concept. And then we offer decompositions that match 1-to-1 with those tree types. And also decompositions built on the space filling curves. So the Morton curve and the Piano-Hilbert curve. In addition, there's a few different traversals. So normal down traversal just uses a stack. It's the one that you write in every computer science programming class. We also have a more cache efficient transpose down traversal, which doesn't use a stack, but uses recursion. And then an up and down traversal for something like k-nearest neighbors. So in seeking avenues to evaluate ParaTreeT performance, we chose to use cosmology because, as Tom mentioned in his previous talk, it has a large dynamic range in spatial scales, which lends itself towards hierarchical structures like trees. It has a large variety of algorithms and physics modules, and it features some pretty large data sets where you want peak performance. So one of the central tenets of ParaTreeT is that clever optimizations to tree traversals in general can allow you to perform better, in fact, than even specialized codes. So we'll see that right now. So I actually presented at the Charm Workshop in 2019 about the beginnings of ParaTreeT and about my work on a new shared memory software cache model for received tree nodes that want to be reused within a traversal step. And that shared memory cache model is weight-free and lock-free using some pretty cool atomics. I won't repeat that talk, but I will show you some of its benefits. So you can see I've compared the weight-free cache model when looking at a simple gravity traversal, and I've compared it against a sequential model, which would be 1 software cache per thread, and an exclusive write model, which is a little more complicated, but still not sufficient. And that's where the cache is shared memory, but inserts require access to a lock. And those do not scale as effectively. This was done in Stampede 2 with Skylake X nodes and 24 cores per process. With historical applications, you'll notice that when particles are divided across processes, you also need to divide the hierarchical subspaces that contain these particles. So you can do this easily if the division of particles you choose matches your tree type. But if you use a space filling curve, which has shown to be fairly performant in decomposing, and space filling curves is a way to map positions in space to a point on a number line. If you use a space filling curve to assign particles to processors, but still use an OT tree, then you need a way to merge these subspaces together when they're built on different processors, different threads. And that's a large synchronization cost, especially at scale. So we solve this problem with the partition subtrees model, which uses 2 parallel char arrays, where subtrees is a char array that acts as a distributed data structure for sections of the global tree. And partitions which is a char array for units that are groups of particles. And this serves to reduce synchronization during the tree build. And it makes, well, I'll explain that in a second. So first you label particles according to their assigned partition index. And then you build the subtrees, and you get buckets like the thick ones, which those are leaves in the global tree. And then you assign those leaves to partitions, and if they need to be split up, then you assign them by copy. And so you'll sometimes get, as you can see with that thin bucket, that's a local partition bucket that splits a tree node leaf. So in addition to reducing synchronization, we also make tree ignorant decompositions possible. So you can write your decomposition strategy separately from your tree builder, instead of needing to write one for every pair of them. And now to the fun stuff. So in evaluating Barn-Site gravity traversals, we found that ParaTreeT performs 2 to 3 times better and also scales better than ChaNGa when doing the same exact work. This is because of the improvements we've shown earlier, and because the modular design that we enforce drives a smaller working set, which leads to better cache performance. And I've also plotted what I call basic trav, which is the stack-based traversal type I mentioned earlier. And I use this to show the effect that cache efficiency has on traversals. This was done on Summit with its Power 9 CPUs with two-way SMT. And so the exciting thing about this is that the user code to do this in ParaTreeT is only 135 lines. You saw some of that with the gravity driver class I showed earlier, and then also there's a gravity visitor and centroid data class that combines to 135 lines. But if you compare this to ChaNGa, there's 4,500 lines of tree and monopole gravity code in ChaNGa. So some pretty impressive productivity here. Then we also looked at another application, which Tom also mentioned, and that's smooth particle hydrodynamics, which is a method for astrophysical fluid simulations, and that also leverages tree traversal. So we also compare favorably against the specialized application here, Gadget 2, which specializes in gas and dark galaxy evolution, hence Gadget. We report a 4 to 8x speed up, and most of the speed up is due to using a k-nearest neighbors algorithm for finding neighbors during SPH, compared to what Gadget 2 does, which converges on a ball size with bisection steps. And we're able to implement this k-nearest neighbors within ParaTreeT's tight abstractions. And in the lines of code category, we're still winning here by a power of 10. And this was done on StampP2 with Skylake X nodes. So with ParaTreeT development, we sought out an additional challenging problem, in this case in astronomy as opposed to cosmology, to see how ParaTreeT would handle it. So we worked with Spencer Wallace at University of Washington on the evolution of a protoplanetary disk, which is mostly 2D, hence disk. So traditional 3D trees and decompositions suffer on this application because they waste resources branching for the tiny third dimension of the disk. So we came up with a different tree and decomposition type, which is the longest dimension tree, which is a KD tree, but it branches always in the longest dimension of the box. And you can see just how well it performed compared to the two Octree implementations, one in ParaTreeT and one in ChaNGa. And this was done by implementing the decomposition and tree interfaces we mentioned earlier. This was also done in StampP2. And here's the result of that newfound performance. We were able to do a groundbreakingly fine-grained simulation of a protoplanetary disk and the planetesimal collisions therein. And so you can see plotted here the number of collisions and their distance from the central star and also the orbital period. And this was done on Bridges 2 for 10 million particles. In addition to our optimizations, we also built out some of the load balancing modules needed to reduce tails. So I've shown a projections profile, which comes with Charm++, of the gravity traversal step at 1500 cores on Stampede 2, and broken it down into sections. So on the left, local traversals. On the right, from top to bottom, we've got communication overhead, remote traversal, traversal resumptions, cache insertions, and cache requests. And you can see that the idle time increases as the traversal step winds down. So after a step like this, you can always reassign work to processes by one of a few ways. So at this scale of 1536 cores, ParaTreeT's built-in load balancers can reduce this simulation's total runtime by up to 26%, either by mapping measured load to the space filling curve and redistributing it in chunks. That's the prefix method. Or by aggregating load and assigning it recursively in 3D space. And that's the orthogonal recursive bisection method. And so there are a few things that we're looking forward to with ParaTreeT, and that is one of those is building out multi-tiered time stepping, which is especially effective when looking at problems where particles or bodies, some of them are moving very quickly, and so you want a smaller time step for those, but many of them are also moving slowly, and you don't want to waste work iterating on those particles, the slow-moving particles, when you could just be focusing on the fast-moving ones. We also want to build out more physics modules to get a larger user base. We're also interested in building on some of the work that Jen Chow and Malind did at Purdue with GPU kernels, and that's both evaluating those flop-heavy models I mentioned earlier, and also local tree traversal has been shown to be performant on a GPU. And we're also always looking at more optimizations to ParaTreeT that will allow for more users to have better performance across a large variety of applications. And so that's all. Thank you.
Thank you, Joseph. And are there any questions? Yes, Professor Kale, I think.
No question, I'll ask it later.
Okay. One question I had was in the comparison that you showed with the Gadget 2 simulation. If I'm not wrong, Gadget 2 does this symmetric neighbor finding, where if one of the particles is the neighbor of the other, then the other particle is also the neighbor of that particle. So if you're doing k-nearest neighbor searching, I don't think that, are you still preserving symmetry or?
Yep, so we do preserve symmetry. It's a great point. By taking the union of these two directions of neighborhood, and then we average the effect, the forces on each particle from inward and outward.
Okay.
Yep, we observe that.
Okay. Are there any other questions?
So are there any other external users yet?
Apart from Spencer and Tom, not yet, but we're looking forward to working with people externally as we build out more physics.
Sure. Okay.
Okay, I think with that, we are at the end of the first day. Anyone have any other comments?
Right. We remember tomorrow's keynote will be a little bit later in the morning. The other talks in the morning, and we start at 9 a.m. again, if I'm not mistaken. And I also want to thank the three organizers, Zane, Jamin, and Matthias. We'll thank them again tomorrow, but do you have any other comments for tomorrow? Any one of you? If not, well, let's stop here then for the day. Unfortunately, no banquet. So next year, we'll make up for it. All right, bye then.
All right. Thanks, everybody.
Thank you, everyone.